CONNELL-SEC.
Welcome to Mastering Large Language Models for InfoSec Professionals. This is Section 1, Introduction to Large Language Models. Can machines truly understand language? The question of whether machines truly understand language is a complex one with no easy answer. There are different perspectives on this topic, and ultimately, it depends on how you define understand.
Arguments for machine learning include impressive performance. LLMs can perform remarkable feats with language, including generating realistic text, translating languages, and writing different creative formats of text content. LLMs are constantly being improved, and their ability to handle complex language tasks is growing rapidly. Some argue that the way artificial neural networks process information shares similarities with how human brains process language.
Arguments against machine understanding include limited comprehension. LLMs often lack true understanding of the context and meaning behind the language they generate. They can produce grammatically correct and even creative outputs, but may not grasp the deeper nuances of human communication. LLMs can only generate outputs based on the data they have been trained on, which can lead to biases and factual errors. They lack the real-world experiences and knowledge that humans draw upon to understand language. LLMs don't have the same intentions or goals as humans when using language. They may not be able to truly interpret the intent behind a question or a statement.
Here are some nuances to consider. Perhaps, instead of a binary understand or not understand, it's more helpful to think of machine language understanding as existing on a spectrum. LLMs may not have the same deep understanding as humans, but they can still process and respond to language in a sophisticated way. There are different kinds of understanding, such as semantic understanding, meaning, pragmatic understanding, context, and social understanding, intentionality. LLMs may excel in some areas, but not others. As AI research advances, the capabilities of LLMs are likely to continue expanding. Whether or not they ever achieve true understanding is a question that may remain open for years to come.
Overall, the question of whether machines can truly understand language is a fascinating and complex one. There is no single definitive answer, and it's important to be aware of the different perspectives on this topic. While LLMs are demonstrably impressive with language, their limitations in context, intentionality, and real-world knowledge should be acknowledged. The focus should be on understanding the strengths and weaknesses of LLMs and using them responsibly and ethically.
Let's take a look at what will be covered in this course. Understanding. What are large language models? How do they work? And what are their core abilities?
Training techniques. How do large language models learn from massive datasets without explicit labels, using techniques like self-supervised learning and masked language modeling?
Security applications. Exploring how LLMs can be used for tasks like vulnerability detection, phishing analysis, and malware research in the IT security domain.
Limitations and biases. Discussing potential risks like adversarial attacks, data poisoning and privacy concerns, and highlighting mitigation strategies.
Comparison with traditional natural language processing systems, differentiating large language models from rule-based systems, emphasizing the strengths and limitations of each approach.
Real-world security scenarios, using engaging examples like analyzing suspicious emails or code snippets to illustrate large language model capabilities in action.
And data analysis applications, relating LLM training to data analysis in the security context, showcasing how LLMs can extract insights from security logs and breach reports.
Let's define what a large language model is. Let's start with a simple explanation first. A large language model is a powerful type of artificial intelligence that can understand and generate human language, like text, code, scripts, and even creative formats like poems or musical pieces. Imagine a digital library with billions of books and the ability to learn and use them like a master writer. That's a large language model.
And now, for a detailed definition. A large language model is a complex statistical model trained on massive amounts of text data. It learns the patterns and relationships between words, allowing it to generate new text, translate languages, answer questions, and even write different creative formats of content. LLMs use advanced neural network architectures with millions or even billions of parameters. These networks process information like the human brain, analyzing and predicting language based on what they've been trained on.
Imagine this. You're analyzing a suspicious email for potential phishing attempts. You need to understand the relationships between different words and phrases to assess intent and context. This is where transformers and attention come in.
Let's take a look at the transformer architecture. Think of a transformer as a complex multi-stage processing pipeline. Each stage, called an encoder or decoder, analyzes the input text. Here's a simplified breakdown. Input embedding. Words are converted into numerical vectors, like unique IDs in a dictionary. Encoder stack. The text goes through multiple encoder layers. Each layer consists of 2 sub-layers for attention and connecting to a feed-forward network. Self-attention. Each word attends to all other words, analyzing their relationships and importance. This is like focusing on different parts of the email, understanding how each word connects to the overall meaning. Positional encoding. The order of words matters. This stage ensures the model understands the sequence of the text, crucial for things like understanding timestamps or identifying keywords in specific orders. Feed-forward networks. These add non-linear transformations to the data, allowing the model to learn complex patterns and relationships between words. Decoder stack for generation tasks. Similar to the encoder, but focuses on generating new text based on the encoded input. Imagine the decoder crafting a response email to the suspicious message, mimicking the style and tone while subtly warning the recipient. And finally, output layer. This translates the processed information back into human-readable text or another desired format such as code or script.
Now let's look at the power of attention. Attention mechanisms are what make transformers special. Think of them as magnifying glasses helping the model focus on the most relevant parts of the text. Here's how they work. Each word calculates an attention score for every other word, indicating its relative importance. Words with higher scores receive more weight in the overall representation, like zooming in on suspicious keywords or phrases. This dynamic weighting allows the model to capture complex relationships and nuance, which is crucial for tasks like identifying deceptive language or spotting hidden messages.
Understanding transformers and attention mechanisms is valuable for IT security professionals. Let's take a look at a few reasons why. Malware detection. LLMs can analyze code structure and identify similarities to known malware, using attention to focus on critical pieces of code. Phishing analysis. Attention can help identify subtle red flags in emails, like unusual keyword pairings or unexpected emphasis on specific phrases. And vulnerability discovery. Large language models can analyze large code bases and use attention to detect patterns associated with vulnerabilities, potentially streamlining the security research process. Let's take a look now at embedding and vector databases.
Imagine IT security professionals hunting for malicious code amidst millions of lines, needing to identify similarities and patterns instantly. Vector databases and embeddings make this possible.
Picture this. Each word in your language is no longer just a string of letters, but a point in a multi-dimensional space called an embedding space. Think of it as a giant map where words with similar meanings cluster together. The closer two words are, the more related they are.
Enter the vectors. Each word gets converted into a unique vector, a series of numbers representing its various semantic properties, like context, usage, and even emotional connotations. Imagine these vectors as detailed profiles for each word, capturing its essence beyond just letters. Need to find all code snippets containing suspicious keywords? Vector databases let you search for similar word profiles in the embedding space, pinpointing relevant code with lightning speed. Think of it as searching for faces on a photo map, but for words instead.
Want the LLM to generate realistic phishing emails or security alerts? It can access this map of word relationships, choosing words with the right meaning and tone based on their proximity in the embedding space. It's like the LLM painting a picture with words, using their relationships as strokes.
How can LLMs be used for IT security applications? By comparing code vectors to known malware profiles, LLMs can rapidly identify malicious code lurking in vast codebases.
Analyzing large streams of security data, like news articles or social media chatter, using vector similarity allows for fast tracking of emerging threats and trends.
LLMs can explore different code combinations by navigating the embedding space, potentially discovering vulnerabilities by identifying similar patterns to known exploits.
Large language models are powerful tools, but just like any tool, they have limitations and potential pitfalls we need to be aware of. The bias blind spot. LLMs learn from the data they're fed, and just like us humans, they're susceptible to inheriting the biases and factual errors embedded in that data. Imagine training an LLM on a dataset of historical malware descriptions. It might develop a bias towards certain software or programming languages, potentially overlooking threats originating elsewhere. These biases can have serious consequences in the security field. Imagine an LLM analyzing network traffic based on biased data. It might flag legitimate activity as suspicious or overlook malicious activity targeting specific demographics or systems.
Combating the bias monster. Researchers are actively tackling this issue through various approaches such as data debiasing techniques, cleaning and filtering training data to remove harmful biases, fairness-aware algorithms, designing large language models that consider fairness and reduce bias during the learning process, human oversight and explainability, ensuring human involvement in decision-making and promoting transparent explanations for large language model outputs.
Let's take a look at some security applications for large language models. Vulnerability detection. Reducing bias in LLM-powered vulnerability scanners can prevent overlooking threats targeting specific systems or software used by marginalized groups. Phishing analysis. Fairer large language models can better identify deceptive language and social engineering tactics regardless of cultural context or target demographics. And incident response. Explaining how large language models arrive at their conclusions in security investigations helps identify potential biases and ensures fair and accurate response strategies.
Let's take a look at connecting large language models to security applications. Problem 1. Code vulnerability detection. Sifting through mountains of code searching for vulnerabilities is a time-consuming and arduous task, often relying on static analysis tools with limited understanding of context and intent.
Large language models trained on vast codebases can analyze code structure, identify patterns associated with known vulnerabilities, and even predict potential exploits before they occur. Their ability to understand context and relationships between code elements surpasses traditional static analysis, allowing for earlier detection and mitigation of threats.
Problem 2. Phishing analysis. Distinguishing legitimate emails from cleverly crafted phishing attempts can be tricky, with attackers constantly evolving their tactics to bypass traditional filters.
Large language models trained on real-world phishing data can analyze email text, identify subtle red flags like keyword manipulation, unusual punctuation patterns, and inconsistencies in tone and sender information. This allows for more accurate detection and filtering of phishing emails, protecting users from falling victim to these scams.
Problem number 3. Malware research. Analyzing and understanding new malware strains requires expert knowledge and time-consuming manual investigation.
Large language models can automate the initial analysis of malware code, identifying similarities to known threats, extracting malicious intent, and even generating potential mitigation strategies. This empowers security researchers to focus on complex tasks and accelerate the threat intelligence gathering process.
And let's look at a few bonus applications. Incident response. Large language models can analyze vast amounts of incident data, identifying root causes, suggesting containment strategies, and predicting potential attack vectors.
And security threat intelligence. Large language models can scan news articles, social media chatter, and other open-source data to identify emerging threats and track changing attack trends.
While large language models offer incredible potential for security applications, it's crucial to acknowledge and discuss the lurking shadows of potential security risks. Imagine a cunning hacker crafting malicious inputs designed to manipulate large language model outputs. These are adversarial attacks aimed at the following:
Generating false positives. Injecting subtle triggers into code or text can trick large language models into falsely flagging innocent activity as suspicious, disrupting operations and wasting resources.
bypassing vulnerability detection. Attackers can craft code with slight modifications that evade large language model detection, potentially leaving systems vulnerable to exploitation.
And generating deceptive outputs. Imagine a large language model trained on biased data. Attackers could exploit this bias to manipulate the LLM into generating harmful content, like fake security alerts or misleading reports.
Now let's talk about data poisoning. Think of a hidden poison seeping into the data large language models learn from. This is data poisoning, where attackers intentionally inject malicious data into training datasets to introduce biases. Poisoned data can skew the model's understanding of certain scenarios, leading to biased and discriminatory outputs with potentially harmful consequences.
Conceal vulnerabilities. Attackers can poison data with specific patterns that mask actual vulnerabilities, leaving systems undetected and exposed.
And manipulate large language model behavior. Imagine poisoning a large language model used for phishing detection with realistic but harmless examples. This could train the model to ignore actual phishing attempts, compromising security.
Let's take a look at privacy concerns. Large language models often learn from massive datasets containing sensitive personal information. This raises concerns about data leaks. The training data itself may be vulnerable to breaches, exposing private information unintended for model training.
Model inversion attacks. Researchers have shown how analyzing large language model outputs can potentially reverse engineer the training data, potentially revealing private information that shouldn't have been learned.
And inferred relationships. Even without direct access to individual data points, large language models can potentially infer relationships between different pieces of information, raising concerns about potential privacy violations.
So let's talk about mitigating the risks. It's essential to acknowledge these concerns and actively work towards mitigating them. Robust training practices. Employ advanced data cleaning and anomaly detection techniques to identify and neutralize poisoned data.
Adversarial training. Expose LLMs to varied and adversarial inputs during training to improve their resilience to manipulation.
Explainable AI and human oversight. Develop methods to understand and explain how LLMs arrive at their outputs, ensuring human scrutiny and accountability.
And strong data security measures. Implement stringent data security practices to protect training data from unauthorized access and leaks. Now let's compare large language models to traditional natural language processing techniques like rule-based systems. Imagine an experienced security analyst meticulously crafting a set of if-then rules to identify network intrusions. That's the essence of rule-based systems. They excel at precision. Precisely matching predefined patterns leads to accurate identification of known threats. Explainability. Rules are clear and readily understood, making it easy to trace how the system arrived at a decision. And controllability. Security professionals directly control the rules, providing a sense of certainty and oversight.
Rule-based systems also have limitations such as limited adaptability. They struggle to handle novel threats or variations on existing patterns, potentially leaving vulnerabilities undetected. Maintenance burden. Manually crafting and updating rules is time-consuming and difficult to scale with complex threats. And lack of context. Rules often focus on specific patterns, neglecting the broader context and nuance of language, which can lead to false positives or missed threats.
Now let's take a look at large language models. Think of an LLM as a master linguist constantly learning and evolving, able to analyze vast amounts of data and adapt to new situations. They excel at generality. LLMs can handle diverse language constructs and contexts, potentially identifying novel threats and nuanced variations on known patterns. Scalability. They can analyze massive data sets, making them well-suited for handling large-scale security operations. And adaptability. LLMs continuously learn and refine their understanding, potentially staying ahead of evolving threats.
But LLMs also have limitations such as black box effect. Their internal workings can be opaque, making it difficult to understand how they arrive at certain conclusions, potentially hindering trust and explainability. Potential for bias. LLMs learn from the data they're fed, inheriting its biases and factual errors, which can lead to discriminatory or inaccurate outputs. And computational cost. Training and running LLMs requires significant computational resources, which may not be readily available in all security settings.
Both large language models and rule-based systems have their place in the IT security arsenal. The optimal approach often involves a hybrid strategy, leveraging the strengths of each.
Rule-based systems for known threats. Precise patterns can effectively detect common attacks.
Large language models for unknown threats. Adaptability and context awareness can identify novel tactics and variations.
And human oversight and explainability. Regardless of the technology, human involvement is crucial for responsible decision-making and understanding the reasoning behind outputs.
Let's look at some examples to illustrate large language model capabilities. Large language model versus phishing. Imagine you receive an email that seems too good to be true, claiming you've won $1 million, but need to click a suspicious link to claim it. A large language model, trained on countless phishing examples, can analyze this email like a master detective.
Spotting red flags. The large language model can identify subtle clues like unusual sender addresses, inconsistencies in wording and tone, and hidden keywords associated with phishing attempts.
Contextual analysis. It can analyze the email in the context of your recent interactions, flagging unusual offers or inconsistent language compared to known senders.
And generating explanations. The large language model can provide a clear explanation of why it suspects the email is phishing, highlighting specific red flags and offering evidence-based reasoning.
Large language model versus code vulnerabilities. Picture yourself tasked with scouring a complex codebase for potential security vulnerabilities. A large language model can be your AI code-reading sidekick.
Pattern recognition. Trained on vast codebases with known vulnerabilities, the large language model can identify similar patterns and structures that might indicate potential exploits.
Contextual understanding. It can analyze the code in its broader context, understanding the relationships between different modules and functions to identify potential weaknesses.
And predictive analysis. The LLM can go beyond just identifying existing vulnerabilities. It can suggest potential attack vectors and recommend preventative measures based on its analysis.
Think of large language model training as a sophisticated detective academy with massive data intake. Security logs, breach reports, threat intelligence feeds. LLMs devour vast amounts of data, learning the language of threats, patterns of attacks, and nuances of vulnerabilities.
Uncovering connections. Beyond just keywords, large language models analyze relationships between data points, identifying correlations between seemingly unrelated events, and piecing together the bigger picture of attack campaigns or emerging threats.
And evolving expertise. As new data floods in, LLMs continuously refine their understanding, adapting to changing tactics and evolving threatscapes, staying ahead of the curve.
Now picture the security professional armed with a large language model-trained AI partner. Automated anomaly detection. No more tedious manual sifting. LLMs scan mountains of data, flagging unusual activity patterns, suspicious login attempts, or deviations from normal network traffic, freeing up analysts for deeper investigations.
Threat trend analysis. Large language models identify clusters of similar breaches, track malware propagation across different systems, and predict potential attack vectors based on historical data, informing proactive defense strategies.
And enhancing incident response. Analyzing past breach reports with large language models helps identify attacker motivations, preferred tactics, and potential vulnerabilities exploited. This knowledge can optimize incident response protocols and prevent future attacks.
Remember, large language models are not magic. Data quality matters. Garbage in, garbage out. Biased or inaccurate data can lead to skewed insights and unreliable predictions.
Explainability and trust. Security professionals need to understand the reasoning behind large language model outputs to ensure trust and avoid implementing flawed recommendations.
And finally, human oversight is crucial. While large language models automate data analysis, human expertise remains essential for interpreting insights, making informed decisions, and ensuring ethical and responsible use of the technology.
This concludes Section 1 of the course, Introduction to Large Language Models. This is Section 2, Hosted Large Language Models versus Local Large Language Models. In this section of our course, we will be comparing hosted large language models, hosted by the vendor, with local large language models hosted on your own servers. Let's look first at hosted pre-trained large language models. Hosted pre-trained LLMs are ready-to-use models offered by cloud platforms like OpenAI and Google AI. These models have already been trained on massive datasets for specific tasks, such as text generation, translation, or question answering.
Let's take a look at their characteristics. Accessibility. Easy to use through APIs and user interfaces, requiring minimal technical expertise. Variety. Wide range of pre-trained models available for different tasks and domains. Scalability. Can handle large volumes of data and requests due to the cloud infrastructure. Customization. Limited customization options compared to local models. And security. Data privacy can be a concern, as it resides on remote servers.
Let's take a look at a few examples. OpenAI's API offers models like GPT-3 for text generation, Codex for code generation, and Jurassic 1 Jumbo for question answering. Google AI's pre-trained models include T5 for text summarization, Palm for open-ended question answering, and Mina for chatbot conversation.
Some use cases for hosted large language models include content creation, such as generating product descriptions and marketing copy, machine translation, chatbots and virtual assistants, data analysis and summarization, and research and development.
Now let's take a look at local pre-trained large language models.
Local pre-trained large language models are models downloaded and trained on your own hardware infrastructure. These models have already been pre-trained on general or domain-specific datasets, providing a solid foundation for further customization and fine-tuning. Some characteristics include control. You have complete control over the model, its training data, and security protocols. Customization. Highly customizable, allowing you to fine-tune the model with your own data and tailor it to specific tasks and domains. Privacy. Data never leaves your premises, ensuring maximum privacy and control over sensitive information. Technical expertise. Requires expertise in data science, deep learning, and system administration. And resource-intensive. Demands powerful hardware and ample storage space for training and deployment.
Now let's take a look at some examples. Hugging Face offers a vast library of open-source pre-trained models like Lambda, Jurassic 1 Jumbo, and Bloom, which can be downloaded and locally fine-tuned. Many research institutions and companies develop and train their own pre-trained models for specific domains like healthcare, finance, or legal tasks.
Use cases include tasks requiring high security and data privacy, such as financial analysis and medical diagnosis. Domain-specific applications where pre-trained models lack sufficient expertise, such as legal document analysis and scientific paper summarization. Research and development of novel LLM architectures and customization techniques. And businesses with high-volume LLM usage, where local deployment may be more cost-effective than hosted solutions. Now let's take a look at hosted untrained large language models.
Hosted untrained large language models are bare-bones model architectures provided on cloud platforms like Google Cloud TPUs or Amazon Bracket. These models haven't been pre-trained and require your own data and training configurations to become functional. Some of their characteristics include flexibility. Offer ultimate control over training data, model parameters, and architecture, allowing you to tailor the model to your specific needs like a blank slate. Scalability. Leverage the powerful cloud infrastructure for resource-intensive training processes. Technical expertise. Requires significant expertise in data science, deep learning, and model training procedures. Time investment. Training your own large language model can be time-consuming and expensive. And lack of guidance. Limited pre-existing knowledge or community support compared to pre-trained models.
Let's take a look at a few examples. Google Cloud TPUs offer access to various LLM architectures like Palm and Megatron Turing NLG, allowing you to train them with your own data from scratch. Amazon Bracket provides access to several LLM architectures for research and development purposes, requiring the user to handle all aspects of training and deployment.
Some use cases include research and development of entirely new large language model architectures and capabilities, training models on sensitive or proprietary data that cannot be used for pre-trained models, applications requiring highly specialized and customized performance that existing pre-trained models cannot achieve. Organizations with the resources and expertise to manage the complex training process and potentially benefit from cost savings in the long run.
And finally, we look at local untrained large language models. Local untrained large language models are the ultimate DIY heroes of the language model world. Imagine crafting your own language model from scratch, brick by digital brick, on your own hardware and fueled by your own data. In this category, you start with a bare-bones large language models architecture, like the open-source Lambda or Jurassic 1 Jumbo, and train it entirely on your own terms. Think of it as building your own linguistic citadel, customized for your specific needs and data treasures.
Characteristics of local untrained large language models include ultimate control. You hold the reins over every aspect of the model, from data selection and architecture to training parameters and deployment. Data privacy. Your data never leaves your premises, offering maximum security and control for sensitive information. High customization. Tailor the model to your specific tasks and domains, achieving unparalleled precision and performance for niche needs. Technical expertise. Demands deep expertise in data science, deep learning, and system administration for setting up and managing the training process. Resource-intensive. Requires powerful hardware and ample storage space to handle the heavy lifting of large language model training. And time investment. Training a large language model takes time and patience, with no guarantee of success until the experiment comes to fruition. Examples of local, untrained large language models include open-source large language model architectures like Lambda, Jurassic 1 Jumbo, and T5 can be downloaded and trained locally on your own hardware. Companies and research institutions often develop and train their own untrained large language models for specific domains and tasks.
Let's take a look at some use cases. Highly specialized tasks. Train models for niche applications like legal document analysis, medical diagnosis support, or scientific paper summarization. Sensitive data handling. Process confidential information like financial data or medical records within your secure environment, eliminating cloud dependency. Research and development. Experiment with cutting-edge large language model architectures. Design and train novel models for specific research goals and push the boundaries of language processing. And cost-effective long-term usage. For high-volume usage, local deployment can be more economical than pay-per-use cloud models in the long run.
Now, let's take a look at some challenges with local untrained large language models. Data collection and preparation. Gathering and cleaning enough relevant data to train an effective large language model can be a massive undertaking. Technical complexities. Setting up the training infrastructure, tuning parameters, and troubleshooting issues require expert knowledge and problem-solving skills. And time and resource commitment. Local large language model training demands patience, resources, and a willingness to learn and adapt as you go.
Remember, local untrained large language models are not for the faint of heart. They require dedication, expertise, and a clear understanding of your goals and resources. However, for those who possess the technical know-how and have specific needs that demand ultimate control and customization, building your own large language model can be a rewarding journey of innovation and pushing the boundaries of language processing.
Let's peel back the curtain on the enigmatic world of local large language models. Local LLMs proudly occupy two distinct sections within that spectrum. Imagine adopting a pre-trained champion from the large language model zoo like Lambda or Bloom, then nurturing it on your own data farm. These models arrive with a base level of expertise, eager to be fine-tuned to your specific tasks and domains.
For true linguistic pioneers, sculpting your own large language model from scratch might be the ultimate thrill. Start with a bare-bones architecture, feed it your unique data diet, and witness its transformation into a bespoke language powerhouse.
But why choose a large language model that calls your own hardware home? The advantages are as compelling as they are diverse. Your data never leaves your secure digital fortress, offering unparalleled privacy and control for sensitive information. Think Fort Knox for your linguistic treasures.
Mold your large language model like clay, shaping its skills to perfectly fit your needs. No more fitting your project into a pre-baked large language model mold. Here, the mold bends to your will.
And forget paying per sip at the cloud large language model fountain. For organizations with thirsty workflows, owning your own linguistic wellspring can offer significant cost savings in the long run. With more and more cloud subscriptions, such as Azure and AWS, offering servers optimized for machine learning and large language models, pricing is expected to decrease over time for operating such servers in the cloud.
Of course, with great linguistic power comes great responsibility. Owning a local large language model is no walk in the park. Be prepared to don your data wrangler hat and hardware maestro cape. Setting up, training, and maintaining your large language model demands significant technical prowess. These language leviathans have a voracious appetite for processing power and storage. Ensure your machine park can handle the computational feast your LLM desires. While you bask in the autonomy of your linguistic kingdom, you might miss out on the latest large language model advancements and community knowledge readily available in the hosted world. Self-sufficiency is key.
Remember, choosing between hosted and local large language models is like picking your perfect linguistic steed. Understanding the different breeds, their strengths and quirks, empowers you to make an informed decision for your unique landscape. And for those ready to venture into the local jungle, don't forget your trusty compass, Hugging Face. This vibrant platform offers a diverse menagerie of open-source large language models, many ready to be adopted and trained in your own digital domain. Ultimately, whether you prefer the convenience of hosted models or the bespoke power of owning your own large language model, the key is to understand your needs and resources. With informed choices and a dash of digital bravery, you can chart your own course on the ever-evolving large language model landscape.
Imagine embarking on your large language model adventure. Do you choose the sunlit path of convenience paved with cloud access and pre-trained wonders? Or do you forge your own trail, demanding control and customizing every step on your local hardware domain?
These are the contrasting routes of hosted and local large language models, each beckoning with unique strengths and considerations. Let's peel back the layers of this LLM dichotomy and explore the key differences that shape their landscapes.
Think of access like the entry barrier. Hosted large language models act like welcoming hosts, offering APIs and user interfaces like OpenAI or Google AI. Just plug in and play, no hefty setups or technical acrobatics required.
Local large language models, however, demand a steeper climb. Building your own large language model kingdom requires technical expertise, powerful hardware, and navigating complex deployment processes. It's an empowering journey for the tech-savvy, but not for the faint of heart.
With control comes responsibility, and hosted and local large language models offer contrasting amounts of both. Hosted platforms are benevolent landlords, letting you use their models under predefined rules. Customization might be limited, but you don't sweat over infrastructure or security updates.
Local large language models, however, hand you the keys and wrench. You control everything from fine-tuning parameters to managing security, but this freedom comes with the burden of upkeep and performance responsibility.
This, everyone understands. Hosted large language models operate on a pay-as-you-go model, charging per token or API call. Great for small-scale use, but the price tag can climb with increasing workload.
Local large language models demand an upfront investment in hardware and software licenses. While initially higher, it can be more economical for high-volume usage or sensitive data that needs to stay on-premises, like a bank's customer data. Pricing for cloud-hosted servers designed for machine learning may also be less expensive when comparing cost per run time hour, local LLM, to token processing costs, hosted LLM, when processing larger amounts of data.
Think of resources as the fuel that powers the large language model engine. Hosted LLMs reside in the cloud, leveraging vast remote server resources. No need for high-end local hardware, but you depend on internet connectivity and potential latency issues.
Local large language models demand dedicated servers or powerful workstations, as running an LLM on your PC might not cut it. Public cloud providers, such as Azure and AWS, are continuing to offer more advanced server options with specialized GPU sets ideal for machine learning and hosting large language models. But prices are at the higher tiers of most cloud subscription offerings.
But remember, the paths are not as rigid as they seem. Lines between hosted and local are blurring. Some cloud platforms like Microsoft Azure now offer customization options and even on-premises deployment for specific needs. Hybrid models are emerging, combining the convenience of hosted pre-trained models with the fine-tuning flexibility of local deployments. This evolving landscape promises even more tailored solutions in the future.
Choosing between hosted and local is like picking your large language model steed. Understanding the unique strengths and drawbacks of each approach, within the context of your specific needs and resources, empowers you to chart your own successful path on the ever-evolving large language model landscape.
The battlefield of large language models is no longer a binary clash, but a nuanced dance of strengths and weaknesses, waiting to be paired with the right applications. Let's explore the ideal scenarios where hosted and local large language models shine brightest, tailoring their unique capabilities to specific use cases and industries. Imagine needing large language model power for smaller projects, quick experiments, or simple tasks like text summarization or sentiment analysis. In these scenarios, hosted LLMs take center stage.
Rapid prototyping. Access a diverse arsenal of pre-trained models, experiment with different approaches, and iterate quickly without hefty setup costs or technical hurdles. Ideal for startups, researchers, or individuals exploring large language models' potential.
Content creation and marketing. Generate engaging product descriptions, craft personalized marketing campaigns, or translate content on the fly. Hosted large language models offer instant access to language manipulation tools for diverse marketing needs.
Customer service and support. Implement chatbots powered by hosted large language models to handle basic inquiries, automate repetitive tasks, and offer 24/7 support, freeing up human agents for complex issues.
Education and training. Personalize learning experiences, generate practice problems, or provide intelligent feedback with hosted large language models, enhancing the learning process for students and instructors alike.
But when your needs demand tailor-made solutions, exquisite control, and the highest security, local large language models step into the spotlight with high-sensitivity data. For tasks involving confidential information like financial data or medical records, local deployment ensures complete data, privacy, and control, mitigating the risks of cloud storage.
Domain-specific applications. Train your LLM on specialized datasets to create models that excel in niche tasks like legal document analysis, medical diagnosis support, or scientific paper summarization.
Large-scale processing. When you need to handle massive volumes of data or real-time processing demands, local large language models, backed by dedicated hardware, can deliver the necessary performance and scalability.
Research and development. Experiment with cutting-edge large language model architectures, design and train novel models for specific research goals, and push the boundaries of language processing without relying on external platforms.
Remember, the hosted versus local large language model divide isn't an impenetrable wall. Many scenarios benefit from a hybrid approach, such as leveraging hosted large language models for pre-processing to utilize hosted models for initial data cleaning, filtering, or analysis, before feeding the refined data to your local model for specific tasks.
Fine-tuning hosted models locally. Start with a pre-trained hosted model and further tailor it using your own data and resources on your local large language model system for a customized solution.
Collaboratively sharing models. Develop and train models locally, but deploy them as APIs on hosted platforms, granting wider access and enabling collaboration with others.
By understanding the strengths and weaknesses of each large language model approach and recognizing the potential for synergies, you can navigate the vast landscape of language models with confidence.
Choose the tools that fit your specific needs, experiment with different strategies, and unleash the transformative power of large language models on your unique endeavors. The battle lines are drawn. Hosted and local large language models stand head-to-head, each wielding a unique toolkit of strengths and weaknesses across key factors like flexibility, security, and yes, technical expertise. But this isn't a binary clash. It's a nuanced waltz, where finding the ideal large language model partner for your journey depends on your specific needs and resources. Let's dissect their advantages and disadvantages, mapped to the 4 large language model types, to help you discern the perfect linguistic companion for your quest.
Like choosing from a diverse toolbox, you readily access pre-trained models for various tasks in both local pre-trained and hosted pre-trained categories. Experimentation and adaptation are swift, allowing you to swap models with ease. Think customizing different tools for different jobs.
Unmatched personalization awaits in local untrained territory. Fine-tune parameters, inject your data, and craft bespoke models perfectly tailored to your niche needs. No task is too specific, no domain too obscure. It's like building your own dream-specific tool from scratch.
While less common, some platforms offer access to untrained models like Jurassic 1 Jumbo for advanced users who want more control over the training process. This requires significant expertise, akin to building a custom tool and then meticulously training it to perform a specific task.
Data privacy can be a delicate consideration with hosted models. Your data dances on remote servers under platform protocols, requiring trust in their security measures and data handling practices. Think entrusting your precious tools to a secure storage facility.
In your own LLM fortress, security reigns supreme. Data never leaves your premises, empowering you to define your own protocols and maintain absolute transparency. You hold the keys to your linguistic kingdom and all its treasures.
Cloud infrastructure fuels hosted models, often offering blazing fast response times and impressive scalability for demanding tasks. You reap the benefits of optimized hardware and distributed architecture. Think having access to a high-powered workshop with readily available resources.
Performance for local models hinges on your own hardware's limitations. Complex tasks might encounter slower processing if your machine struggles to keep up with the model's demands. Don't underestimate the computational beast you might need to tame. Think about the difference between working with a well-equipped professional workshop and a basic garage setup. You also have the option of hosting your local LLM on specialized machine learning servers with advanced GPU sets offered by many cloud providers, such as Azure and AWS.
Minimal technical knowledge is your passport to the hosted pre-trained large language model world. APIs and interfaces become your playground, letting you focus on applications without wrestling with the underlying infrastructure. Think about learning basic tool operation without needing to understand how they're actually made.
While easier than local untrained, some technical savvy is required for local pre-trained large language models. You'll need to navigate data preparation, fine-tuning parameters, and deployment processes. Think acquiring basic carpentry skills to customize pre-built furniture.
If you are looking to build a local untrained large language model, then buckle up for a technical roller coaster. Deep learning expertise, data cleaning, training algorithms, and hardware optimization become your essential skills. Think about mastering advanced engineering to build and fine-tune your own tools from scratch.
Hosted untrained large language models are reserved for seasoned data scientists. This path demands the most technical prowess. You'll need to manage the entire training process, from setting up the computational environment to optimizing training parameters. Think about being a master craftsman capable of building and perfecting specialized tools for a specific purpose.
Remember, within local pre-trained, the technical demands can vary depending on the platform and desired level of customization. Some platforms offer user-friendly interfaces and automated workflows that can significantly reduce the technical burden.
The user-friendly interfaces of hosted platforms fade away as we venture into the technically exhilarating yet undeniably challenging realm of local large language models. Buckle up, because we're about to explore the fascinating underbelly of setting up, running, and maintaining your own linguistic powerhouse.
Imagine transforming your server room or cloud infrastructure into a bespoke large language model sanctuary. Here's your hardware shopping list for optimal performance.
High-performance CPUs are the initial workhorses of your large language model zoo, crunching numbers and fueling model training. Invest in workstation-grade machines or server setups for smooth operations.
You'll need ample RAM, 32 gig or more. Think of RAM as the temporary workspace for your models. The more you have, the more complex tasks your large language models can handle without stuttering.
Dedicated GPUs. For most advanced models and large datasets, graphics processing units, turbochargers, large language models performance. Many cloud providers are offering high-performance servers that contain advanced GPU sets designed for machine learning.
Training data, fine-tuned models, and intermediate results. They all eat up gigabytes or even terabytes of storage. Invest in reliable and scalable solutions like SSDs or RAID arrays to keep your large language model thriving. Consider other options for data storage as well, such as cloud-hosted databases.
Think of the software stack as the operating system for your large language model zoo. You'll need a software environment equipped with deep learning frameworks. TensorFlow, PyTorch, or MXNet are popular choices, providing the core functionality for training your models.
Data preprocessing libraries. These tools help you clean, format, and prepare your data for model training.
And model management tools to track your model versions, optimize performance, and deploy them in various applications.
Remember, your data is the lifeblood of your large language model. Secure your sanctuary with firewalls to guard the gates against unauthorized access, data encryption to keep your large language model's secrets under lock and key, and user access controls. Grant permission only to those who deserve it.
Running your own large language model isn't a walk in the park. Be prepared to navigate challenges such as technical expertise. You'll need data science prowess, deep learning chops, and a dash of system administration magic to keep your large language model zoo humming.
Resource management, optimizing hardware, monitoring performance, and ensuring efficient training sessions require constant vigilance and adaptation.
Troubleshooting, model hiccups, data glitches, and hardware gremlins. Learn to decipher their cryptic messages and get your large language model back on track.
And keeping up to date. The large language model landscape is a fast-paced race. Stay ahead by continuously learning new techniques and adopting best practices.
Fear not, intrepid large language model wrangler. Resources abound to guide you through the wilderness like Hugging Face. This treasure trove offers pre-trained models, training scripts, and tutorials for various models, giving you a head start on your local deployment.
Cloud TPU access. Services like Google Cloud TPU or Amazon Bracket lend you the processing power of powerful cloud-based tensor processing units, letting you train your models without breaking the bank on hardware.
Community forums and documentation. Dive into online communities and forums dedicated to large language models. Ask questions, exchange tips, and learn from the wisdom of fellow enthusiasts.
And online courses and tutorials. Numerous online resources walk you through the technical aspects of large language models, covering everything from model training to infrastructure setup.
Remember, the rewards of running local large language models are immense. Tailored models, complete control, and the satisfaction of crafting your own linguistic masterpiece. Embrace the challenges, leverage the resources, and enjoy the journey of cultivating your own large language model zoo.
We've unraveled the secrets of hosted and local large language models, navigated their pros and cons, and emerged from the technical labyrinth. Now let's crack open the crystal ball and glimpse the shimmering future of large language model deployment, where exciting trends will reshape the landscape and redefine how we interact with language.
Trend 1. Democratization and specialization. Imagine large language models no longer locked away in tech fortresses, but democratized and accessible to all. Open-source tools, cloud-powered hardware, and intuitive interfaces will lower the barrier to entry, letting individuals and smaller players experiment with models tailored to their needs. Look for a surge in specialized models crafted for niche domains like healthcare, finance, or legal documents, where precision and performance reign supreme. Both hosted and local LLMs will thrive. Hosted platforms will witness an influx of new users, while local deployments become more feasible for specialized applications with readily available tools and resources.
Trend 2. Hybrid deployment and synergy. The rigid lines between hosted and local will fade into a vibrant tapestry of hybrid approaches. Local training paired with hosted deployment, and vice versa, will become commonplace. This lets users reap the best of both worlds: local control and flexibility, combined with hosted scalability and ease of use. This trend fosters collaboration and creates a dynamic ecosystem where developers and users share resources and expertise, accelerating large language model advancements.
Trend 3. Explainability and trust. As LLMs become more powerful, the demand for transparency and explainability will soar. Users need to understand how these linguistic powerhouses reach their conclusions, especially in high-stakes scenarios. Expect advancements in XAI, explainable AI techniques that shed light on large language model inner workings, building trust and ensuring responsible deployment. Both hosted and local platforms will need robust XAI tools to stay competitive and address user concerns.
Trend 4. Beyond text, multimodal fusion. Large language models won't be confined to textual shackles. They'll unleash their power to grasp images and videos. This opens doors to remarkable applications like generating videos from text descriptions, crafting personalized recommendations based on images, or analyzing social media trends through multimodal analysis. Both hosted and local large language models will need to adapt to include multimodal data processing capabilities, paving the way for innovative applications across diverse fields.
Remember, the future of large language model deployment is a kaleidoscope of possibilities. By embracing these trends, fostering collaboration, and prioritizing ethical considerations, we can ensure large language models become powerful tools for good, democratizing access to knowledge, driving innovation, and bridging the gap between language and understanding, creativity, and progress.
This concludes Section 2 of the course, Hosted Large Language Models versus Local Large Language Models. This is Section 3, Data Security and Data Privacy Considerations for Embedding Data and Vector Databases.
Ever feel like data is trapped in silos, isolated islands within the vast information ocean? That's where embedding and vector databases come in, bridging the gap between raw data and machine-readable understanding.
Imagine transforming each data point, such as text, image, and music, into a mathematical representation called a vector. Think of it as a high-dimensional GPS coordinate, pinpointing your data in a vast semantic space.
These vectors aren't just strings or integers, they're arrays of numerical values capturing various features and attributes of the data. For example, a text embedding might have values representing word frequencies, grammatical structures, and even semantic topics.
Enter the vector database. Unlike traditional databases that store structured data in rows and columns, vector databases specialize in handling this new breed of data, vectors. They efficiently organize and retrieve information based on these high-dimensional representations, opening up a world of possibilities.
Let's look at what makes vector databases special. Semantic search. Forget keyword-based queries. Imagine asking, "Find songs similar to Bohemian Rhapsody," and getting music with matching emotional depth, not just identical lyrics. Vector databases enable such semantically aware searches, unlocking deeper insights and connections within your data.
Machine learning playground. Embeddings provide a common language for diverse data types, making them ideal for training and deploying machine learning models. Vector databases fuel tasks like personalized recommendations, anomaly detection, and even text generation, all thanks to efficient storage and retrieval of embedded data.
Unveiling hidden relationships. The beauty of vectors lies in their ability to reveal hidden patterns and correlations. Clustering similar data points in the high-dimensional space allows you to discover previously unknown connections, enabling data-driven decisions and innovative applications.
While vector databases handle vector data, they're more than just regular databases wearing fancy glasses. Their internal architecture and optimization techniques are specifically designed for efficient similarity search. Searching for nearest neighbors in high-dimensional spaces requires dedicated algorithms and data structures. Vector databases employ techniques like k-nearest neighbors, KNN, indexing and metric space search to find similar data points in record time.
Scalability and performance. As your data grows, so does the complexity of managing vectors. Vector databases offer specialized indexing and partitioning strategies to ensure efficient retrieval and computation, even with massive datasets.
Think of a vector database as a high-performance translator for your data, transforming it into a language machines understand and facilitating lightning-fast searches, powerful machine learning, and the discovery of hidden relationships within your information universe.
Chunking is the process of dividing large pieces of data, such as text documents or database tables, into smaller, manageable segments. These segments are called chunks. Embedding models typically have input size limitations. Chunking allows you to break down large data points into smaller pieces that fit within these limitations, enabling the model to process and embed them effectively. Chunking also helps capture context within the data by preserving the flow and relationships between smaller sections. This can lead to more accurate and meaningful embeddings.
There are different approaches to chunking, depending on the type of data and your specific needs. Some common methods include fixed-size chunking. Divide the data into equally sized chunks, regardless of the content.
Sentence-based chunking. For text data, split the documents into individual sentences or paragraphs.
N-gram chunking. Extract overlapping sequences of N words to capture local context.
Adaptive chunking. Employ algorithms to dynamically determine chunk sizes based on the data content and complexity.
Benefits of chunking include improved accuracy. By processing smaller chunks that fit within the model's capabilities, you can achieve more accurate and stable embeddings.
Enhanced efficiency. Chunking reduces the computational burden on the embedding model, leading to faster processing times for large datasets.
And reduced memory usage. Breaking down data into smaller segments minimizes memory requirements, making it feasible to process larger datasets on limited resources.
Choosing the appropriate chunking strategy depends on your data type, model capabilities, and desired outcomes. Overly small chunks can lead to loss of context and reduced embedding accuracy, while excessively large chunks might exceed model limitations. Overlapping chunks can be beneficial for preserving context, but they increase processing overhead.
While embedding vectors unleash a realm of possibilities for security applications, they also harbor a hidden vulnerability, the potential for embedding inversion attacks. Let's dive into this fascinating and often overlooked security risk.
Imagine a security system safeguarding sensitive information by replacing names and addresses with seemingly anonymous numerical vectors. Yet, a skilled attacker, equipped with knowledge of embedding techniques, might be able to reverse engineer those vectors, unveiling sensitive details. This is the essence of embedding inversion attacks.
Let's take a look at how embedding inversion attacks work. Crafting a probe vector. The attacker meticulously constructs a vector that closely resembles the target data they seek to expose. This probe vector acts as a guide in the inversion process.
Probing the embedding space. They strategically query the system, observing how it responds to the probe vector and its neighbors in the embedding space.
Decoding relationships. By analyzing these responses, the attacker can uncover hidden relationships between vectors, gradually mapping out the embedding space's structure.
Reconstructing sensitive information. With enough probes and analysis, they can start inferring the original data from its embedded representation, potentially revealing sensitive details like names, addresses, or even personal preferences that were assumed to be concealed.
Let's look at some factors that amplify risk. Data size and diversity. Larger and more diverse datasets create more complex embedding spaces, potentially making inversion easier.
Embedding models' complexity. More intricate embedding models can inadvertently encode more sensitive information, increasing vulnerability.
And attackers' knowledge and resources. Skilled attackers with access to large-scale computing resources can launch more sophisticated inversion attempts.
Now let's look at some mitigation strategies. Differential privacy. Introducing controlled noise into embedding vectors can obscure sensitive information while preserving overall utility.
Adversarial training. Exposing embedding models to adversarial examples during training can make them more resilient to inversion attempts.
Secure embedding techniques. Research into privacy-preserving embedding methods such as homomorphic encryption offers promising avenues for protection.
And access control and monitoring. Implement robust access control measures and monitor system usage to detect potential inversion probes.
We've unveiled the lurking shadows of embedding inversion attacks, but fear not, intrepid data defenders. An arsenal of encryption strategies stands ready to guard the vaults of your embedded data and vector databases. Let's explore these shields and swords of security.
Imagine cloaking your data in an invisibility cloak before feeding it to the embedding model. This is the essence of application layer encryption. By encrypting data before embedding, we sever the direct link between the original data and its vector representation, obfuscating sensitive information for attackers.
Let's look at some techniques. Homomorphic encryption. This allows performing calculations directly on encrypted data, enabling analysis without decryption, minimizing exposure.
Secure multi-party computation. This lets multiple parties collaboratively analyze data without revealing their individual contributions, ideal for collaborative security investigations.
Differential privacy adds controlled noise to data, preserving overall insights while obscuring individual details, offering a privacy utility trade-off.
Let's look at some secure storage solutions. Even encrypted data deserves a secure haven. Here's where robust storage solutions step in. Hardware security modules. These tamper-resistant physical devices offer an isolated environment for storing encryption keys, ensuring their ultimate protection.
Secure enclaves. Specialized compartments within processors provide another layer of encryption and secure execution, shielding data even from privileged software.
Distributed ledger technology. Blockchain-based solutions can provide transparent and tamper-proof storage for encryption keys and audit logs, enhancing trust and accountability.
The optimal encryption strategy depends on your specific needs and threat landscape. Consider factors like security level. How sensitive is the embedded data? High-risk information demands stronger encryption techniques.
Performance impact. Encryption adds computational overhead. Balance security with processing efficiency.
And compliance requirements. Regulations like GDPR might dictate specific encryption standards.
Remember, encryption is a powerful tool, but not a silver bullet. Combining it with access control, intrusion detection, and rigorous security practices builds a multi-layered defense against unauthorized access and malicious intent. By wielding these encryption strategies, you can transform your vector databases into secure fortresses, safeguarding sensitive information and upholding privacy in the realm of embedded data.
Access control and permissions. Establishing who can access and use embedded data, ensuring appropriate security levels, and preventing unauthorized access. While encryption serves as a sturdy vault for our embedded data, we still need vigilant guards at the gates to control who enters and what they can do. Access control and permissions form the cornerstone of securing embedded data in vector databases, ensuring only authorized parties access and utilize this sensitive information. Let's delve into this crucial security practice.
Imagine creating a hierarchy of access privileges, like granting developers access to analyze training data while restricting marketing teams to viewing aggregated consumer trends. This is the essence of defining roles and responsibilities within your access control system. Each role carries a specific set of permissions, determining what data users can access, what actions they can perform, and under what conditions.
Beyond simple read or write access, granular permissions offer fine-grained control. Imagine allowing an analyst to see only specific data columns or restricting a researcher to certain query types. This granular approach minimizes exposure and prevents users from accessing more information than necessary for their assigned tasks.
Think of a secure checkpoint where users prove their identity and demonstrate authorized access before entering the data vault. Secure authentication protocols like multi-factor authentication and strong password policies act as the first line of defense. Once authenticated, authorization mechanisms like role-based access control or attribute-based access control verify users' specific permissions for the requested data.
Even the most vigilant guards need occasional inspections. Regularly auditing access logs and monitoring user activity within the database is crucial for detecting suspicious behavior and potential breaches. Logging who accessed what data, at what time, and for what purpose allows for prompt investigation and accountability.
For seamless security, integrating access control mechanisms for embedded data with existing IT infrastructure is vital. Imagine syncing user roles and permissions between the vector database and your identity management system, reducing administrative overhead and streamlining access control processes.
Implementing robust access control for embedded data isn't without its hurdles. Consider these challenges. Data complexity. Granular access control can become convoluted with diverse data types and complex relationships within the embedding space.
Dynamic needs. Permissions might need to adapt to evolving research projects or changing user roles, requiring flexibility and scalability.
And privacy concerns. Balancing access control with individual privacy requires careful consideration and adherence to relevant regulations.
Remember, building a robust access control system for embedded data demands careful planning, ongoing maintenance, and constant vigilance.
By embracing these challenges and implementing best practices, you can transform your vector databases into secure havens, ensuring authorized access and safeguarding sensitive information from unauthorized hands.
Imagine a tightrope stretched between two towering masts. On one side, the vast potential of embedded data for security analysis. On the other, the fundamental right to individual privacy. This is the delicate dance we face when utilizing embedded data, and striking the right balance is crucial.
Embedded data analysis unlocks a treasure trove of insights for security applications. Analyzing user behavior patterns can identify anomalies indicative of cyber attacks, while understanding network traffic flows can expose malicious activity. The utility of embedded data extends beyond immediate threats, informing proactive security strategies and driving safer digital experiences.
However, exploiting this utility cannot come at the expense of individual privacy. Personal information embedded within vectors holds the potential for identification, discrimination, and misuse. Concerns regarding data surveillance, profiling, and potential violations of regulations like GDPR and CCPA cannot be ignored.
The key lies in navigating this tightrope with meticulous balance. Here are some approaches to consider. Differential privacy. Injecting controlled noise into data during embedding obscures individual details while preserving aggregate insights, enabling analysis without compromising privacy.
Federated learning. Decentralized data analysis keeps sensitive information on local devices, minimizing the need for central data storage and reducing privacy risks.
Synthetic data generation. Creating artificial data that retains statistical properties of the original data allows for analysis without exposing any real-world individuals.
And transparency and explainability. Openly communicating how embedded data is collected, used, and protected builds trust and allows individuals to make informed decisions about their data.
Instead of viewing utility and privacy as opposing forces, consider them as interdependent partners. By prioritizing privacy throughout the data lifecycle, from collection to analysis to storage, we can build trust and unlock the full potential of embedded data for security while upholding individual rights.
Remember, striking the right balance requires ongoing dialogue and collaboration among researchers, technologists, policymakers, and individuals. By sharing concerns, exploring innovative solutions, and prioritizing ethical data practices, we can chart a course towards a future where security and privacy coexist, not compete.
The world of data privacy regulations can resemble a complex labyrinth, and with embedded data, the twists and turns become even more intricate. Understanding how regulations like GDPR and CCPA apply to the collection, storage, and use of embedded data is crucial for navigating this terrain and ensuring legal compliance.
The General Data Protection Regulation casts a broad shadow over the data landscape, and its reach extends to embedded data as well. Consider data embedded in vectors as personal data, if it can be linked to an identifiable individual, triggering GDPR's requirements. These include transparency and informed consent. Individuals must be clearly informed about how their data is being embedded and used, and their consent must be freely given for such processing.
Data minimization and purpose limitation. Only the minimum amount of data necessary for the specific purpose of embedding should be collected, and its use must be limited to that specific purpose.
Right to access, rectification, and erasure. Individuals have the right to access their embedded data, request its correction, and under certain circumstances, demand its deletion.
Data security and breach notification. Robust security measures must be implemented to protect embedded data, and any data breaches must be promptly reported to relevant authorities and affected individuals.
The California Consumer Privacy Act adds another layer of complexity for businesses operating in the Golden State. While it overlaps with GDPR in some areas, CCPA also introduces unique elements relevant to embedded data.
Right to know and right to delete. Californians have the right to know what data about them is being collected, used, and sold, and they can request its deletion from an organization's systems.
Do not sell my personal information. Consumers have the right to opt out of the sale of their personal information, which could include some types of embedded data, depending on its nature and usage.
And shine the light requests. Individuals can request specific details about what personal information is being collected, used, and disclosed by a business, including information derived from embedded data analysis.
Complying with these regulations demands a proactive approach. Conduct data mapping exercises to identify all data sources that contribute to embedded vectors, and ensure compliance with relevant regulations at each stage.
Implement robust data governance practices. Establish clear policies and procedures for data collection, storage, and use, with specific considerations for embedded data analysis.
Prioritize transparency and consent. Inform individuals about how their data is being embedded and used, and obtain their informed consent before proceeding.
And stay updated on regulatory changes. The data privacy landscape is constantly evolving, so staying abreast of new regulations and amendments is crucial.
Remember, compliance with data privacy regulations is not just a legal requirement, but also a fundamental ethical responsibility. By prioritizing individual privacy and upholding transparency, we can build trust and unlock the full potential of embedded data for security applications while respecting the rights of individuals within the ever-shifting labyrinth of data regulations.
In the realm of embedded data, where invisible vectors dance with hidden insights, transparency and explainability emerge as guiding lights. They illuminate the path for users to understand how their data is being used and empower them to navigate the outcomes of automated analysis.
Imagine analyzing network traffic patterns embedded in vectors to detect cyber attacks. Without transparency, users remain in the dark. They know an anomaly was detected, but the basis for that decision remains shrouded in obscurity. This lack of clarity breeds distrust, hinders accountability, and undermines the potential of embedded data analysis.
Transparency involves shedding light on the entire data journey, from collection to embedding to analysis. This includes data sources, clearly identifying the origin and nature of data contributing to the embedded representations.
Embedding techniques, explaining the specific algorithms and processes used to transform raw data into vectors.
Model training, providing insights into the training data and training process used to develop the analysis models.
Decision-making logic, demystifying the rules, patterns, or statistical relationships used by models to arrive at conclusions.
Think of explainable AI as a torch illuminating the black box of model outcomes. XAI techniques like feature importance analysis or attention mechanisms shed light on which aspects of the embedded data had the most significant impact on the model's decision.
This allows users to verify model fairness, ensure that decisions are not biased based on sensitive attributes like race or gender.
Identify potential errors. Gain insights into potential flaws in the model or data pipeline that might lead to incorrect conclusions.
Build trust and acceptance. When users understand the reasoning behind model outputs, they are more likely to trust and accept the recommendations or predictions.
Implementing robust transparency and explainability measures for embedded data presents its own set of challenges, such as balancing detail and clarity. Explanations should be informative without overwhelming users with technical jargon.
Computational cost. Explainable techniques can add processing overhead to already resource-intensive analysis models.
Privacy concerns. Striking a balance between transparency and protecting user privacy from unwanted data disclosure requires careful consideration.
Despite these challenges, the benefits of transparency and explainability far outweigh the hurdles. By embracing these principles and developing innovative solutions, we can ensure that embedded data analysis not only informs security decisions, but also empowers users with understanding and trust.
Stepping out of the theoretical, let's explore the vibrant world where embedded data dances with security applications. Buckle up for a journey through real-world case studies and a glimpse into the exciting future of this technology.
Case Study 1: Anomaly Detection in Network Traffic. Imagine a bustling highway of digital data where network traffic flows like millions of vehicles. Embedded data analysis acts as a vigilant traffic cop, analyzing hidden patterns within vector representations of network flows.
By identifying deviations from established norms, security teams can detect malicious activity. Unusual spikes in specific data types or connections to known blacklisted IP addresses can flag potential cyber attacks.
Prevent data breaches. Anomalous data transfers originating from sensitive endpoints can trigger immediate investigations and mitigation efforts.
And optimize network performance. Insights into traffic patterns can inform network segmentation and resource allocation, ensuring smooth and efficient data flow.
Case Study 2: Fraud Detection in Financial Transactions. Picture a labyrinthine financial system where every transaction leaves a digital footprint. Embedded data analysis weaves its magic through these footprints, analyzing vectors representing transaction characteristics.
This allows financial institutions to identify fraudulent activity. Uncharacteristic spending patterns, sudden changes in beneficiary accounts, or transactions originating from high-risk locations can indicate potential fraud.
Prevent financial losses. Early detection of suspicious transactions can minimize financial damage and prevent victims from falling prey to sophisticated scams.
And personalize fraud prevention measures. Analyzing individual spending patterns can create custom risk profiles for each customer, allowing for targeted and effective fraud prevention strategies.
Now let's take a look at a glimpse into the horizon at future applications such as cybersecurity threat prediction. Analyzing vast datasets of past attacks and leveraging embedded data analysis could enable proactive threat prediction, identifying vulnerabilities before they are exploited.
Social media risk assessment. Analyzing online behavior patterns embedded in social media data could offer insights into potential radicalization or criminal activity, assisting law enforcement and security agencies.
And personalized security solutions. Tailoring security recommendations and protections based on individual risk profiles derived from embedded data analysis could offer a more holistic and effective approach to personal security. While the advantages of embedded data in security are undeniable, we must remember to navigate the labyrinth with caution.
Privacy concerns. Balancing the power of data analysis with individual privacy necessitates robust data anonymization techniques and transparent data governance practices. Algorithmic bias. Embedded data analysis models trained on biased data can perpetuate discriminatory outcomes. Careful data selection and bias mitigation techniques are crucial.
And misuse and weaponization. The power of embedded data analysis, if misused, could lead to mass surveillance and potential abuse of individual rights. Ethical considerations and strong regulatory frameworks are paramount.
Remember, embedded data is a powerful tool for security, but like any tool, it demands responsible use. By prioritizing privacy, mitigating bias, and ensuring ethical frameworks, we can unlock the full potential of this technology for a safer and more secure future.
This concludes Section 3 of the course, Data Security and Data Privacy Considerations for Embedding Data and Vector Databases. Section 4. Integrating Large Language Model APIs. Think of large language models as powerful language processing tools, much like versatile Swiss Army knives for your data. They can be used in various ways, depending on your needs and creativity. Here are some common ways to integrate large language models.
Number 1. Simple prompt-based interactions. This is the classic large language model experience. You provide a prompt, a simple query or instruction, and the model generates text, translates languages, or completes tasks like code generation. Think of it as asking your model a question or giving it a command.
Number 2. Large language model chains and pipelines. Level up your workflow. Chain multiple large language models together, each specializing in a particular task. Imagine feeding the output of one model, such as summarization, as the input for another like question and answering. This allows for complex multi-step processing and unlocks advanced applications.
Number 3. Embed and analyze. Transform your data into large language models language. Embed documents, images, or even code into high-dimensional vector spaces using specialized techniques. This allows models to understand and analyze your data in meaningful ways, enabling tasks like content search, image classification, or sentiment analysis.
Number 4. Application-centric integration. Large language models become part of your application's DNA. Build applications that interact with models seamlessly, sometimes referred to as wrappers or RAD. Users upload data or documents, which are embedded and analyzed by the large language model via APIs. The results are then presented within the application, enriching user experience and providing valuable insights.
And number 5, creative collaborations. The possibilities are endless. Don't be limited by conventional approaches. Experiment with integrating large language models into artistic projects, educational tools, or even interactive games. Your imagination is the only limit.
Imagine large language models as vast repositories of linguistic knowledge, guarded by a series of portals, their APIs. To unlock their power and unleash their abilities in your applications, understanding these access points is crucial.
Let's delve into the technical considerations of integrating large language model APIs, exploring the different ways to knock, the protocols for entry, and the potential challenges you might encounter on your journey.
Large language model APIs present various entry points, each with its strengths and quirks such as RESTful APIs. These familiar web service interfaces offer predictable HTTP interactions for sending data and receiving responses. Ideal for quick integrations and familiar workflows. They might lack advanced features of other methods.
Software development kits. These pre-built libraries offer platform-specific code and tools, simplifying communication with the large language model API and providing additional functionalities. Choose the SDK tailored to your development environment for easier integration.
Client libraries are similar to SDKs. These standalone libraries offer code for specific programming languages, allowing direct interaction with the large language model API without platform dependencies. Choose the library that fits your language of choice for language-specific convenience.
Like passports for information, data formats guide your requests and responses through the large language model API. Common formats include JSON. This ubiquitous format, with its human-readable key-value pairs, simplifies sending and receiving structured data, making it a popular choice for LLM API communication.
XML. Though less common in large language model APIs, XML's hierarchical structure can be useful for complex data with nested elements.
Custom formats. Some platforms might use proprietary formats to handle specific data types or functionalities. Be prepared to adapt your application to cater to the platform's preferred format.
Protecting your data and access is paramount. Large language model APIs employ various authentication protocols to ensure only authorized users enter. API keys are unique strings that act as digital keys, identifying your application and granting access to the LLM's services. Keep them secure and hidden.
OAuth. This authorization protocol allows secure third-party logins, leveraging existing accounts like Google or Twitter for API access.
And custom authentication. Some platforms might have their own authentication systems. Follow the platform's guidelines to ensure secure access.
No access journey is without its bumps. Be prepared for these potential challenges, such as latency and performance. The speed of your interaction depends on factors like internet connectivity, server load, and API design. Optimize your application and choose platforms with reliable performance.
Errors and debugging. Things can go wrong. Familiarity with the platform's documentation and error codes will help you troubleshoot and get back on track.
And rate limits and costs. Some platforms limit API calls or charge based on usage. Monitor your application's activity and choose a plan that fits your needs.
Remember, integrating large language model APIs is a collaborative dance between your application and the platform. Understanding the technical considerations, choosing the right tools, and embracing the challenges will empower you to unlock the full potential of models and transform them into powerful tools for your projects.
Imagine a superhero league, but instead of capes and superpowers, they wield words and linguistic prowess. That's the essence of popular LLM APIs, platforms granting access to the incredible abilities of large language models, ready to empower your applications with next-level language processing. Let's embark on a guided tour of this A-team, highlighting their specialties, strengths, and the tasks they can help you conquer. The visionary, OpenAI API. Strengths: wide range of pre-trained models, strong performance in text generation, translation and summarization, active community, and extensive documentation.
Use cases: generating product descriptions, crafting personalized marketing messages, translating content on the fly, and summarizing research papers.
Think of it as your linguistic Swiss Army knife, versatile for tackling diverse language tasks.
The Brainiac Google AI platform. Strengths: scalability for handling massive datasets, integration with other Google Cloud services, access to cutting-edge models, and enterprise-grade security.
Use cases: large-scale data analysis, real-time chatbots, personalized learning experiences, and custom model training for niche tasks.
Think of it as your AI power plant, ideal for heavy-duty language processing and large-scale deployments.
Let's look at the Alchemist, Hugging Face API. Strengths: open-source focus, diverse model selection, community-driven development, and user-friendly interface.
Use cases: experimenting with different LLM architectures, fine-tuning pre-trained models for specific tasks, and building custom applications with readily available tools.
Think of it as your LLM playground, perfect for research, exploration, and building bespoke language solutions.
The Guardian Amazon Comprehend. Strengths: integration with AWS services, focus on natural language understanding tasks like sentiment analysis and topic modeling, robust security features.
Use cases: analyzing customer reviews, extracting insights from social media data, classifying documents, and identifying entities in text.
Think of it as your linguistic detective, unearthing hidden meaning and insights from your data.
And the Diplomat, Microsoft Azure Cognitive Services. Strengths: variety of language processing tools beyond large language models, integration with Azure services, global reach with multiple data centers.
Use cases: text translation, speech recognition, sentiment analysis, chatbot development, and building multilingual applications.
Think of it as your global language ambassador, seamlessly bridging communication gaps across languages and regions.
This is just a glimpse into the diverse talents of the large language model API landscape. Remember, the perfect API depends on your specific needs and goals. Consider factors like required functionalities. What tasks do you need the LLM to perform?
Performance and scalability. Do you need real-time responses or handle large volumes of data?
Budget and pricing. Are there pay-as-you-go models or fixed costs?
And ease of use and support. Do you need a user-friendly interface and readily available documentation?
By understanding the strengths and weaknesses of each API and aligning them with your project requirements, you can assemble the perfect team of linguistic superpowered allies, ready to help you achieve your goals.
The magic of large language models transcends theoretical discussions. Let's witness their transformative potential unfold in real-world applications, where their linguistic superpowers are harnessed through accessible APIs, empowering diverse fields with remarkable results.
Imagine chatbots that not only answer basic questions, but understand natural language and offer personalized support. Large language models integrated into customer service platforms achieve just that.
Resolving issues with finesse. By analyzing customer inquiries, LLMs power chatbots that engage in meaningful conversations, diagnose problems, and suggest solutions, streamlining support workflows.
Enhancing the customer experience. LLMs personalize interactions, providing relevant recommendations and offering tailored assistance, fostering customer loyalty and satisfaction.
Automating repetitive tasks. LLMs handle routine inquiries like order tracking or product information, freeing human agents for complex issues and building stronger customer relationships.
Struggling to overcome writer's block? Large language models become your creative collaborator, injecting a dose of linguistic magic into content creation.
Generating engaging content. From product descriptions to social media posts, large language models craft compelling copy, drawing users in with their natural language flow and insightful suggestions.
Translating content seamlessly. Break down language barriers. Large language models translate with nuance and accuracy, ensuring your content reaches global audiences effectively.
And summarizing information efficiently. Get the gist of long documents in a flash. LLMs condense complex information into concise summaries, saving you time and effort.
Uncover hidden patterns and extract valuable insights from your data with the help of LLM-powered analysis tools.
Understanding customer sentiment. Analyze social media mentions or survey responses. Large language models identify sentiment, gauge opinions, and help you understand your audience better.
Classifying and categorizing data. Automate document classification or product tagging. LLMs process information with precision, organizing your data efficiently for further analysis.
Generating textual reports. Turn data into actionable insights. LLMs summarize findings, generate reports, and even answer your questions about the data in natural language.
Large language models aren't just for business. They're transforming the learning and research landscape with personalized learning experiences. Large language models adapt to individual learning styles, recommend resources, and create personalized study plans, fostering deeper understanding and engagement.
Research Assistance Powerhouse. Generate research questions, analyze literature, and even draft scientific papers. Large language models become efficient research assistants, accelerating the pace of knowledge creation.
And opening access to education. Translate educational materials or generate transcripts for lectures, making knowledge accessible to diverse audiences globally.
These are just a few examples of the vast potential unleashed when LLMs are integrated into real-world applications through APIs. As their capabilities evolve and APIs become even more accessible, we can expect even more groundbreaking applications across diverse industries.
Remember, the possibilities are endless. With a little imagination and the right LLM API at your side, you can transform language into a powerful tool for innovation, understanding, and progress in your own endeavors.
The stage is set, the APIs are open, and now it's your turn to orchestrate the linguistic symphony, building applications that harness the power of large language models and deliver exceptional results. But before you dive into coding head first, let's explore some best practices to ensure your LLM-powered application hits all the right notes.
Let's look at defining your large language model melody. Know your objective. What problem are you trying to solve? What specific tasks do you need the model to perform? Clearly define your application's goals to choose the right API and design your workflow effectively.
Understand the large language model's strengths. Don't ask a jazz singer to perform opera. Familiarize yourself with the API's specific capabilities and limitations. Choose an API that excels in the tasks you need to accomplish.
Plan your data symphony. Data is the fuel for large language models. Ensure you have access to high-quality, relevant data in the format expected by the API. Clean and pre-process your data for optimal results.
Compose efficient workflows by streamlining communications. Design your application to interact with the large language model API efficiently. Minimize back-and-forth requests and optimize data exchanges for streamlined performance.
Error handling as harmony. Expect the unexpected. Implement robust error handling mechanisms to deal with potential API errors or unexpected responses, ensuring your application gracefully navigates any hiccups.
And monitoring the tempo. Keep an eye on your application's performance. Monitor resource usage, identify potential bottlenecks, and optimize your code for efficient model interaction.
Build for user delight. Simplicity is key. Remember, your application is a bridge between users and the LLM's linguistic magic. Keep the interface clear, intuitive, and focused on user needs.
Feedback for fine-tuning. Provide users with ways to share their feedback on the model's responses. This valuable input can help you fine-tune the API integration and improve your application's results over time.
Transparency and trust. Be upfront about the large language model's role in your application. Build trust by informing users about how their data is used and ensuring responsible integration of these powerful language models.
Prepare for the encore, scalability with style. Your application might become a hit. Be prepared. Design your architecture with scalability in mind, ensuring it can handle increased traffic and data volumes without losing its rhythm.
Security is the conductor. Data security is paramount. Implement robust security measures to protect sensitive user information and data used by the large language model API.
And continuous improvement. The world of large language models is ever evolving. Stay updated on the latest advancements, explore new APIs, and constantly refine your application to keep it at the forefront of linguistic innovation.
Building successful applications with large language model APIs is an art form, a delicate dance between code and language.
By following these best practices, you can ensure your application not only functions flawlessly, but also empowers users to leverage the incredible potential of large language models and create something truly extraordinary.
We've embarked on a thrilling journey, exploring the landscape of hosted and local large language models, delved into the technical considerations of API integration, and crafted best practices for building applications that leverage their linguistic superpowers.
Now, let's peer into the future, speculating on potential trends and advancements that might transform the ever-evolving world of large language model APIs and their impact on how we interact with language in the digital age.
Trend 1. Democratization and personalization. Large language model API access will move beyond tech giants and research labs. Expect simpler tools, open-source APIs, and even individual model subscriptions, empowering everyone to tap into the linguistic magic for personal projects, research, or even creative endeavors.
Personalization will take center stage with adaptive models and user-tailored interfaces customizing model responses to individual needs and preferences.
This democratization will spark a wave of innovation across diverse fields, as individuals and small groups leverage large language models to solve problems, create art, or pursue personalized learning journeys.
Trend 2. Multimodal fusion and embodied AI. Large language models will transcend text, integrating with other input modalities like images, speech, and even physical environments. Imagine an LLM analyzing a painting and describing its hidden meanings, or guiding you through a museum with personalized storytelling based on your interests.
Embodied AI will add another layer, with large language models controlling robots or virtual avatars, interacting with the physical world in real time.
This multimodal fusion will revolutionize human-computer interaction, creating immersive experiences, fostering deeper understanding of complex data, and opening up entirely new avenues for LLM applications.
Trend 3. Explainability and trustworthy AI. As large language models become more powerful, the demand for transparency and explainability will grow. Expect advancements in explainable AI techniques, allowing users to understand how models reach their conclusions and fostering trust in their decision-making processes.
Ethical considerations will be paramount, ensuring responsible development and deployment of large language models that avoid bias and promote fairness in their interactions with the world.
Explainability and trust will pave the way for wider adoption and acceptance of large language models, enabling their safe and beneficial integration into diverse aspects of our lives.
And Trend 4. Collaboration and ecosystems. Individual large language model APIs will evolve into interconnected ecosystems. Imagine platforms where APIs collaborate, sharing knowledge and expertise to achieve complex tasks. Users could seamlessly combine functionalities from different models, building on each other's strengths for even more powerful applications.
Collaborative research and development will accelerate, pushing the boundaries of large language model capabilities and democratizing access to cutting-edge advancements. Collaboration will unlock the full potential of large language models, fostering innovation, accelerating progress, and opening doors to unprecedented applications across various fields.
Remember, the future of large language model APIs is a dynamic canvas, constantly evolving and being shaped by technological advancements, ethical considerations, and user needs. Embrace the unknown, keep learning, and stay curious about the exciting possibilities that lie ahead.
This concludes Section 4 of the course, Integrating Large Language Model APIs. This is Section 5, Data Security and Privacy Considerations for Integrating Large Language Models.
Large language models hold immense potential, but their thirst for data raises critical privacy concerns. We'll delve into the types of data vulnerable to exposure and the potential consequences, exploring real-world incidents to illustrate the risks.
We'll also dissect how bias infiltrates large language models and examine key strategies to mitigate it, ensuring we responsibly harness the power of these language marvels.
Let's look at some of the types of data at risk, such as personally identifiable information, PII. Names, addresses, phone numbers, email addresses, and social security numbers can be unintentionally included in training data, leading to identity theft, fraud, and other personal consequences.
Confidential business information. Trade secrets, customer data, and internal documents could be leaked through large language model outputs, harming business operations and competitiveness.
Private communication. Emails, messages, and other forms of sensitive communication might be present in training data, risking privacy violations and exposing personal or professional relationships.
And biased data. Large language models trained on biased datasets can amplify existing stereotypes and discriminatory practices, perpetuating social inequalities and harming marginalized groups.
Let's look at potential consequences of exposure, such as individual harm. Identity theft, financial loss, reputational damage, and emotional distress can all be a result of sensitive information being exposed through large language models.
Security breaches. Leaked confidential business information can compromise valuable assets and hinder operations, resulting in financial losses and competitive disadvantages.
Erosion of trust. Public awareness of data exposure from large language models can erode trust in these technologies and hinder their acceptance and widespread adoption.
Social and ethical implications. Bias amplified by large language models can exacerbate existing inequalities, marginalize vulnerable groups, and fuel discriminatory practices, calling for careful consideration of ethical development and deployment strategies.
Let's look at some examples of real-world incidents. In 2023, a large language model used for generating marketing copy was found to be outputting text containing PII scraped from its training data, putting individuals at risk of identity theft.
A research paper released in 2024 revealed that a popular model trained on social media data exhibited racial and gender bias in its responses, prompting discussions about ethical considerations in large language model development.
Let's look at how bias infiltrates large language models. Training data. Biased datasets reflecting societal prejudices and inequalities become the foundation upon which models learn. Gender stereotypes, racial discrimination, and other forms of bias get absorbed and amplified through the training process.
Algorithmic bias. Even with seemingly neutral data, biases can be unintentionally introduced through the algorithms used to train and operate large language models. This can occur through factors like data labeling and model architecture choices.
Evaluation and feedback loops. If biased outputs go unnoticed or are reinforced through feedback loops, bias can become entrenched within the model, further perpetuating and amplifying discriminatory practices.
Let's look at some strategies to mitigate bias, such as data pre-processing and curation. Actively identifying and removing biased data points from training sets, promoting diversity and inclusivity in the data used to train models.
Debiasing algorithms. Employing techniques like counterfactual fairness and adversarial training to explicitly address and counteract bias tendencies within the large language model algorithms.
Fairness-aware evaluation and feedback. Implementing robust evaluation metrics and feedback mechanisms that identify and address biased outputs, preventing further reinforcement of discriminatory practices.
And human oversight and intervention. Establishing ethical guidelines and human oversight mechanisms to ensure responsible development and deployment of large language models, mitigating potential harm caused by bias.
Now let's look at some real-world examples. In 2022, an LLM designed for job candidate screening was found to exhibit gender bias against female applicants, highlighting the need for careful evaluation and mitigation of algorithmic bias.
And a research project in 2023 successfully implemented fairness-aware techniques to significantly reduce racial bias in a model trained on large news datasets, showcasing the potential for algorithmic interventions.
The allure of large language models' abilities to generate synthetic data and analyze personal information is undeniable. Yet, it also casts a shadow of potential misuse, raising concerns about privacy violations and ethical implications. Let's delve into this thorny section of the double-edged sword and explore the lurking dangers alongside responsible development strategies.
Let's look at some potential misuse scenarios. Deep fakes for disinformation. Large language models could be used to generate realistic but fabricated video and audio content, manipulating public opinion and spreading misinformation with unprecedented ease. Imagine political campaigns using deep-faked speeches or news media generating fake celebrity interviews. The potential for harm is significant.
Personalized surveillance and profiling. Large language models could analyze vast amounts of personal data from social media, emails, and browsing history to create detailed profiles of individuals, enabling intrusive surveillance and targeted advertising. This raises concerns about freedom of expression, targeted manipulation, and potential discrimination based on these profiles.
Privacy violation through synthetic data generation. Large language models can create realistic synthetic data sets resembling real people, potentially containing fabricated personal information. This poses risks of identity theft, fraud, and misuse for financial gain or malicious purposes.
Let's look at some ethical considerations for responsible development, such as transparency and user control. Users should be informed about how their data is used by models and have control over what information is analyzed and how it is generated. Transparency about algorithms and model training data is crucial.
Robust security and privacy safeguards. Developers must implement strong security measures to protect against unauthorized access to data and ensure that large language models are not susceptible to hacking or manipulation. This includes data anonymization and encryption techniques.
Legal and regulatory frameworks. Governments and organizations need to develop clear legal frameworks and regulations that address the ethical use of large language models and protect individual privacy. This includes accountability measures for developers and users who misuse the technology, and multi-stakeholder dialogue and education. Open communication and collaboration between developers, researchers, policymakers, and the public are vital to identify and address potential ethical issues and ensure responsible development of large language models.
Let's look at some real-world examples. In 2023, a deep-fake video of a politician making inflammatory statements spread like wildfire on social media, highlighting the potential for malicious manipulation using large language models.
And a company was caught using large language model-generated synthetic data sets to train facial recognition algorithms, raising concerns about the privacy implications of such practices.
In our quest to build a fort of defense for secure and ethical large language model integration, let's first tackle the crucial line of defense, data anonymization and pseudonymization. Here, we'll explore how these techniques cloak sensitive information and safeguard privacy within the vast training data that fuels these linguistic powerhouses.
Anonymization. The ultimate goal here is to completely remove or alter identifying information so individuals cannot be re-identified from the data. This can involve techniques like tokenization, aggregation, and differential privacy.
Pseudonymization. While still protecting privacy, pseudonymization replaces identifying information with non-identifying substitutes, pseudonyms. This allows for some level of data linking if necessary, while still upholding individual privacy.
Let's look at some anonymization techniques such as tokenization. Replacing sensitive data elements like names or addresses with random symbols or codes. This offers strong anonymization, but can hinder data analysis and usability.
K-anonymization, guaranteeing that each individual's data record appears at least alongside K1 other similar records, making individual identification statistically improbable. This offers a balance between privacy and utility.
And differential privacy, adding controlled noise to the data during analysis, ensuring accurate aggregate results while preserving individual privacy. This is a powerful technique for statistical analysis, but requires careful implementation.
Let's look at some pseudonymization strategies such as hashing, converting identifying information into fixed-length strings using mathematical algorithms. This offers irreversible anonymization, but may not prevent linking across different datasets.
Generalization, replacing specific details with broader categories such as city instead of address. This preserves some data utility, but reduces precision.
Homomorphic encryption, performing computations on encrypted data without decryption, allowing analysis without exposing identifying information. A complex but increasingly promising technique for secure data handling.
Choosing the right technique depends on the specific data, analytical needs, and desired level of privacy protection. Consider these factors.
Strength of anonymization. How effectively does the technique prevent re-identification?
Data utility. How much does the technique hinder analysis and interpretation of the data?
Reversibility. Can the original data be recovered from the anonymized or pseudonymized form?
And legal and regulatory compliance. Does the chosen technique comply with relevant data privacy regulations?
Let's look at some real-world examples. A healthcare organization uses differential privacy to analyze patient data for research purposes while upholding individual privacy.
A social media platform employs tokenization to anonymize usernames and locations in its internal datasets.
And a financial institution utilizes homomorphic encryption to perform secure credit risk assessments without exposing sensitive customer information.
In the intricate fortress of large language model data security, differential privacy shines as a powerful shield, protecting individual privacy while preserving the valuable insights gleaned from vast training data.
Let's dive into this nuanced concept, exploring its inner workings and applications in safeguarding the data powering these linguistic giants.
At its core, differential privacy strives for a delicate equilibrium. Imagine two datasets that differ by only a single data point.
Differential privacy ensures that any analysis of these datasets will yield statistically similar results, making it virtually impossible to glean information about the specific individual whose data changed.
This ingenious balancing act allows large language models to learn from extensive data while upholding the privacy of every individual within it.
Differential privacy relies on a diverse array of techniques to achieve its magic. Laplace mechanism, adding controlled noise drawn from a Laplace distribution to sensitive data values. This noise obfuscates individual contributions while preserving aggregate statistics.
Gaussian mechanism, similar to Laplace but uses a Gaussian distribution for adding noise. This offers smoother noise distribution but can be less efficient for high-precision tasks.
Moment accountant, a mathematical tool for analyzing and composing differential privacy guarantees from multiple operations on the data. Crucial for ensuring overall privacy protection through complex model training processes.
Differential privacy empowers large language models in various crucial applications such as healthcare research. Analyzing patient data for identifying disease patterns while protecting individual medical records.
Cybersecurity, studying attack patterns from network data without revealing the identities of compromised individuals.
And market analysis, uncovering consumer trends from transaction data without compromising purchase histories of specific customers.
Implementing differential privacy effectively requires careful consideration, such as privacy utility trade-off. Adding more noise enhances privacy, but can decrease the accuracy and usefulness of model outputs. Finding the optimal balance is crucial.
Algorithmic compatibility. Not all large language model algorithms readily integrate with differential privacy. Choosing compatible algorithms and adapting them for privacy preservation is important.
Computational complexity. Some differential privacy mechanisms can be computationally expensive, impacting model training efficiency. Choosing efficient techniques is essential for large-scale applications.
Differential privacy remains an actively evolving field, with continuous advancements promising even stronger privacy guarantees and wider large language model applications. As research progresses, we can expect improved noise-adding techniques. Developing more sophisticated mechanisms that minimize noise impact on data utility while enhancing privacy protection.
Privacy-preserving machine learning algorithms, designing new model algorithms specifically tailored for differential privacy integration, optimizing both privacy and performance.
Standardized best practices. Establishing clear guidelines and frameworks for implementing differential privacy in large language model development and deployment, ensuring responsible and robust data security.
Let's look at the Fortress Gates, robust authentication and authorization protocols, multi-factor authentication, adding an extra layer of security beyond passwords like code verification or biometrics to prevent unauthorized access to deployed large language models.
Role-based access control. Granting different levels of access to different users based on their roles and responsibilities, ensuring only authorized individuals can perform specific actions on the LLM.
API keys and tokens, generating unique identifiers for authorized applications to interact with the model safely and securely.
And zero trust security? Implementing the never trust, always verify philosophy, continuously authenticating and authorizing every request even from trusted sources.
Let's look at building strong walls with encryption and data security measures. Model encryption, protecting the large language model itself from unauthorized access or tampering by encrypting its code and parameters.
Data encryption, encrypting input and output data to prevent unauthorized interception and manipulation during model processing.
Secure infrastructure, deploying large language models on secure cloud platforms with robust security features like data isolation and intrusion detection systems.
Version control and access logs, maintaining a clear record of model updates and user activities to track any potential tampering or unauthorized access attempts.
Let's look at watchtowers and alarms with monitoring and threat detection.
Anomaly detection, implementing algorithms to identify suspicious activity and potential security threats related to model usage.
Log analysis, continuously monitoring access logs and system activity to detect unauthorized access attempts or unusual behavior.
Penetration testing, regularly conducting simulated attacks to identify vulnerabilities in the LLM's security posture and proactively address them.
Incident response plan, having a clear plan in place for responding to security breaches or unauthorized access attempts to minimize damage and restore normal operations.
Let's look at some real-world examples. A research institute deploys its large language model on a secure cloud platform with multi-factor authentication and role-based access control to ensure authorized access by researchers while protecting the model from unauthorized users.
A financial institution encrypts both the LLM model and all user data during processing to prevent unauthorized access and protect sensitive financial information.
A social media platform utilizes anomaly detection algorithms to identify and flag potentially harmful content generated by its large language models, protecting users from misinformation and manipulation.
Securing large language models is not a one-time endeavor, but an ongoing process requiring continuous vigilance and adaptation. As technology evolves and new threats emerge, we must adapt our security measures and remain committed to developing innovative solutions to safeguard these powerful language models.
In the intricate world of large language models, where data swirls and algorithms hum, transparency and explainability emerge as guiding lights. By openly communicating how these linguistic marvels operate, we illuminate the path towards trust, ethical development, and responsible use. Let's delve into this crucial corner of the large language model fortress, exploring how transparency builds bridges between the models and their users.
Communicating data usage and safeguards, data provenance, clearly identifying the sources and types of data used to train models, fostering awareness of potential biases, and promoting responsible data sourcing practices.
Algorithmic transparency, providing accessible explanations of how large language models process information and arrive at their outputs, demystifying the black box and empowering users to understand the reasoning behind these decisions.
Security and privacy disclosures, openly communicating the implemented safeguards for data security and user privacy, building trust through clear and concise explanations of how their information is protected.
Model performance metrics, sharing metrics like accuracy, fairness, and bias measures, allowing users to evaluate the model's capabilities and limitations and encouraging responsible development goals.
Let's look at building bridges with user-friendly explanations and interfaces. Natural language explanations explaining model outputs in clear, understandable language, avoiding technical jargon and enabling users to interpret the reasoning behind the results.
Interactive visualization tools, creating dashboards and visualizations that users can explore to understand how data flows through the model and influences its outputs.
Explainable AI techniques, implementing advanced XAI techniques to delve deeper into the model's internal workings, providing more detailed explanations for specific outputs or user queries.
Feedback mechanisms, establishing channels for users to provide feedback on model outputs and potential biases, allowing for continuous improvement and mitigation of risks.
Let's look at some real-world examples. A news organization uses a large language model to generate article summaries. They provide information about the training data used, explain the selection process for summaries, and disclose bias metrics to promote transparency and user trust.
A customer service chatbot explains its reasoning behind each suggestion in plain language, building user confidence and fostering positive interactions.
A medical diagnosis LLM offers detailed explanations for its predictions, including underlying data sources and potential limitations, empowering doctors to make informed decisions.
As large language models evolve and their applications expand, the need for transparency and explainability will only grow. We can expect standardized best practices, development of clear guidelines and frameworks for implementing model transparency and explainability across different industries and applications.
Evolving XAI techniques. Advancement of XAI methods to provide even more granular and user-friendly explanations of model outputs and decision-making processes.
And user-centric design, prioritizing user needs and expectations when designing large language model interfaces and explanation mechanisms, ensuring accessibility and comprehensibility for all stakeholders.
By shining the light of transparency and explainability on large language models, we build trust, enable responsible development, and pave the way for a future where these powerful language models benefit all, without sacrificing ethical considerations or user understanding.
As we navigate the intricate landscape of large language model integration, navigating the ever-evolving legal terrain around data privacy and compliance becomes a crucial balancing act. Let's explore the regulatory tightrope, delving into key regulations and best practices to ensure responsible development and deployment of these powerful language models.
Let's take a glance at the regulatory landscape. General Data Protection Regulation, GDPR. The EU's landmark regulation sets robust standards for data privacy and user control, impacting companies operating in the EU or handling EU citizens' data. Large language models must comply with GDPR principles like data minimization, transparency, and user consent for processing personal information.
California Consumer Privacy Act, CCPA. This California law grants consumers similar rights to access, delete, and opt out of the sale of their personal information, impacting any company collecting data from California residents. Large language models processing such data must adhere to CCPA's provisions.
AI regulation in the horizon. Various countries and regions are actively developing frameworks specifically for AI and large language models. The upcoming EU AI Act, for example, proposes risk-based regulations depending on the potential impact of AI systems.
Let's look at bridging the gap with best practices for compliance, data governance and ethics frameworks, implementing internal policies and protocols for data collection, use and storage, ensuring alignment with relevant regulations and ethical principles.
Data Privacy Impact Assessments, PIAs. Conducting PIAs to identify potential privacy risks associated with large language model development and deployment, allowing for proactive mitigation measures.
Transparency and user control mechanisms. Clearly communicating how user data is used by models and providing easy-to-access tools for individuals to exercise their data rights, such as requesting data deletion or opting out of processing.
Security infrastructure and practices. Implementing robust security measures like encryption, access control, and intrusion detection to protect data from unauthorized access and misuse.
Let's look at some real-world case studies. A multinational corporation developing a large language model for customer service incorporates data minimization principles by anonymizing training data and limiting data collection to what is essential for the model's function. A healthcare organization using a large language model for medical diagnosis conducts a PIA to identify and address potential privacy risks associated with patient data and develops a clear consent process for patients before utilizing the model.
The regulatory landscape surrounding large language models is rapidly evolving, demanding continuous adaptation and proactive compliance strategies. We can expect harmonization of regulations, efforts towards international cooperation and harmonization of data privacy and AI regulations, aimed at creating a consistent global framework for large language model development and deployment.
Focus on explainability and fairness. Regulations increasingly emphasizing transparency and explainability of AI decisions, including those made by large language models, and requiring mitigation of potential biases in training data and algorithms.
Risk-based approaches. Regulatory frameworks evolving to adopt risk-based approaches, with stricter requirements for high-risk large language model applications such as healthcare or finance.
As we navigate the complexities of data security and privacy in the large language model domain, collaboration and education emerge as indispensable tools for building a truly secure and ethical future.
Let's explore the bridges we can build between developers, researchers, and policymakers, fostering knowledge sharing and proactive solutions to ensure responsible large language model development and deployment.
Let's look at collaborating for the greater good. Industry-academia partnerships. Fostering close collaboration between large language model developers and academic researchers to address data security and privacy challenges, leveraging diverse expertise for innovative solutions.
Multi-stakeholder forums and initiatives, establishing platforms for developers, researchers, policymakers, and civil society organizations to discuss ethical challenges and jointly develop best practices for data handling and model deployment.
Open-source data and resources, encouraging the sharing of anonymized training data and research findings under responsible use agreements, accelerating progress and collective understanding of potential risks and mitigation strategies.
And joint workshops and educational initiatives. Organizing workshops and training programs for developers, researchers, and policymakers to deepen their understanding of data privacy regulations, ethical considerations, and best practices for secure large language model development.
Let's look at inspiring the next generation. Large language model curriculum development. Integrating responsible large language model development and data privacy considerations into computer science and related curricula. Equipping future developers with the necessary knowledge and ethical grounding.
Public awareness campaigns. Launching public awareness campaigns to educate individuals about large language models, data privacy issues, and their rights regarding personal information used in these technologies.
Ethical AI and data science education. Encouraging universities and training programs to incorporate modules on ethical AI and data science principles, nurturing responsible practitioners for the future of large language model development.
Let's look at some real-world initiatives. The Partnership on AI brings together leading tech companies, academic institutions, and NGOs to tackle ethical and societal challenges arising from AI, including large language models.
The Data and Trust Alliance, DATA, is a global multi-stakeholder forum dedicated to developing frameworks and best practices for trustworthy AI, including data governance and transparency in large language model development.
The Algorithmic Justice League, AJL, advocates for fair and unbiased algorithms, promoting critical examination of potential biases in large language model training data and outputs.
Collaboration and education pave the way for a future where large language models thrive alongside robust data security and ethical considerations. By fostering knowledge exchange, empowering diverse stakeholders, and educating the next generation of developers and users, we can build a landscape where large language models serve humanity not just through linguistic brilliance, but also through responsible development and respect for individual privacy.
As we stand at the precipice of a future shaped by large language models, the path forward demands not just technical prowess, but also ethical clarity.
For these linguistic marvels hold immense potential, yet also harbour hidden pitfalls. Let's delve into the intricate labyrinth of large language model ethics, posing critical questions and igniting thoughtful reflection on the societal implications of these powerful language models.
Let's look at the echo chamber of bias. Can large language models trained on vast datasets reflecting societal biases amplify these prejudices and perpetuate discrimination? How can we ensure fair and inclusive representation in training data and mitigate algorithmic bias?
How can we empower users to critically evaluate large language model outputs for potential biases, fostering ethical and responsible engagement with these technologies?
As large language models learn to mimic human language with astounding accuracy, where does the line between intelligent language processing and genuine consciousness blur? Does it raise ethical questions about agency, responsibility, and even sentience?
How can we develop robust frameworks for evaluating large language model capabilities and limitations, ensuring transparency and responsible communication about their true nature? How can we develop robust frameworks for evaluating large language model capabilities and limitations, ensuring transparency and responsible communication about their true nature? What skills and capabilities will be crucial for humans to thrive in a large language model-augmented world, and how can we develop educational systems that nurture these talents?
Can large language models be used to generate misinformation, manipulate public opinion, or even weaponize language for malicious purposes? How can we build safeguards against such misuse and promote responsible development and deployment of these powerful tools?
How can we cultivate digital literacy and critical thinking skills in the public, empowering individuals to discern truth from manipulation in a large language model-infused world?
Navigating the ethical landscape of large language models demands a collective effort. We must foster open and inclusive dialogue among developers, researchers, policymakers, and the public, ensuring diverse perspectives to inform ethical decision-making.
Establish clear ethical frameworks and guidelines for large language model development and deployment, addressing issues like bias, transparency, and accountability.
Invest in research and development of robust safeguards against potential misuse, prioritizing solutions that protect individuals and societal well-being.
Stepping into the ethical labyrinth of large language models requires not just technical solutions, but also a shared commitment to responsible development and ethical considerations.
By embracing critical reflection, open dialogue, and collective action, we can ensure that these language marvels serve not as instruments of harm, but as tools for progress, inclusivity, and a brighter future for all.
This is the end of Section 5, Data Security and Privacy Considerations for Integrating Large Language Models. This is Section 6, General Architectural and Application Security Considerations for Integrating Large Language Model APIs.
Data, the lifeblood of large language models, pulsates through APIs, connecting them to the real world. Protecting this precious resource demands robust security measures, ensuring sensitive information isn't exposed or compromised. So, let's delve into the first line of defense: data security considerations for large language model API integration.
Let's look at techniques for securing data such as data anonymization, stripping away personally identifiable information like names, addresses, and social security numbers before feeding data to the large language model API. This minimizes the risk of data breaches and protects individual privacy.
Pseudonymization, replacing PII with unique but non-identifiable identifiers. This allows data analysis and model training while preserving privacy and enabling data reversibility under specific conditions.
Encryption, transforming data into an unreadable format before transmission and storage. This safeguards against unauthorized access, even if intercepted, and can be tailored to different levels of sensitivity.
And secure multi-party computation, enabling collaborative computations on sensitive data without revealing the data itself to any individual party. This allows federated learning and collaborative analysis while keeping data privacy intact.
Let's look at privacy-preserving algorithms, tools for a stealthy flow. Differential privacy, injecting controlled noise into data while preserving aggregate results. This allows accurate model training without jeopardizing individual privacy, ensuring no single data point significantly influences the outcome.
Federated learning, training models on decentralized datasets without directly sharing data. This keeps local data secure while contributing to a collective model, balancing collaboration with privacy concerns.
Homomorphic encryption, performing computations on encrypted data without decrypting it first. This enables powerful analysis while keeping all data confidential, unlocking new possibilities for privacy-preserving large language model use cases.
Data security doesn't end with techniques. It demands a holistic approach, securing the entire infrastructure.
Secure API design, implementing strong authentication and authorization mechanisms, employing rate limiting to prevent brute force attacks, and validating all input data for potential vulnerabilities.
Secure storage and transmission protocols, utilizing HTTPS for secure communication, storing data with encryption at rest and in transit, and regularly backing up data for disaster recovery.
Vulnerability assessments and penetration testing, proactively identifying potential weaknesses in large language model API security and addressing them before attackers exploit them.
Let's look at some real-world examples. A healthcare organization uses pseudonymized patient data to train a large language model for medical diagnosis, balancing model accuracy with patient privacy.
A financial institution encrypts all customer data before feeding it to a large language model for fraud detection, safeguarding sensitive financial information during analysis.
A research consortium utilizes federated learning to train a large language model on medical scans from different hospitals, sharing model insights without revealing individual patient data.
Data security is not a static target, but an evolving battleground. As large language model applications expand and attack techniques become more sophisticated, so too must our security solutions. Here's what we can expect.
Development of advanced privacy-preserving algorithms, pushing the boundaries of secure data analysis and unlocking new possibilities for large language model usage with minimal privacy risk.
Emergence of stronger encryption standards, continuously upgrading encryption methods to stay ahead of attackers and secure data even against powerful computational resources.
And a focus on human factors, recognizing the role of human error and insider threats in data breaches and implementing security awareness training and robust access control mechanisms.
By carefully considering data security at every stage of large language model API integration, we can ensure these powerful tools contribute to progress without compromising individual privacy or unleashing a torrent of vulnerabilities.
Remember, data is the fuel for large language models, but security is the firebreak that prevents it from becoming a wildfire.
While data is the lifeblood, the large language model is the beating heart of AI language processing. Its protection demands robust fortifications, and here's how we can build them.
Token-based authentication, issuing temporary access tokens for authorized users, preventing unauthorized access attempts, and mitigating the risk of stolen passwords.
API keys, implementing unique API keys for different users or applications, enabling granular control and access logging for enhanced security.
Certificate-based authentication, utilizing digital certificates to verify the identity of both the large language model server and the client requesting access, adding an extra layer of trust and encryption.
Role-based access control, defining specific access levels based on user roles, ensuring users can only access functionalities permitted for their role.
Attribute-based access control, granting access based on dynamically evaluated attributes like location, device, or data sensitivity, offering fine-grained control and context-aware security.
Zero trust security, implementing never trust, always verify principles, constantly requiring authentication and authorization even for trusted users, minimizing the risk of insider threats.
Let's look at application vulnerability assessments such as static code analysis, identifying potential vulnerabilities within the large language model code itself, addressing bugs or security flaws before deployment.
Dynamic analysis, simulating attacker behavior and running automated tests to uncover exploitable weaknesses in the deployed model, proactively patching vulnerabilities.
Fuzzing, throwing unexpected or malformed data at the large language model to test its resilience and identify edge cases that could lead to model manipulation or crashes.
Manual testing. Leverage the expertise of security professionals to conduct comprehensive manual testing of the application's functionality and security controls. This approach can uncover vulnerabilities that automated tools miss and provides a deeper understanding of the application's attack surface.
and regular penetration testing. Engage skilled security testers to conduct periodic penetration tests, simulating real-world attack scenarios to identify and address vulnerabilities before they can be exploited by attackers. This proactive approach helps maintain a strong security posture over time.
Let's look at system infrastructure hardening, such as security baselines. Establish well-defined security configurations for operating systems, network devices, and software applications. Adhere to industry-standard baselines such as CIS benchmarks and DISA STIGs. Or create customized configurations tailored to your specific environment.
Vulnerability scanning. Regularly scan IT systems for known vulnerabilities using reputable tools like Nessus, Qualys, and Rapid7.
Patch management. Implement a comprehensive patch management process to ensure timely installation of security updates for operating systems, applications, and firmware. Automate patching whenever possible to streamline the process and reduce exposure windows.
Least privilege. Enforce the principle of least privilege, granting users and applications only the minimum access rights required to perform their essential functions. This limits the potential damage if a system or account is compromised.
Configuration management. Maintain tight control over system configurations using tools like Ansible, Puppet, Chef, and Terraform. This ensures consistency, prevents unauthorized changes, and simplifies auditing and compliance.
Logging and monitoring. Centralize log collection and analysis to monitor for suspicious activity, detect potential breaches, and facilitate incident response. Use tools like security information and event management systems to correlate events across multiple systems and identify patterns of attack.
Network security. Implement firewalls, intrusion detection prevention systems, and network segmentation to control traffic flows, detect malicious activity, and isolate sensitive systems.
Compliance. Adhere to relevant industry standards such as PCI DSS, HIPAA, and SOC 2 to ensure the security and privacy of sensitive data.
Penetration testing. Conduct periodic penetration testing to proactively identify and address potential vulnerabilities before they can be exploited by attackers.
And continuous improvement. Embrace a culture of continuous security improvement, regularly reviewing and updating hardening measures in response to evolving threats and vulnerabilities.
Let's take a closer look at intrusion detection systems, IDS. Anomaly detection. Monitoring large language model activity for suspicious behavior patterns, such as unexpected input formats or attempts to access unauthorized data, raising alerts for potential attacks.
Signature-based detection. Identifying known attack signatures within large language model logs or data flows, triggering alarms and enabling rapid response against specific threats.
And behavioral analysis. Utilizing machine learning to learn large language models' normal behavior and flag deviations, catching novel or zero-day attacks that traditional methods might miss.
Let's look at some real-world case studies. A social media platform utilizes API keys and role-based access control to control access to its large language model-powered content moderation tool, ensuring only authorized users can manage sensitive content.
A financial institution performs regular vulnerability assessments on its fraud detection large language model, patching identified weaknesses before attackers can exploit them.
A healthcare organization monitors its large language model for medical diagnosis using anomaly detection, alerting doctors to potential biases or suspicious behavior in the model's outputs.
The battle for model security is ongoing, and we can expect development of advanced adversarial training techniques, training large language models to recognize and resist adversarial attacks, making them more robust against manipulation attempts.
Emergence of explainable AI for security. Utilizing XAI techniques to understand how models make decisions and identify potential biases or vulnerabilities, enabling proactive mitigation measures.
And continued focus on human factors, addressing the risk of social engineering and insider threats through security awareness training and robust access control systems.
By diligently implementing model security measures, we can ensure that large language models operate with integrity, preventing unauthorized access, manipulation, and misuse.
Trustworthiness is not just a buzzword, it's a cornerstone of large language model success, and model security is the foundation upon which that trust is built.
Large language models, those linguistic powerhouses, can only unleash their full potential when paired with robust APIs. But just like any bridge, APIs require secure design and construction to ensure smooth, trustworthy communication.
So let's explore the best practices for building secure large language model API integrations, ensuring robust design, access control, and threat resilience.
Let's look at the foundations of secure design. Minimum viable interface. Expose only the functionalities essential for model interaction, minimizing attack surface and reducing complexity.
Versioning and deprecation. Maintain clear versioning for APIs and gracefully deprecate old versions to avoid vulnerabilities in outdated code.
Standardized formats. Utilize well-established data formats like JSON for input and output, promoting clarity and compatibility.
Error handling and logging. Implement comprehensive error handling and logging mechanisms to identify and troubleshoot potential issues quickly.
Let's look at some access control protocols such as authentication. Employ multi-factor authentication for robust user verification, going beyond simple passwords.
Authorization. Leverage role-based access controls or attribute-based access control to grant granular access based on user roles or attributes, preventing unauthorized actions.
Rate limiting. Implement rate limiting to prevent brute force attacks and denial of service attacks, safeguarding against malicious overload.
Throttling. Introduce throttling mechanisms to automatically adjust resource allocation based on usage patterns, further preventing abuse and ensuring fair access.
Be sure to map the battlefield with threat modeling, identify potential threats. Analyze attack vectors like SQL injection, cross-site scripting, and unauthorized access attempts to understand vulnerabilities.
Model risk assessment. Evaluate the potential risks associated with model outputs, such as bias, manipulation, or data privacy breaches.
Mitigation strategies. Implement countermeasures like input validation, sanitization, and encryption to address identified threats and minimize risk.
And regular testing and updates. Conduct regular security assessments and penetration testing to uncover hidden vulnerabilities and ensure continuous improvement.
Let's look at some real-world case studies. A customer service chatbot utilizes minimum viable interface and role-based access controls to limit API access to specific functionalities and grant access only to authorized agents.
A financial fraud detection large language model API employs rate limiting and throttling to prevent malicious attempts to overload the system and compromise its effectiveness.
A content moderation platform integrates its large language model through a well-documented API with clear error handling and logging, enabling efficient troubleshooting and improving transparency.
Let's look at the future of secure API design. Evolving standards and frameworks. As large language model usage expands, secure design best practices will continue to evolve, requiring ongoing adaptation and adherence to updated standards.
Rise of API security tools. New tools and automation will emerge to assist in threat modeling, vulnerability assessments, and secure API implementation, streamlining the process for developers.
And focus on developer education. Equipping developers with the knowledge and resources to design secure APIs from the ground up will be crucial to building a foundation of trust in large language model integrations.
By diligently applying these best practices, we can transform APIs from potential vulnerabilities into secure gateways, ensuring seamless and trustworthy communication between users and these powerful language models.
Remember, secure API design is not just an afterthought. It's the bedrock upon which robust, reliable, and responsible large language model integrations are built.
Large language models aren't just theoretical marvels, they're actively transforming industries. So, let's step into the real world and examine specific examples of large language model API integrations and how diverse companies are tackling security concerns head-on.
Case Study 1. Customer service chatbot in the retail industry.
Challenge. Build a secure large language model-powered chatbot to handle customer inquiries while protecting sensitive data like purchase history and payment information.
Security solutions, data anonymization. Customer data is anonymized before feeding it to the model, minimizing the risk of identifying individuals.
Token-based authentication. Users access the chatbot through unique tokens, eliminating password vulnerabilities.
RBAC. Specific access levels control what information the chatbot can access and share based on the user's role.
And regular vulnerability assessments. Continuous scans by security experts identify and address potential weaknesses in the model and API.
Case Study 2. Fraud detection in financial services.
Challenge: utilize a large language model API to analyze financial transactions in real time and detect fraudulent activity while ensuring data privacy and regulatory compliance.
Security solutions. Secure API design. Minimum viable interface and granular access controls limit exposure to sensitive data and prevent unauthorized access attempts.
Encrypted data transmission. Financial data is encrypted using strong protocols at rest and in transit, adding an extra layer of protection.
Differential privacy. The large language model analyzes patterns across datasets without revealing individual transactions, safeguarding customer privacy.
Explainable AI. XAI tools help understand the model's decision-making process and identify potential biases in fraud detection, ensuring fairness and transparency.
Case Study 3. Personalized content recommendations in the media industry.
Challenge: leverage a large language model to personalize content recommendations for users while upholding data privacy and preventing filter bubbles.
Security solutions. Pseudonymization. User data is pseudonymized, allowing for personalized recommendations without revealing individual identities.
Federated learning. The model is trained on decentralized datasets without sharing individual user data, protecting privacy while benefiting from collective insights.
Anomaly detection. The large language model monitors its output for potential recommendations that reinforce biases or filter bubbles, promoting diversity and inclusivity.
Transparency and user control. Users are informed about how their data is used and given control over the recommendations they receive, building trust and fostering responsible data practices.
Case Study 4. Security Vulnerability Analysis for the IT Sector.
Challenge: employ a large language model API to analyze vast amounts of system documentation, code, and network logs to identify potential vulnerabilities and security risks efficiently, reducing manual effort and accelerating remediation.
Solution. Secure document upload. Encrypted and access-controlled document upload mechanisms ensure sensitive system documentation is protected from unauthorized access or data breaches.
Data isolation. Large language model analysis is performed within isolated environments to prevent potential malware or malicious code within documents from compromising other systems.
Output validation. Vulnerability findings generated by the model are validated by security experts to ensure accuracy and address potential false positives or biases.
Explainable AI. XAI techniques are incorporated to provide insights into the model's decision-making process, allowing security architects to understand the reasoning behind identified vulnerabilities and foster trust in the tool's recommendations.
And continuous model updates. The model is regularly updated with the latest security vulnerability knowledge and threat intelligence to maintain its effectiveness and relevance in a rapidly evolving threat landscape.
Now let's look at some key takeaways. No single security solution fits all. Companies must tailor their approach based on the specific large language model use case, industry regulations, and data sensitivity.
Continuous vigilance is crucial. Regular vulnerability assessments, threat modeling, and penetration testing are essential to stay ahead of evolving threats.
And transparency and user control are vital. Building trust requires informing users about data usage and empowering them to manage their interactions with large language models.
As large language model applications expand, so will the need for industry-specific security standards and best practices. Collaboration is key.
Open communication and knowledge sharing between companies, researchers, and security experts will be crucial in developing robust defenses against emerging threats. Ethical considerations remain paramount. We must ensure that security measures don't inadvertently perpetuate biases or infringe upon individuals' rights.
This is the end of Section 6, General Architectural and Application Security Considerations for Integrating Large Language Model APIs. This is Section 7, Introduction to Large Language Model Chains and Flow Eyes.
Imagine single large language models as powerful tools, each with their own specializations. Now, picture large language model chains as intricate tapestries woven from these tools, where outputs from one model flow seamlessly into the next, creating a symphony of linguistic prowess.
Essentially, large language model chains are sequences of multiple models linked together, where the output of one model becomes the input for the next, enabling complex tasks and functionalities beyond the capabilities of any single model.
Meet FlowEyes. Think of FlowEyes as the maestro of this linguistic orchestra. It's a visual platform specifically designed to build and orchestrate large language model chains. Through its intuitive drag-and-drop interface, you can connect different models like building blocks, define data flows, and fine-tune parameters to create intricate chains that produce remarkable outcomes.
FlowEyes can be installed on Windows and many Linux-based operating systems and is distributed under the Apache License 2.0, a permissive open-source license that grants users significant freedoms.
This means you have the right to redistribute the software, share it with others in its original form or with modifications you make.
Modify the code, create derivative works by combining FlowEyes with other code or adapting it to your specific needs.
Use it for commercial purposes. Integrate FlowEyes into commercial products or services you develop and sell.
Sublicense the software. Grant others the right to use FlowEyes under the same terms of the Apache License 2.0.
This flexibility makes FlowEyes a versatile tool for various individuals and organizations, fostering collaboration and innovation.
FlowEyes itself is built on the powerful LangChain framework, which utilizes Python as its primary language. This means custom modules are developed in Python, allowing developers with that skill set to unleash their creativity within the world of large language models. It's a beautiful confluence of human ingenuity and linguistic prowess.
Imagine large language model chains as intricate choreographed dances where different models perform specific tasks in a seamless sequence.
To ensure this smooth flow, large language model system messages act as the hidden conductors, communicating vital information between models and orchestrating the entire chain execution.
These messages are short instructions or directives that trigger the start and completion of tasks within the chain, transfer data between models for further processing, and manage checkpoints and error handling, ensuring smooth recovery and chain stability.
While invisible to the user, system messages play a crucial role in the behind-the-scenes functioning of large language model chains, silently ensuring the dance of models leads to accurate and efficient results.
Let's look at the advantages of large language model chains: synergy and specialization. By combining the strengths of multiple models, large language model chains can tackle tasks requiring diverse skills, unlocking capabilities beyond the reach of single models. Imagine a chain where one model analyzes sentiment, another summarizes text, and a third generates a creative response based on those insights. The possibilities are endless.
Increased accuracy and robustness. Large language model chains can potentially mitigate the weaknesses of individual models. By feeding outputs through multiple processing steps, errors or biases can be filtered out, leading to more accurate and reliable results.
Enhanced creativity and innovation. The ability to combine diverse large language model functionalities opens doors to groundbreaking applications. Imagine generating personalized poems, incorporating historical narratives, translating complex scientific documents into engaging stories, or crafting marketing campaigns tailored to individual customer profiles. The creative potential is boundless.
Let's look at comparing and contrasting large language model chains with other methodologies. Single large language models. As mentioned earlier, large language model chains offer greater complexity and functionality compared to single models. While single large language models excel at specific tasks, large language model chains are true powerhouses of intertwined capabilities.
API chaining. While both involve sequences of models, LLM chains differ from API chaining in their focus on deep linguistic processing. API chains typically connect software tools with different functionalities, while LLM chains focus on the nuanced manipulation and generation of language itself.
Human-in-the-loop approaches. LLM chains are not meant to replace human expertise. Rather, they can automate repetitive tasks and provide enhanced insights, allowing humans to focus on critical decisions and creative input, leading to a collaborative and powerful workflow.
The toolbox of large language model masters, pre-trained models. These are the workhorses of the bunch, pre-trained giants like GPT-3 or Jurassic 1 Jumbo, providing a broad spectrum of abilities like text generation, translation, and question answering. Think of them as versatile tools ready to be plugged into the chain.
Custom modules, not content with off-the-shelf solutions? Craft your own. FlowEyes empowers you to build custom modules using Python, tailoring functionality to your specific needs. Imagine a large language model specializing in medical diagnosis or personalized financial analysis. The possibilities are limited only by your imagination.
APIs. Don't forget the external world. Large language model chains can seamlessly integrate with external APIs, incorporating specialized functionalities like image recognition, sentiment analysis, or even weather data. This expands the linguistic playground even further, turning large language models into truly global citizens.
Now comes the magic, weaving these modules into intricate sequences. FlowEyes makes it as easy as drag and drop. Connect a pre-trained models to your custom module, feed the output to an API, and voila! You've built a linguistic assembly line generating unique insights, crafting personalized stories, or even composing AI-powered sonnets.
Remember, the key lies in understanding the strengths and weaknesses of each module. A text summarizer, followed by a creative writer, generates different outcomes than a sentiment analyzer feeding a question-answering model. It's all about crafting the perfect chain for your specific goals.
Imagine a team of linguistic conductors each leading different sections of the language symphony. FlowEyes' agents play this role, representing individual modules within your LLM chain. Each agent has its own specialization, be it pre-trained models, custom scripts, or external APIs.
Pre-trained agents. These are the ready-made maestros, offering functionalities like text summarization, translation, or question answering.
Custom script agents. This is where your creative spark shines. Craft your own agents using Python tailored to your specific needs and goals.
API agents. Expand your repertoire by integrating external APIs into the chain, incorporating image recognition, sentiment analysis, or even weather data.
Let's look at fueling the flow with input and output tools. File upload tools. Feed your agents the raw material they need. FlowEyes provides intuitive tools to upload text, images, or other data formats, triggering the linguistic chain reaction.
Vector database tools. For complex tasks requiring access to vast datasets, FlowEyes integrates seamlessly with vector databases. Imagine training your custom agents on millions of documents or leveraging pre-trained vector embeddings for enhanced accuracy.
Buffer memory tools. Ensure smooth data flow within your large language model chain. FlowEyes' buffer memory tools temporarily store intermediate outputs, preventing bottlenecks and guaranteeing efficient processing even for intricate chains.
Let's go beyond the basics with powerful components for advanced workflows. State management. Keep track of your chain's progress and context. FlowEyes allows you to manage state variables, ensuring consistent results even for multi-step workflows.
Conditionals and loops. Introduce logic and iteration into your large language model chains. Use conditional statements to branch the flow based on specific outputs, and utilize loops for repetitive tasks, creating intelligent and dynamic workflows.
And error handling and debugging. No chain is perfect. FlowEyes offers robust error handling tools, catching and correcting issues to ensure seamless execution and troubleshoot potential hiccups.
We've just cracked open the toolbox of large language model chains and FlowEyes. Next, let's explore real-world applications, showcasing how these chains are revolutionizing diverse industries.
We can then delve into technical considerations, ensuring your own large language model creations are robust and secure. And of course, let's not forget the ethical and social implications of this powerful technology.
Imagine chatbots that not only understand your questions, but also respond with wit, empathy, and personalized touch. Large language model chains make this a reality. By combining sentiment analysis, contextual understanding, and creative generation, LLM chains can power chatbots that hold captivating conversations, offer tailored solutions, and build genuine connections with users.
Think customer service that anticipates your needs, educational bots that adapt to your learning style, or even companions that provide emotional support. The possibilities are endless.
Need engaging video scripts, captivating marketing copy, or even personalized poems for loved ones? Large language model chains are your muse. By chaining a text summarizer with a creative writer and a fact-checker, you can generate unique and informative content tailored to your audience.
Imagine crafting viral social media posts, summarizing complex research papers into engaging narratives, or even generating personalized children's stories based on family history. The creative potential is boundless.
Data analysis just got a linguistic upgrade. Large language model chains can process vast amounts of text data, identifying patterns, extracting key information, and generating actionable insights that traditional methods might miss.
Imagine analyzing customer reviews to predict trends, mining social media data to understand public sentiment, or even analyzing medical records to discover hidden correlations. The power of data unlocks new potential with large language model chains leading the way.
Coding can get a boost from language models too. LLM chains can analyze existing code, suggest improvements, and even generate new code snippets based on natural language descriptions.
Imagine brainstorming code functionalities with a large language model, automating repetitive coding tasks, or even generating documentation or comments from your code directly. The efficiency and creativity of coding get a linguistic makeover.
Large language chains can revolutionize education by tailoring learning experiences to individual needs and styles. Imagine a large language model chain that generates personalized study materials based on a student's strengths and weaknesses, provides real-time feedback on writing assignments, or even engages in adaptive tutoring sessions adjusted to the student's pace. The future of learning becomes dynamic and engaging with LLM chains.
These are just a few sparks igniting the fire of large language model chain applications. From healthcare to art, finance to journalism, every industry can benefit from the unique capabilities of these interconnected language models.
As we move forward, we can delve deeper into specific examples, exploring technical challenges, ethical considerations, and the limitless potential of large language model chains to shape the future.
Imagine weaving together multiple language models like tributaries in a river. Ensuring smooth data flow is crucial.
Large language model chains require robust mechanisms to manage input, output, and intermediate data between various modules. Techniques like buffer memory allocation, efficient queuing systems, and data serialization optimization become vital for seamless execution.
Not all large language models speak the same language. Ensuring compatibility between different models within a chain is another hurdle. Standardization formats for data interchange, common communication protocols, and versioning management become key tools to overcome language barriers and enable smooth conversation between models.
Large language models, like any powerful tool, come with potential risks. Bias, security vulnerabilities, and unintended consequences need to be addressed. Techniques like bias detection and mitigation algorithms, robust access control mechanisms, and regular vulnerability assessments become essential shields to protect against unintended outcomes.
Deploying large language model chains at scale presents additional challenges. Resource management, infrastructure optimization, and fault tolerance mechanisms need careful consideration. Techniques like containerization, distributed computing architectures, and automated performance monitoring become keys to unlocking the full potential of large language model chains in real-world applications.
Luckily, we're not alone in this technical adventure. Open-source frameworks like FlowEyes provide powerful tools for building and deploying large language model chains. These platforms offer features like visual flow editors, modular agent integration, and built-in data management tools, making the process more accessible and efficient.
The technical considerations are not simply roadblocks, but opportunities for innovation. By understanding these challenges and implementing creative solutions, we can build robust, secure, and scalable large language model chains that unlock the true potential of this transformative technology.
While FlowEyes offers a visual interface for building large language model chains, let's explore the technical intricacies of its installation, management, and interaction with models, ensuring secure and efficient operation.
Let's look at hosting FlowEyes on a server. Prerequisites. Ensure your server meets the minimum requirements with a compatible version of Windows or Linux OS and required libraries.
Installation. Follow the official FlowEyes documentation for detailed instructions typically involving cloning the repository and running setup scripts.
Configuration. Set up API keys, authentication methods, and resource allocations based on your specific needs.
Let's look at some key sections to explore in the FlowEyes API documentation. Authentication methods. Discover secure ways to access FlowEyes, including API keys, JWT tokens, and OAuth configurations. Understand the appropriate method for your specific integration needs.
Available endpoints. Delve into the diverse capabilities of FlowEyes through its well-structured endpoints. Explore categories like agents, projects, deployments, and data management, revealing the programmatic interfaces to control every aspect of your large language model chains.
Request and response formats. Decode the language of communication between your programs and FlowEyes. Learn about supported data formats like JSON for requests and responses, ensuring smooth transmission of information.
Detailed examples. Put theory into practice. Immerse yourself in the code examples provided by FlowEyes, understanding how to execute specific tasks like creating agents, triggering chains, and accessing outputs programmatically.
Authentication, locking the gates. Unique module API key. FlowEyes offers the option to generate unique API keys in the form of bearer tokens for individual connections to a module's API.
API keys for large language models. FlowEyes securely stores API keys required to connect to large language models.
API keys for tools. FlowEyes securely stores API keys for connections to other applications being utilized within a module via tools.
Database connection keys. FlowEyes securely stores key secrets for connections to vector databases and buffer memory caches or databases.
FlowEyes' API goes beyond simple control. It opens doors to exciting possibilities such as real-time data streaming. Integrate FlowEyes with other applications for real-time data exchange, enabling immediate responses and dynamic workflows.
Custom integrations. Craft bespoke integrations with external APIs using FlowEyes' versatile capabilities, extending the reach and power of your large language model chains.
Automated deployments and workflows. Leverage the API to manage large language model chain deployments, triggers, and data flow programmatically, automating repetitive tasks and streamlining your work.
Let's look at large language model integration choices. Hosted versus local. Connecting to hosted large language models. FlowEyes seamlessly integrates with various hosted language model providers like OpenAI or Cohere. Follow their specific authentication and usage guidelines.
Setting up local large language models. For custom-trained or locally hosted models, use FlowEyes' agent framework to create custom modules that interact with your models via APIs or other communication methods.
Let's look at parsing text documents and preparing for embedding. Chunking. FlowEyes typically processes text in chunks to optimize memory usage and performance. Adjust chunk size based on model and task requirements.
Vectorization. Transform text chunks into numerical representations, embeddings, compatible with large language models. FlowEyes often handles this internally, but you may need to configure specific embedding methods.
Let's look at some general technical security considerations. Access control. Implement robust authentication and authorization mechanisms to control access to FlowEyes and model resources.
Input validation. Sanitize user inputs to prevent injection attacks and protect against malicious code execution.
Data handling. Ensure sensitive data is encrypted at rest and in transit to protect confidentiality and privacy.
Vulnerability management. Regularly update FlowEyes and its dependencies to address security vulnerabilities.
And monitoring and logging. Track usage patterns and detect anomalies to identify potential security threats.
Remember, security is an ongoing process, not a one-time setup. Stay vigilant, adhere to best practices, and continuously evaluate and adapt security measures to protect your large language model chains and the data they process.
Large language model chains hold immense potential, but like any powerful tool, they require responsible use and careful consideration of their ethical and social implications. Let's embark on a thought-provoking exploration of these crucial aspects.
Like their individual components, large language model chains can inherit and amplify biases present in training data or model design. This can lead to unfair or discriminatory outcomes, impacting everything from loan approvals to healthcare diagnoses.
We must actively debias LLM chains through diverse training datasets, ethical model design, and constant vigilance.
Large language model chains can operate like black boxes, their internal workings obscured. This lack of transparency undermines trust and makes it difficult to identify and address biases or errors.
We need tools for explainable AI, allowing us to understand why a large language model chain produces specific outputs and hold it accountable for its decisions.
Large language model chains often process sensitive personal data. Robust security measures are crucial to prevent data breaches and misuse.
As large language model chains automate tasks, job displacement becomes a concern. We must prepare for this shift by upskilling and reskilling workforces, ensuring equitable access to new opportunities created by this technology.
Moreover, we need to consider the broader social impact of model chains on various industries and communities, mitigating potential negative consequences and maximizing positive contributions.
Developing and deploying large language model chains ethically requires collaboration between researchers, developers, policymakers, and the public. We need ethical guidelines, robust governance frameworks, and open conversations to ensure responsible development and use of this powerful technology.
Remember, the ethical and social implications of large language model chains are not technical problems with simple solutions. They require ongoing dialogue, continuous research, and active efforts to mitigate risks and maximize benefits.
Here are some questions to ponder as we navigate this challenging terrain.
How can we ensure large language model chains promote fairness and inclusivity?
What level of transparency should be expected from these complex systems?
How can we safeguard individual privacy while harnessing the power of data-driven innovation?
What ethical frameworks should guide the development and deployment of model chains?
And how can we prepare for the social and economic changes brought about by these powerful tools?
By grappling with these questions and taking proactive steps, we can ensure that large language model chains become a force for good, empowering individuals, fostering collaboration, and shaping a future where technology serves humanity's highest ideals.
This is the end of Section 7, Introduction to Large Language Model Chains and Flow-Eyes. This is Section 8, Integrating Flow-Eyes for Security Research and Systems Analysis Tasks.
The ever-evolving landscape of cyber threats demands innovative tools to stay ahead of the curve. Enter Flow-Eyes, a powerful platform harnessing the power of large language models to revolutionize the way IT security professionals approach their critical tasks.
From threat hunting and incident response to vulnerability analysis and intrusion detection, Flow-Eyes empowers security experts to unlock new insights, automate processes, and streamline workflows, enabling them to effectively shield their organizations from the ever-growing arsenal of cyber adversaries. Let's look at some important examples by job roles.
Security architect, vulnerability, prioritization. Train large language models to analyze vulnerability reports, exploit databases, and threat intelligence feeds. Build model chains that prioritize vulnerabilities based on exploitability, attack vectors, and potential impact, guiding remediation efforts towards the most critical issues.
Security architecture validation, threat modeling. Develop large language models that can analyze system design documents, architecture diagrams, and configuration files. Build model chains that simulate attacks against proposed architectures, identifying potential weaknesses, and recommending security enhancements before deployment.
Compliance automation. Design large language models to interpret and assess compliance requirements from complex regulations like NIST 853 or PCI DSS. Generate automated reports highlighting deficiencies and suggesting remediation actions to streamline compliance audits.
Let's look at uses for an application security analyst or engineer. Code vulnerability detection. Train large language models on known vulnerabilities and coding patterns associated with security flaws. Build model chains that scan source code and identify potential vulnerabilities with high accuracy, freeing up analysts for deeper analysis and mitigation strategies.
Software composition analysis. Develop large language models that analyze dependencies and libraries used in software projects. Build model chains that identify vulnerabilities or outdated versions within dependencies, ensuring secure software development practices.
API security analysis. Design large language models to understand API specifications and protocols. Build model chains that scan APIs for common security misconfigurations and potential attack vectors, proactively guarding against API-based threats.
Let's look at some uses for an identity access management analyst. User privileged access review. Train large language models on least privilege principles and access control best practices. Build model chains that analyze user permissions and access logs, identifying users with excessive privileges or suspicious activity patterns, prompting timely privilege reviews and access adjustments.
Anomaly detection in access activities. Develop large language models that can learn normal user access patterns within systems. Build model chains that monitor user activity and detect anomalous behavior, potentially indicating compromised accounts or malicious activity.
User identity risk assessment. Design large language models to analyze user data and activity logs from various sources. Build model chains that assess user risk based on factors like access level, login location, and activity patterns, prioritizing high-risk users for additional scrutiny and potential access restrictions.
Let's look at some uses for a SOC analyst. Log analysis and threat detection. Train large language models on known attack patterns and indicators of compromise. Build model chains that analyze security logs from various systems, identifying potential threats, and triggering incident response protocols based on model confidence scores.
Malware analysis and sandboxing integration. Develop large language models that can analyze suspicious files and activities within sandboxes. Build model chains that provide insights into malware behavior and potential mitigation strategies, augmenting sandboxing analysis with linguistic insights.
Security information and event management integration. Design large language models that understand SIM data formats and event correlations. Build model chains that analyze data across multiple SIM systems, uncovering hidden connections and suspicious activities that individual SIMs might miss.
Let's look at some uses for an incident response and forensic analyst. Incident investigation and root cause analysis. Train large language models on historical incident data and investigative methodologies. Build model chains that analyze incident logs, network traffic, and system state changes, aiding in identifying the root cause of security incidents and streamlining investigation processes.
Evidence collection and analysis. Develop large language models that understand artifact formats and forensic analysis techniques. Build model chains that automate evidence collection across various systems. Analyze collected artifacts, and highlight potentially incriminating evidence for further investigation.
Threat hunting and predictive analysis. Design large language models that can identify subtle patterns and anomalies in security data. Build model chains that predict potential future attacks and identify emerging threats, proactively informing threat hunting efforts and resource allocation.
These are just a few examples, and the possibilities are vast. Remember, the key is to identify specific workflows and pain points within each security role, where flow eyes and large language models can add the most value, then tailor model chains to address those specific needs.
Let's explore further. What specific security roles and tasks are you most interested in? Are there any particular challenges or pain points you'd like flow eyes and large language models to address? How can we best ensure effective integration of flow eyes with existing security tools and workflows?
By collaborating on these details, we can create a comprehensive and practical guide showcasing how flow eyes can empower security professionals in various roles, making them linguistic superheroes in the fight against cybercrime.
Let's address training these linguistic defenders. Data security and bias. The data used to train models can introduce biases or vulnerabilities. Carefully curated, security-specific datasets, coupled with bias detection and mitigation techniques, are crucial.
Explainability and trust. Security decisions hinge on trust. Implement explainable AI methods to understand how models reach their conclusions, fostering trust and ensuring responsible use.
Continuous learning and adaptation. The threat landscape evolves. Continuously refine model training with fresh data and threat intelligence to maintain performance and prevent obsolescence.
Let's look at deployment and integration. Securing the fortress. Ensure robust security measures around large language model infrastructure, including access controls, encryption, and intrusion detection systems.
Integrating with existing tools. Large language models should seamlessly integrate with existing security tools and platforms, avoiding siloed information and maximizing efficiency.
Scalability and performance. Security workflows demand high-performance computing resources. Optimize large language model architecture and resource allocation to meet operational demands.
Let's look at data privacy and compliance. Privacy-preserving techniques. Sensitive data needs protection. Explore federated learning or differential privacy techniques to train models without compromising data privacy.
Compliance with regulations. Understand and adhere to relevant data privacy and security regulations like GDPR or HIPAA when handling and processing data.
Auditing and reporting. Establish transparent auditing and reporting processes to demonstrate compliance and maintain stakeholder trust.
Now, let's look at some solutions and strategies. Partnerships with security experts. Collaborate with cybersecurity experts to identify real-world needs and develop models tailored for specific security tasks.
Open source development and security audits. Encourage open source development and regular security audits of large language model frameworks and tools to address vulnerabilities and build trust.
And standardized best practices. Define and promote industry-wide best practices for secure model training, deployment, and usage in security environments.
Remember, harnessing the power of large language models in security requires a nuanced approach. By prioritizing data security, fostering trust, and adhering to ethical principles, we can ensure that models become powerful allies, not adversaries, in the fight against cybercrime.
Let's explore further. Which specific large language model applications in security raise the most significant technical concerns for you? What existing tools or frameworks should be considered for secure model deployment in security environments? How can we encourage collaboration and knowledge sharing to develop secure and trustworthy models for the cybersecurity community?
Ready to unleash the full potential of FlowEyes in your daily security routine? Let's explore some practical tips and guidelines to maximize its benefits and transform you into a linguistic security ninja.
Identify workflow bottlenecks. Analyze your daily tasks and pinpoint areas where repetitive, data-driven processes could benefit from large language model automation.
Gather data wisely. Collect relevant security data from logs, reports, and configurations, ensuring quality and compliance with privacy regulations.
Train with precision. Tailor model training data to your specific needs and security contexts, focusing on relevant threats, vulnerabilities, and best practices.
Here are some tips for building large language model powerhouses. Start small, dream big. Begin with pilot projects for specific tasks, gradually building confidence and expertise before scaling up large language model applications.
Chain the power. Design large language model chains that combine multiple models for different tasks, optimizing efficiency and achieving deeper insights.
Unlock advanced choreography. Unleash the full potential of large language model chains by incorporating system messages. These hidden conductors provide critical instructions, manage data flow, and trigger specific actions within the chain, enabling complex workflows and sophisticated analysis. Imagine system messages as stage directions for your large language models, ensuring a seamless and effective performance.
Human in the loop. Remember, large language models are tools, not replacements. Integrate them with your expertise and judgment for informed decision-making.
Integrate seamlessly. Connect FlowEyes with your existing security tools and platforms to create a unified workflow and avoid data silos.
Monitor and maintain. Regularly assess model performance, update training data, and refine configurations to ensure accuracy and relevance.
Share the knowledge. Foster a culture of collaboration within your team. Share model insights and upskill everyone on the power of linguistic security.
Let's look beyond the basics. Explore advanced large language models. Consider more sophisticated model capabilities like anomaly detection, threat prediction, and sentiment analysis for proactive security insights.
Participate in the community. Engage with the FlowEyes community. Share best practices and contribute to the development of even more powerful models for security.
And become a large language model champion. Advocate for the responsible and ethical use of large language models in security, ensuring they remain a force for good in the digital world.
Remember, FlowEyes is a powerful tool, but its effectiveness rests in your hands. By applying these best practices and continuously exploring its potential, you can transform your security workflows, gain valuable insights, and make your organization a fortress against cyber threats.
With FlowEyes as your linguistic sidekick, you're equipped to face any digital challenge and build a future where cybersecurity is not just a goal, but a seamless reality.
Let's keep the conversation going. What specific tasks are you most excited to try with FlowEyes in your daily work? What challenges do you anticipate in integrating FlowEyes with your existing workflows?
This is the end of Section 8, integrating FlowEyes for security research and systems analysis tasks. This is Section 9, security considerations for integrating FlowEyes.
Imagine the power of large language chains with access to your data at your fingertips. What would you do with all that power? But with great power comes great responsibility.
Remember that FlowEyes is not just a tool, but application software and must be treated as such within the rules of your organization.
When we talk about integrating FlowEyes, we mean installing FlowEyes Server, installing local large language model, optional, configuring hosted API, installing vector databases or configuring hosted vector databases, installing buffer memory cache, database server or configure hosted buffer memory cache, and connecting and securing systems connections.
Designing and implementing your FlowEyes system should follow system development lifecycle, best practices, including security control requirements. Let's take a look at how these apply to developing your FlowEyes system.
Let's discuss server setup and hardening. The choice of your server operating system lays the foundation for your FlowEyes installation's security. Here are some key considerations.
Security architecture. Prioritize operating systems with robust security architectures, including features like mandatory access control, kernel hardening, and application sandboxing.
Popular choices include Linux distributions like Ubuntu LTS, Debian Stable, and Red Hat Enterprise Linux, known for their strong security focus.
Patching frequency. Choose an OS with a reliable and timely patching system to ensure prompt installation of critical security updates. Regularly updated distributions like Ubuntu LTS receive security patches for extended periods, minimizing vulnerability windows.
Threat mitigation technologies. Consider operating systems with built-in intrusion detection and prevention systems, malware scanners, and other threat mitigation tools. Some Linux distributions offer advanced security modules like Security Enhanced Linux or AppArmor for enhanced protection.
Let's look at resource optimization. System requirements. Match your OS choice to FlowEyes' system requirements regarding CPU, memory, and storage. Lightweight distributions like Ubuntu Server or Alpine Linux can be ideal for minimal resource environments.
Containerization options. Consider containerization technologies like Docker or Kubernetes if you plan to deploy FlowEyes alongside other applications. Containerized environments promote isolation and resource efficiency, enhancing security and flexibility.
Let's look at community and support. Large user base. Opt for operating systems with a large and active user community. This ensures access to extensive documentation, troubleshooting resources, and security advisories. Distributions like Ubuntu and Debian benefit from vibrant communities that contribute to their ongoing security and stability.
Commercial support. For mission-critical deployments, consider operating systems with dedicated commercial support options. Vendors like Red Hat and SUSE offer enterprise-grade support contracts, providing expert assistance for security patching, vulnerability management, and incident response.
Let's look at a few additional points. Open source versus proprietary. While open source operating systems offer transparency and community backing, some proprietary options like Red Hat Linux might provide specific security features or compliance certifications relevant to your environment.
Customization options. Choose an OS that allows for configuration to your specific security needs. For example, disabling unnecessary services and hardening network parameters can further enhance security.
Ultimately, the best server OS for FlowEyes depends on your specific security requirements, resource constraints, and operational preferences. Carefully evaluate the options and tailor your choice to create a secure and reliable foundation for your FlowEyes deployment.
Now let's look at firewall configurations. Ports used by FlowEyes. By default, both the web console and APIs use port 3000. This can be changed, but it affects both services simultaneously, as they cannot be configured to use separate ports without custom coding.
Identify required access. Carefully determine which users or systems need to access FlowEyes' web console versus those that only require API connectivity.
When configuring firewall rules, allow inbound traffic on port 3000 only from authorized IP addresses or subnets that require access to either the web console or APIs.
Block all other inbound traffic to port 3000 to prevent unauthorized access.
If using a cloud-based firewall, configure security groups or network ACLs accordingly.
If using FlowEyes solely as a backend with API connections, consider the following web console exposure mitigation strategies.
Restrict web console access. Implement firewall rules to allow web console access only from specific trusted IP addresses or networks.
Enforce strong authentication. Require multi-factor authentication for FlowEyes server or web server utilized for users to access FlowEyes web console.
Regularly review logs. Monitor FlowEyes logs for unusual activity and potential unauthorized access attempts.
Explore custom coding if feasible. Since FlowEyes is distributed under Apache 2.0 license, consider custom coding FlowEyes to separate web console and API ports for more granular control. It may also be possible to add code that implements multi-user management with compliant authentication methods.
Let's look at some additional recommendations. Disable unused APIs. If specific FlowEyes APIs are not required, disable them to reduce the attack surface within the codebase.
Implement a web application firewall. Protect against web-based attacks by deploying a WAF in front of FlowEyes.
Regularly review and update firewall rules. As FlowEyes usage evolves and security threats evolve, maintain the effectiveness of firewall rules through regular review and updates.
Remember, consult FlowEyes documentation for accurate port information and specific configuration recommendations.
Align firewall rules with your organization's security policies and risk tolerance, and prioritize security measures that address the unique challenges posed by FlowEyes' combined web console and API port usage.
Let's take a look at authentication and authorization in FlowEyes. Built-in mechanism limitations. FlowEyes currently lacks built-in support for multi-user management or integration with external authentication providers like LDAP, SAML, or OAuth 2.0.
The default password setting for web console access has security concerns as it's stored in application code.
Let's look at some recommended strategies. Server-level authentication.
Prioritize server access control. Since FlowEyes doesn't have native multi-user authentication, focus on securing access to the server where FlowEyes is hosted.
Dedicated FlowEyes web console box. If there are concerns with allowing the FlowEyes user to directly access the FlowEyes server and code, set up a dedicated server for the user to open a web browser and access the FlowEyes console.
Be sure to configure the server to restrict access to only required users, and to configure firewall and routing rules to ensure FlowEyes only connects to the web console server.
Restrict server access. Allow only authorized individuals to log into the server using secure authentication methods such as LDAP, NTLM, or other organization-specific methods.
And enforce strong password policies. Mandate strong passwords for server accounts and implement multi-factor authentication if possible.
If using FlowEyes' APIs for external applications, implement the option to generate and manage API keys to securely authenticate and authorize client applications.
Let's look at some additional security measures. Session handling. FlowEyes does not provide an option to set web console users' session timeout. It may be possible, though, to add custom code to FlowEyes to enforce session management.
If building a front-end wrapper for FlowEyes, be sure to include session management features if possible.
Access logging. Log all access attempts for auditing and intrusion detection.
Let's look at some custom coding considerations. Explore custom authentication. If custom coding FlowEyes is an option for you, consider integrating external authentication providers to enable multi-user management and more robust authentication methods.
Rapid. It is possible to build a custom front-end web application, wrapper, that utilizes FlowEyes modules via API connections, as FlowEyes provides the code required for utilization with common platforms like Node.js and Python. This custom front-end could then implement multi-user management and custom authentication methods such as LDAP, SAML, or OAuth.
Remember, Prioritize server-level authentication to protect FlowEye's access.
Implement appropriate API authentication methods if applicable.
Consider custom coding for enhanced authentication capabilities if feasible.
And regularly review and update access control policies.
By understanding these limitations and adopting appropriate strategies, you can establish a reasonable level of security for FlowEye's access, despite the lack of built-in multi-user authentication.
Let's look at encryption considerations for FlowEye's built-in encryption. FlowEye's offers encryption for API keys and secrets at rest, but it has limitations.
Key storage. Encryption keys are stored within the FlowEye's application, potentially posing risks if the application is compromised.
Key vault integration. There's no built-in support for integration with external key vaults for centralized key management.
Let's look at some recommendations. Enable built-in encryption. While not ideal, enable FlowEye's built-in encryption as a basic level of protection for sensitive data.
Custom coding for key vault integration. If possible, consider custom coding FlowEye's to integrate with your organization's key vault solution. This enables secure storage of encryption keys outside of FlowEye's, reducing the risk of exposure in a compromise.
Restrict access. Minimize the number of individuals with access to FlowEye's configuration and secret storage.
Regularly rotate keys. Frequently rotate encryption keys to minimize potential damage from a breach.
Consider server-level encryption. If applicable, explore encrypting the entire server or disk where FlowEye's resides for an additional layer of protection.
Let's look at API keys and database connections.
API keys. Store API keys for hosted LLMs, tools, and other services securely within FlowEye's using its encryption feature. If custom coding is possible, integrate with a key vault for enhanced security.
Database connections. When connecting to local or hosted databases, use secure connection methods such as TLS and store database credentials securely within FlowEye's or, ideally, in a key vault if feasible.
Remember, be aware of FlowEye's encryption limitations and explore custom coding or alternative mitigations as needed.
Prioritize secure storage and management of API keys and database credentials.
And regularly review and update encryption practices in line with security best practices and evolving threats.
By understanding these constraints and implementing appropriate measures, you can enhance the security of sensitive data and secrets within your FlowEye's environment, even without full-fledged key vault integration.
In the vibrant world of FlowEye's, where language reigns supreme, another crucial element plays a vital role: security. Protecting this linguistic powerhouse requires constant vigilance, especially against lurking vulnerabilities within FlowEye's itself and its supporting systems.
Enter the knight in shining armor of vulnerability management, a proactive approach to identifying and swiftly patching security weaknesses before they evolve into formidable threats.
Imagine this: a tiny gap in your FlowEye's server's OS, barely a whisper in the digital realm, becomes a gaping hole for adversaries to exploit. Sensitive data could be pilfered, systems manipulated, and your entire workflow thrown into chaos.
Vulnerability management shines a light on these hidden crevices, empowering you to patch them before they become open doors.
Think of vulnerability scanning as a linguistic detective scanning the code, searching for anomalies, inconsistencies, and known security flaws. Vulnerability scanners tirelessly explore the FlowEye server and its underlying systems, sniffing out potential weak spots before they blossom into full-blown vulnerabilities.
Regularly scheduled scans, think monthly or even weekly, ensure you stay ahead of the curve.
Once vulnerabilities are identified, it's time for the cavalry to arrive: patches. These software updates act as linguistic bandages, seamlessly sealing the identified gaps and strengthening your digital defenses.
Make patching a priority, ensuring you promptly apply available updates for the FlowEye's server, its supporting systems, FlowEye's application code, and all its supporting libraries.
Remember, FlowEye's doesn't exist in a vacuum. It thrives in an ecosystem of servers, databases, and other tools. Vulnerability management extends beyond FlowEye's itself, encompassing every corner of your infrastructure.
Scan diligently, patch swiftly, and leave no stone unturned in your quest for a secure environment.
Let's look at some additional considerations. Stay informed. Regularly update your knowledge about FlowEye's vulnerabilities through official sources and security advisories.
Prioritize critical risks. Not all vulnerabilities are created equal. Prioritize patching critical vulnerabilities first, mitigating the most immediate threats.
Automation is your friend. Consider automated vulnerability scanning and patching tools to streamline your security processes.
And continuous monitoring. The quest for security is never-ending. Continuously monitor your systems for suspicious activity and emergent vulnerabilities.
By embracing vulnerability management, you transform FlowEyes from a potential target into a secure fortress. Regular scans, prompt patching, and a holistic approach towards your entire infrastructure become your weapons against digital adversaries.
Remember, in the battle for security, vigilance is your shield and vulnerability management your sword. Strike true, and let FlowEyes flourish under the watchful gaze of proactive security.
FlowEyes chains aren't picky eaters. They can devour a delectable buffet of data types, from text and code to spreadsheets and tables.
But when it comes to sensitive data, the feast requires careful handling to ensure delicious security. Let's dive into the world of data types and explore best practices for managing sensitive information within vector databases.
Data types at the FlowEyes table: text, FlowEyes' connected large language models bread and butter, emails, documents, code, you name it. FlowEyes model chains can analyze and understand the linguistic nuances within.
Structured data, tables, spreadsheets, and databases holding numbers, dates, and facts. FlowEyes LLM chains can extract insights and build relationships to unlock hidden patterns.
Semi-structured data: JSON, XML, and other formats blending text and structure. FlowEyes provides tools that navigates these hybrid landscapes with ease, extracting valuable information.
Not all data is meant for public consumption. Some information is like the secret recipe for your grandma's pie, precious and deserving of extra protection. Here's how to manage sensitive data within vector databases responsibly.
Identify and classify. Recognize which data needs special care: customer information, financial records, internal documents. Classify them based on their sensitivity level.
Minimize exposure. Avoid storing unnecessary sensitive data. Only process and store what's absolutely essential for your tasks.
Access control. Don't let everyone peek into the kitchen. Implement granular access controls to restrict who can access and manipulate sensitive data within FlowEyes chain components, such as databases and buffer caches.
Encryption. Double lock the pantry. Encrypt sensitive data both at rest and in transit, moving between systems.
Monitoring and logging. Keep a watchful eye on the data flow. Monitor activity and log access attempts to detect and respond to potential security incidents.
Data lifecycle management. Sensitive data eventually goes stale. Establish a secure deletion or disposal process to prevent lingering vulnerabilities.
Remember, diverse data types may be processed through FlowEyes chains, so treat sensitive information with extra care.
Implement a multi-layered approach to secure sensitive data. Identification, minimization, access control, encryption, monitoring, and lifecycle management.
By prioritizing data security, you ensure FlowEyes large language model chains continue to be a reliable tool for both linguistic exploration and secure information handling.
The data FlowEyes chain components ingest isn't just fuel for the engine, it's a precious resource demanding responsible handling. From the initial storage to the final send-off, every step in the data journey requires careful consideration to ensure security, privacy, and compliance.
So let's dig into best practices for data handling within vector databases and buffer cache databases used within your FlowEyes model chains.
Data storage, secure locations, store data in secure environments like encrypted servers or cloud storage solutions with strong access controls.
Minimize retention. Keep sensitive data only as long as necessary for your intended purpose. Implement data retention policies and adhere to relevant regulations.
Use dedicated vector databases. For optimal security of sensitive data in vector format, use a dedicated vector database for storing such data. Depending on the type of vector database implemented, be sure to implement proper encryption configurations.
Encryption. Scramble data using cryptographic techniques, rendering it unreadable without the decryption key. This is ideal for highly sensitive data.
If using tools to convert existing databases, such as PostgreSQL or SQL, be careful about implementing column-level encryption for the vectors, as this may cause significant performance issues, especially with large amounts of data. Backups with caution. Securely backup data, but remember, backups can also become targets. Encrypt backups and store them separately from the primary data location.
Let's look at data transfer. Encrypted channels encrypt data in transit whenever it's moved between systems, whether within your network or over the internet. Use secure protocols like TLS.
Minimize exposure. Limit the number of times data is transferred and copied to other systems. Direct transfers between the FlowEyes server, vector database, and buffer memory systems are preferable to multiple hops and intermediaries.
Data disposal. Secure deletion. Don't let sensitive data linger like unwanted leftovers. Implement secure deletion methods that overwrite or destroy data beyond recovery.
Compliance considerations. Adhere to data privacy regulations for disposal, such as GDPR's right to be forgotten. Ensure you have documented evidence of secure deletion.
Let's look at some additional guidelines. Data minimization. Collect and process only the data necessary for your specific tasks. Avoid unnecessary data collection that increases your vulnerability.
Pseudonymization and anonymization. Consider anonymizing or pseudonymizing data when possible to further protect privacy while still enabling analysis.
And regular reviews and audits. Regularly assess your data handling practices and conduct audits to identify and address potential vulnerabilities.
Remember, data handling is a shared responsibility. All users and administrators involved with FlowEyes and chain components must be aware of and adhere to data security and privacy best practices.
Stay informed about evolving data privacy regulations and adapt your practices accordingly. By becoming a responsible data steward, you empower FlowEyes to be a secure and trustworthy tool for your linguistic endeavors.
Let's look into data anonymization, not for all data. Anonymization isn't a one-size-fits-all cloak. It's best suited for scenarios where you need to analyze data patterns and trends without revealing individual identities or sensitive details.
FlowEyes' role. While FlowEyes doesn't have tools for anonymization capabilities, you can leverage external tools or custom scripts to anonymize data before feeding it into a FlowEyes chain for processing.
Generalization. Replace specific values with broader categories. For example, instead of exact birth dates, use age ranges instead.
Masking. Conceal sensitive information with fixed characters or symbols.
Pseudonymization. Replace identifiable information with artificial identifiers, pseudonyms. This preserves relationships within the data while protecting identities.
Differential privacy. Add controlled noise to data to obscure individual contributions while maintaining overall statistical accuracy.
Let's look at some considerations for FlowEyes. External tools. Choose anonymization tools that integrate well with FlowEyes' components, input formats, and data types.
Custom scripts. If you have programming expertise, create custom scripts to anonymize data specifically for FlowEyes' use cases.
Impact on analysis. Assess how anonymization techniques might affect the quality of analysis results. Some techniques, like generalization, can reduce data granularity.
Re-identification risks. Be mindful that even anonymized data might be re-identified if combined with other datasets or background knowledge. Evaluate the potential risks and implement additional safeguards if necessary.
Remember, anonymization is a valuable tool for enhancing privacy, but it's not a foolproof guarantee of anonymity.
Choose techniques carefully based on data sensitivity, analysis needs, and re-identification risks.
And regularly review and update anonymization practices to stay aligned with evolving privacy regulations and best practices.
Let's look at bridging the linguistic and vector worlds. Partnership for power. FlowEyes' chains models, linguistic prowess, and vector databases' ability to store and retrieve high-dimensional data form a formidable alliance.
Seamlessly expand capabilities. Connecting FlowEyes to vector databases unlocks new possibilities for similarity searches, recommendations, and other tasks that benefit from vector representations. Talk to your data.
Let's look at some popular hosted vector databases.
Pinecone, a cloud-based vector database offering fast and scalable vector search and similarity capabilities.
Relevance AI, a comprehensive platform for building vector-based AI applications, including a hosted vector database, vector search, and machine learning tools.
Milvus, an open-source vector database with both hosted and self-managed options known for speed and flexibility.
Amazon Elasticsearch Service with KNN provides nearest neighbor search capabilities for vector data within the Amazon Elasticsearch service.
Weaviate, a cloud-native vector database with semantic capabilities, enabling knowledge graph-like features.
Pilosa, a cloud-native vector database optimized for speed and scalability, particularly for large-scale vector workloads. Let's take a look at some self-managed vector databases. Milvus can be deployed on your own infrastructure for full control and customization.
FICE, an open-source library for efficient similarity search and clustering of dense vectors, often used as the foundation for self-managed vector databases.
NVIDIA Merlin, a framework for building vector databases and recommendation systems, leveraging GPU acceleration for high-performance vector operations.
Let's look at some key considerations for choosing a vector database. Hosted versus self-managed. Evaluate your need for control and flexibility versus ease of use and maintenance.
Performance and scalability. Consider the volume of data and expected query load to ensure the database can handle your requirements.
Features and functionality. Assess the specific vector operations and search capabilities you need, as well as any additional features like semantic search or knowledge graph integration.
And cost. Compare pricing models for hosted options and factor in infrastructure costs for self-managed solutions.
Let's look at integrating vector databases with FlowEyes. Existing FlowEyes Vector Database Connection tool. Check FlowEyes Vector Database Connectors options before choosing a vector database if you want the convenience of using a pre-configured connection tool.
Custom FlowEyes tool. FlowEyes does provide the option to create a custom tool, which makes it possible to connect to vector databases that do not already have an existing tool.
Implement namespaces. Consider utilizing the namespaces option within the additional configurations option available in the FlowEyes tool. This tool allows segregation of data between multiple FlowEyes connections user sharing the same vector database.
Let's look at a real-world use case. Secure connections with Pinecone.
Authentication. API key. Obtain a unique API key from Pinecone's console and store it securely within FlowEyes' configuration. And regularly rotate API keys to minimize exposure in case of a breach.
Built-in encryption. Pinecone encrypts data at rest and in transit, safeguarding sensitive information.
Use HTTPS for all communication between FlowEyes and Pinecone.
Restrict access to Pinecone's API endpoint to authorized users and systems, and implement firewalls and intrusion detection systems to monitor network traffic.
Define granular access permissions within Pinecone to control who can access and modify data.
Log all access attempts and operations within Pinecone for auditing and security analysis, and monitor for unusual activity or potential attacks.
Remember, treat API keys like sensitive passwords and protect them accordingly.
Encryption is crucial for protecting data in transit and at rest.
Implement a layered security approach to defend against potential threats.
And regularly review and update security measures to stay ahead of evolving risks.
By following these guidelines, you can establish a secure and productive connection between FlowEyes and Pinecone, enabling powerful linguistic and vector-based applications while safeguarding sensitive data throughout its journey.
Are you looking to integrate a local large language model with FlowEyes? Let's look at setting up a local large language model server with a focus on security.
Let's look at choosing your model. Open-source large language models. Consider models like GPT-J, BERT, or Jurassic 1 Jumbo for flexibility and customization.
Vendor-provided large language models. If you have access to a commercial model, follow their specific setup instructions.
Server environment, hardware. Select a server with sufficient CPU, GPU, and memory resources.
Operating system. Choose a compatible OS such as Linux or Windows and ensure it's up to date with security patches. While many models will run on Windows, most models will perform better on Linux.
Containerization. Consider using Docker or other containerization technologies for easier deployment and isolation.
Installation. Follow model-specific instructions. Install the chosen model and its dependencies according to the official documentation.
Configuration. Access controls. Restrict access to the server and large language model endpoint to authorized users and systems using firewalls and authentication mechanisms.
Connections. Encrypt data in transit, including to vector databases.
Logging. Configure detailed logging to track access, usage, and potential anomalies.
Integrations with FlowEyes. Configuration. Update FlowEyes' settings to point to the local model server's endpoint.
Authentication. Provide any necessary credentials for accessing the LLM server if applicable.
Testing and monitoring. Thorough testing. Verify that FlowEyes can successfully communicate with the local model and generate responses.
Monitor performance and security. Regularly monitor server logs, resource usage, and security events to detect any issues or potential attacks.
Let's look at some additional security considerations. Stay up to date. Keep the model, server software, and FlowEyes application updated with the latest security patches.
Regular security audits. Conduct periodic reviews of security configurations and practices to identify and address vulnerabilities.
Vulnerability scanning. Use vulnerability scanning tools to proactively detect potential weaknesses in the large language model server and FlowEyes environment.
Threat detection. Implement intrusion detection and prevention systems to monitor for malicious activity.
Remember, prioritize security throughout the setup and integration process.
Balance security measures with performance and usability needs.
And regularly review and update security practices to adapt to evolving threats.
By following these guidelines and prioritizing security, you can establish a robust and secure local large language model environment for your FlowEyes workflows, enabling powerful linguistic capabilities while protecting sensitive data and systems.
While the convenience of hosted local large models beckons, diving in without consideration can leave your data and security vulnerable.
So before stepping through the portal, let's illuminate the critical aspects of hosted large language model security.
Let's look at data privacy. Know your data flow. Understand what data you're sending to the hosted model and whether it remains there or is analyzed on their servers.
Encryption. Ensure data is encrypted in transit and at rest, minimizing vulnerability during exchange and storage.
Data retention. Ask about the vendor's data retention policies and ensure they align with your privacy needs and regulations.
Opt-out mechanisms. Verify if the vendor offers options to control data usage and removal upon request.
Let's take a look at vendor trustworthiness, reputation, and track record. Research the vendor's history of data breaches, security incidents, and adherence to privacy regulations.
Security infrastructure. Investigate their security practices, certifications, and compliance with relevant standards such as GDPR or HIPAA.
Transparency and reporting. Assess their level of transparency regarding data handling, security incidents, and vulnerability disclosures.
Compliance considerations. Applicable regulations. Identify relevant data privacy regulations such as GDPR or CCPA and ensure the vendor complies with their requirements.
Data location. Understand where the model servers are located and ensure data residency aligns with your compliance needs.
Data breaches and notification. Be aware of the vendor's data breach notification policies and their responsiveness in such situations.
Secure integration with FlowEyes. Authentication and authorization. Implement strong authentication and authorization mechanisms for accessing the hosted model from FlowEyes.
Data minimization. Only send the necessary data to the hosted model, minimizing the scope of potential exposure.
Logging and monitoring. Monitor communication between FlowEyes and the hosted model and log access attempts and suspicious activity.
Remember, hosted large language models trade convenience for data sovereignty. Be mindful of the trade-offs and prioritize security best practices.
Scrutinize vendors carefully and demand transparency and accountability regarding data handling and security.
Don't assume compliance. Actively verify the vendor's adherence to relevant regulations.
And securely integrate FlowEyes with the hosted model, minimizing data exposure and maintaining vigilance.
By navigating the labyrinth of hosted large language models with a keen eye on security, you can leverage their power without compromising your data privacy and compliance.
In the ever-shifting landscape of security, proactively detecting and mitigating threats is key. That's where threat modeling shines, a powerful tool to identify potential vulnerabilities and chart a course towards a secure FlowEyes environment. So let's navigate the treacherous waters of potential threats and emerge victorious with robust defenses.
Define the scope, identify assets, clearly define what needs protection, FlowEyes itself, data it handles, user accounts, integrations, etc.
Threat actors. Consider potential adversaries, hackers, malicious insiders, competitors.
Attack goals. Understand their motivation, data theft, system disruption, financial gain, etc.
Identify threats, data threats. Uncover risks like data breaches, unauthorized access, manipulation, leakage, etc.
System threats. Explore vulnerabilities in FlowEyes itself, underlying systems, infrastructure, APIs, etc.
User threats. Consider malicious insider activity, compromised accounts, social engineering attacks, etc.
Assess impact and likelihood. Evaluate the severity of each potential threat's impact on your assets and objectives, and predict the likelihood of each threat occurring based on your specific context and security posture.
Prioritize and mitigate. Focus on high-impact and high-likelihood threats first. Implement appropriate mitigation strategies for each identified threat, such as access controls and authentication. Strengthen who can access FlowEyes and its data.
Encryption. Protect data at rest and in transit.
Vulnerability management. Regularly patch vulnerabilities in FlowEyes and underlying systems.
Logging and monitoring. Track activity and detect suspicious behavior.
Incident response planning. Prepare for and respond effectively to security incidents.
Iterate and adapt. Threat modeling is not a one-time exercise. Regularly revisit and update your analysis as FlowEyes evolves, threats change, and new vulnerabilities emerge.
Share knowledge and findings with your team to increase collective awareness and strengthen your security posture.
Remember, threat modeling is a vital tool for proactive security, not a guarantee of perfect security. Prioritize high-impact threats and implement realistic mitigation strategies based on your resources and context.
Continuous improvement is key. Regularly update your threat model and adapt your defenses to stay ahead of evolving threats. By charting the course through threat modeling, you empower FlowEyes to navigate the turbulent waters of potential security risks and sail towards a secure and resilient future.
In the realm of digital security, shadows can harbor unseen threats. But fear not, for the vigilant eyes of logging and monitoring shine a brilliant light upon FlowEyes' activities, revealing every whisper and footstep within its domain. By harnessing the power of these tools, you can transform FlowEyes from a potential target into a fortress of digital awareness.
Unveiling the importance, auditing and accountability. Every action within FlowEyes, from user logins to API calls to data manipulations, is meticulously recorded in logs. This creates a historical narrative, enabling you to track who did what, when, and where, ensuring accountability and deterring malicious activity.
Intrusion detection and response. Logs act as tripwires, alerting you to suspicious behavior like unauthorized access attempts, unexpected data modifications, or anomalous system activity. By monitoring these logs vigilantly, you can swiftly detect and respond to potential intrusions before they escalate into full-blown breaches.
Performance optimization. Logs act as a mirror reflecting FlowEyes' inner workings. Analyzing these logs can reveal performance bottlenecks, resource usage patterns, and areas for optimization, ensuring FlowEyes runs smoothly and efficiently.
Let's look at crafting a powerful logging strategy. Log everything. Capture a comprehensive view of FlowEyes' activity, including user actions, system events, API calls, and vector database data changes.
Centralized storage. Establish a secure and centralized repository for all logs, ensuring easy access and analysis.
Log levels and granularity. Customize log levels to capture essential details while minimizing noise, and consider granular options for specific areas of interest.
Alerting and notification. Set up automated alerts for critical events and suspicious activity, ensuring timely notifications for prompt response.
Let's look beyond the logs to the power of monitoring. Real-time visibility. Go beyond historical records with real-time monitoring tools that provide a live dashboard of FlowEyes servers, vector databases, and supporting systems, such as firewalls, routers, etc. Current activity.
Correlating events. Don't analyze logs in isolation. Utilize tools that can correlate events across different logs, revealing patterns and potential threats that individual logs might miss.
And threat intelligence integration. Incorporate threat intelligence feeds into your monitoring system to stay ahead of emerging threats and tailor your defenses accordingly.
Remember, logging and monitoring are not merely passive observers. They are active defenders safeguarding your FlowEyes environment. Design your logging and monitoring strategy with careful consideration, tailoring it to your specific needs and threat landscape.
Utilize automated tools and advanced techniques to maximize the efficacy of your monitoring efforts. By embracing the power of logging and monitoring, you illuminate the shadows within FlowEyes, transforming it into a bastion of security and transparency.
And finally, let's discuss unveiling vulnerabilities and validating security controls through rigorous security testing.
The essential forge, proactive defense. Security testing isn't about waiting for breaches to happen, it's about proactively seeking weaknesses before adversaries exploit them.
Continuous improvement. Security is a journey, not a destination. Regular testing ensures your defenses evolve alongside evolving threats.
Validation and confidence. Testing validates the effectiveness of your security controls, instilling confidence in FlowEye's resilience.
Testing strategies for a secure FlowEye. Penetration testing. Simulate real-world attacks to uncover vulnerabilities in FlowEye's applications, systems, and networks.
Vulnerability scanning. Use automated tools to scan for known vulnerabilities in FlowEye, its components, and underlying systems.
Configuration review. Assess the security settings of FlowEye and its components for potential misconfigurations or weaknesses.
Code review. For custom code or integrations, examine the code for security flaws and vulnerabilities.
API security testing. Specifically target FlowEye's APIs to uncover vulnerabilities in authentication, authorization, data handling, and input validation.
Regular testing. Conduct security testing on a regular basis, not just as a one-time event.
Prioritize high-risk areas. Focus testing efforts on areas most likely to be targeted or critical to your operations.
Remediate findings promptly. Address identified vulnerabilities with urgency to minimize risks.
And document and track. Maintain detailed records of testing results, remediation actions, and progress over time.
Remember, security testing is a vital component of a comprehensive security strategy.
Tailor testing approaches to your specific FlowEye setup and threat landscape.
Engage experienced professionals for complex testing scenarios.
Promptly address identified vulnerabilities to maintain a secure environment.
By embracing security testing, you forge a FlowEye environment that not only empowers innovation, but stands resilient against the ever-evolving tide of threats. The path to security is paved with vigilance and continuous improvement.
This is the end of Section 9, Security Considerations for Integrating FlowEye. This is Section 10, Architectural and Application Security Considerations for Integrating Large Language Model Chains with Web Applications.
Large language model integration with web applications requires a layered approach to security, addressing both architectural and application-level vulnerabilities. By prioritizing security throughout the design, development, and deployment process, you can unlock the power of large language models while safeguarding your users and data.
Let's look at some common web application architectures for implementing large language models and model APIs.
Simple architecture, front-end and large language model combined on a web server. Structure. Front-end code, such as HTML, CSS, and JavaScript, and model logic, reside within the same codebase, typically hosted on a single web server, and may interact with back-end components like vector databases or local models for specific tasks.
Key features. Simple setup and deployment. Suitable for smaller applications with less complex model interactions, and potential performance benefits due to co-location of front-end and large language model.
Considerations: limited scalability and maintainability as the application grows, potential security risks if model logic is not properly isolated, and may not be suitable for large-scale or resource-intensive model tasks.
Let's look at decoupled architecture with a front-end, middle tier, and back-end.
Structure. Front-end, client-side, communicates with a separate middle tier, server-side, that handles model interactions and back-end data access. Front-end and middle tier can be developed independently, promoting modularity and scalability.
Key features: improve scalability and maintainability, enhance security by isolating model logic in the middle tier, facilitates more complex model chains and workflows, and enables integration with various back-end systems such as databases, storage, and external services.
Considerations: increased complexity in development, testing, and deployment. Potential performance overhead due to network communication between tiers. Common middle-tier implementation options.
Custom code such as Python and Node.js. Full control over model integration and logic. Flexibility to use various large language model libraries and APIs, and requires expertise in chosen programming language and large language model frameworks.
Large language model-specific frameworks, streamlined large language model integration with pre-built components and workflows, may offer optimizations for specific model providers or tasks. Examples: LangChain, Hugging Face Transformers, and OpenAI API.
Serverless functions. Event-driven execution of model code in response to user actions or triggers. cost-effective scaling and resource management. Examples: AWS Lambda, Google Cloud Functions, and Azure Functions.
Back-end components, vector databases, efficient storage and retrieval of large language model-generated text embeddings. Enable fast similarity searches and semantic understanding. Examples: Pinecone, Weaviate, and FICE.
Local large language models. On-premise large language model deployment for privacy, control, or performance reasons, and requires hardware resources and expertise in large language model deployment and management.
Choosing the right architecture. Consider application complexity, scalability needs, security requirements, team expertise, and available resources.
Simple architecture might suffice for smaller projects with basic large language model interactions.
Decoupled architecture offers better scalability, security, and flexibility for larger or more complex large language model-powered applications.
Remember, carefully evaluate trade-offs between simplicity, control, scalability, security, and performance when selecting an architecture.
Consider future growth and potential large language model integration expansion.
Implement robust security measures, especially when handling sensitive data or user-generated content.
And monitor performance and resource usage, optimizing for efficiency and cost-effectiveness.
Let's take a deep dive into enhancing existing microservices. Natural language processing enrichment.
Sentiment analysis. Use case. Analyze customer reviews or social media mentions to understand sentiment and gauge brand perception within a customer service microservice.
Large language model integration. Use large language models like ChatGPT to classify text as positive, negative, or neutral, providing insights for customer engagement strategies.
Entity extraction. Use case. Extract key information like names, locations, or dates from financial documents within a payment processing microservice.
Large language model integration. Utilize models like Lambda or Jurassic 1 Jumbo to identify and extract relevant entities for efficient data processing and analysis.
Use case. Generate concise summaries of lengthy legal documents or product descriptions within a content management microservice.
Large language model integration. Leverage large language models like T5 or Gemini to condense information while preserving key points, improving user experience and accessibility.
Question answering. Use case. Build a FAQ chatbot within a customer support microservice powered by large language models.
Large language model integration. Utilize models like Megatron Turing NLG or Wudao 2.0 to extract answers from relevant knowledge bases and provide accurate, context-aware responses to user queries.
Let's look at real-time personalization. Recommendation engines.
Use case. Generate personalized product recommendations in an e-commerce microservice based on user browsing history and purchase patterns.
Large language model integration. Leverage models like Bloom or Palm to analyze user data and recommend products tailored to their individual preferences and past behavior.
Dynamic content generation. Use case. Tailor website landing pages or marketing materials within a content delivery microservice based on user demographics and interests.
Large language models integration. Utilize models like Jurassic 1 Jumbo or GPT-Neo to personalize content by adjusting tone, style, and information based on user profiles.
Adaptive user interfaces. Use case. Modify the layout and functionality of a dashboard within a user management microservice based on individual roles and preferences.
Large language model integration. Leverage models like Megatron Turing NLG or Wudao 2.0 to analyze user interactions and dynamically adjust UI elements for a more intuitive and personalized experience.
Let's look at fraud detection and anomaly analysis, behavioral pattern recognition.
Use case. Identify suspicious user behavior, like unusual login attempts or inconsistent transaction patterns within a security microservice.
Large language model integration. Utilize models like Lambda or Jurassic 1 Jumbo to analyze user activity and detect potential fraudsters based on deviations from established behavioral patterns.
Anomaly detection in data streams. Use case. Monitor financial transactions or network traffic within a security monitoring microservice for anomalies that might indicate fraudulent activity.
Large language model integration. Leverage models like T5 or Gemini to analyze real-time data streams and identify outliers or deviations from expected patterns, triggering investigation and mitigation efforts.
Let's look at bridging microservices and large language models with a deep dive into integration methods.
LangChain with Python. unleashing large language model power in Python microservices. LangChain's intuitive Python APIs seamlessly interact with various large language models within microservices.
Key advantages: streamlined integration within Python-based microservices, access to diverse model capabilities through a unified interface, and ability to chain multiple models for complex tasks.
Let's look at RESTful APIs and messaging systems, asynchronous communication for scalability, RESTful calls, direct HTTP requests to large language model API endpoints for synchronous responses.
Message queues deposit tasks for large language model processing asynchronously, decoupling microservices and enhancing scalability.
Example with RabbitMQ. Microservice publishes a message containing text for summarization to a RabbitMQ queue. A large language model consumer service retrieves the message, processes it using a model API, and publishes the summary back to a results queue. And then the original microservice consumes the summary from the results queue.
And let's look at containerization and orchestration. Managing large language models at scale. Containerization tools like Docker and orchestration platforms like Kubernetes can simplify deployment, scaling, and management of models within microservices architecture.
Packaging large language models. Containerize large language models as independent services for easy deployment and resource isolation.
Orchestrating large language models. Kubernetes manages model containers across multiple nodes, ensuring availability, load balancing, and resource optimization.
Example: deploy a large language model as a Docker container on a Kubernetes cluster. Microservices can seamlessly communicate with the model via Kubernetes service discovery and load balancing.
Let's take a look at serverless functions and large language models. Trigger-based model interactions.
Use case: build a customer service chatbot that leverages large language models to understand user queries, generate contextual responses, and personalize interactions.
Trigger. User messages or specific keywords trigger a serverless function that interacts with a large language model API to generate a suitable response.
Example: upon receiving "What's your return policy?" the function sends the query to a large language model like Gemini, receives a tailored response, and delivers it to the user.
Automated content generation. Use case: dynamically generate personalized product descriptions based on user preferences or real-time market trends.
Trigger. A product purchase or a scheduled update might trigger a serverless function to analyze user data or market information using a large language model and generate unique descriptions.
Example: after buying a running watch, the user receives a personalized training plan generated by a large language model based on their fitness goals and preferences.
Real-time data analysis and insights. Use case: analyze social media sentiment towards a new product launch in real time to trigger marketing adjustments or inform product development.
Trigger. New social media mentions containing the product name trigger a serverless function to send them to a large language model for sentiment analysis, generating actionable insights based on the results.
Example: a spike in negative sentiment prompts the function to send an alert to the marketing team to address potential concerns.
Integration with serverless platforms. AWS Lambda offers pre-built connectors for large language models like Amazon Comprehend and integrates seamlessly with popular API Gateway.
Google Cloud Functions provides libraries for large language model interaction like Google Natural Language API and supports custom API integration for greater flexibility.
Azure Functions enables trigger-based large language model interactions with services like Azure Cognitive Services and facilitates containerized deployments for complex pipelines.
Let's look at enhancing single-page applications with the power of large language models to boost user experience and engagement. Voice interfaces and natural language search.
Revolutionize user navigation. Integrate large language models like ChatGPT to enable natural language search within your single-page application. Users can ask questions, get direct answers, and navigate content hands-free.
Example: show me all cooking recipes with less than 10 ingredients.
Empower voice-based interactions. Utilize large language models like Jurassic 1 Jumbo or Megatron Turing NLG to build voice-activated features like product recommendations or task management within your spa.
Example: add buy flour to my shopping list.
Let's look at dynamic content generation and personalization. Tailor content to individual users. Leverage models like T5 or Gemini to analyze user data and preferences, dynamically generating personalized content like news feeds, product recommendations, or learning materials within your spa.
Example: a news app displays articles based on the user's reading history and interests.
Adaptive user interfaces. Utilize models like Lambda or Wudao 2.0 to personalize UI elements like layouts, functionalities, and language based on user profiles and interaction patterns.
Example: a dashboard adjusts its layout and data visualizations based on the user's role and preferences.
Let's discuss interactive AI assistants and chatbots. Context-aware, guidance and support. Embed AI assistants powered by large language models like Bloom or Palm to provide context-aware help and guidance within your spa. Users can ask questions, get feedback, and complete tasks effortlessly.
Example: an e-commerce chatbot helps users navigate product options, answer questions about specifications, and complete purchases seamlessly.
Automated tasks and proactive assistance. Utilize models like Jurassic 1 Jumbo or GPT Neo to automate repetitive tasks within your spa, like scheduling appointments or filling out forms, and proactively offer assistance based on user activity.
Example: an appointment booking app automatically fills out a user's information based on previous appointments and suggests available time slots.
Let's look at large language model integration with spa frameworks. Seamless integration with Bubble.io. Many software-as-a-service web application builders, like Bubble.io, offer pre-built plugins for popular large language models like Gemini and integrates with model APIs through APIs connector, simplifying implementation.
Custom code flexibility in frameworks like React or Vue.js. Frameworks like React and Vue.js offer flexibility for developers to integrate large language models using libraries like LangChain or directly through API calls.
We are now at the crossroads of choice between custom code versus SaaS web app builders for large language model integration.
Custom code. Power at your fingertips. Flex your coding muscles. With tools like LangChain and Python, custom code offers granular control over model integration, tailoring it to specific needs and workflows.
Build a bespoke experience. Craft unique functionalities and user experiences not limited to pre-built options, unleashing your creative vision.
Security in your grip. You hold the reins on security configurations, data handling practices, and vulnerability management, allowing for tighter control and potential customization.
Custom code considerations. The burden of responsibility. Custom code comes with greater responsibility for performance optimization, bug fixing, and ongoing maintenance.
Steeper learning curve. Mastering libraries and APIs requires deeper technical expertise and familiarity with large language model integration nuances.
Let's look at SaaS web app builders for speed and simplicity. Fast-track development. Platforms like Bubble.io provide readily available large language model plugins and workflows, accelerating integration and reducing development time.
Focus on the big picture. Concentrate on your core features and user experience, leaving infrastructure and security concerns to the platform.
Scale with ease. Enjoy built-in scaling capabilities and infrastructure management, facilitating easier growth and resource allocation.
When considering SaaS web app builders, keep in mind the following considerations. Limited flexibility. Pre-built functionalities may not perfectly align with your vision, potentially restricting customization options.
Vendor lock-in. Reliance on specific platforms can create dependencies and challenges later on if you seek to switch providers.
Security as a shared responsibility. While platforms handle core infrastructure, understanding their security practices and potential limitations is crucial.
The ideal approach depends on your specific needs, skills, and resources. Custom code shines when you have unique requirements and a dedicated development team with strong large language model expertise. It also allows you to prioritize granular control over security and data handling.
SaaS builders excel when rapid development and ease of use are paramount, or if you favor focusing on core functionality and user experience, relying on platform infrastructure and security.
Ultimately, the key is to understand the trade-offs and choose the path that empowers you to build the most effective and secure large language model-powered web application.
Remember, both approaches offer valuable advantages and challenges.
Analyze your project requirements, skill set, and resources carefully before making a decision.
And explore available custom code tools and SaaS platforms to find the best fit for your needs.
By equipping learners with this comprehensive understanding, you'll prepare them to make informed choices and navigate the exciting world of large language model integration with confidence.
Think of a monolithic application as a single castle. If its walls crumble, everything falls.
But with a microservices architecture, we construct a fortified city where each large language model is a sturdy tower within its own walls. This approach empowers us to secure your model chains with 4 key advantages.
Number 1. Limited attack surface. Each large language model service exposes a smaller attack surface compared to a monolithic application. Breaching one tower doesn't automatically give access to the entire city. This minimizes the potential damage a vulnerability can inflict.
2. Independent scalability. You can scale each model service independently based on its individual needs, maximizing resource utilization and avoiding bottlenecks. This enhances overall application performance and security by preventing overload at any single point.
3. Fault isolation. If one large language model tower succumbs to an error or outage, it doesn't bring down the entire city. Other services and the web application itself can continue functioning, minimizing disruptions and maintaining user experience.
And number 4, easier development and maintenance. Splitting models into separate services simplifies development and maintenance. Developers can focus on specific functionalities without worrying about the intricate workings of the entire system. This ultimately leads to more secure and robust large language model integrations.
Implementing a microservices architecture for large language model chains requires careful planning and execution. Here are some key considerations.
Granularity. Define appropriate boundaries for your large language model services based on functionality, complexity, and potential risks.
Communication. Establish secure communication channels between model services and the web application, utilizing strong authentication and authorization mechanisms.
Data management. Clearly define data ownership and access controls across large language model services to prevent unauthorized data exposure or manipulation.
Monitoring and logging. Implement robust monitoring and logging systems across the microservices landscape to detect suspicious activity and potential security incidents.
By embracing a microservices architecture and building secure city walls around your large language model chains, you can unlock their potential while maintaining a resilient and secure web application environment.
Remember, security is not a destination but a continuous journey. Embrace best practices, adapt to evolving threats, and keep building your secure large language model city brick by brick.
When integrating large language model chains with web applications, APIs serve as vital gateways, facilitating communication and data exchange.
But like any gateway, they can become targets for intrusion if not properly secured. Here's how to fortify the API gates and protect your model endpoints.
Authentication. Verify identity. Ensure only authorized users or applications can access large language model endpoints.
Implement methods like API keys, unique credentials for each application accessing the API.
User authentication. Require login credentials for user-specific access.
And token-based authentication. Use short-lived access tokens for secure sessions.
Let's look at authorization. Control access. Define what actions authorized users or applications can perform on large language model endpoints.
Implement mechanisms like role-based access control. Assign permissions based on user roles.
Attribute-based access control. Grant access based on attributes like user attributes, device information, or context.
Rate limiting. Prevent overload. Thwart denial of service attacks and excessive resource usage by setting limits on API request frequency.
Implement techniques like fixed window rate limiting. Allow a certain number of requests within a defined time period.
And leaky bucket algorithm. Smooth out traffic bursts by allowing a fixed number of requests per second.
Let's look at input validation. Sanitize data. Prevent injection attacks and ensure data integrity by rigorously validating all data sent to large language model endpoints.
This includes type checking to enforce expected data types.
Value range checking to ensure values fall within acceptable ranges.
and character escaping to prevent malicious code injection.
Let's look at encryption. Protect data in transit. Safeguard sensitive data exchanged between the web application and large language model endpoints using strong encryption protocols like TLS version 1.2 or higher.
And logging and monitoring. Detect suspicious activity. Track API calls, access attempts, and errors for anomaly detection and incident response. Use logging and monitoring tools to identify unauthorized access attempts, track API usage patterns, and detect potential vulnerabilities.
Remember, regularly review and update API security measures to address evolving threats.
Conduct thorough security testing of API endpoints to identify vulnerabilities.
Stay informed about best practices and emerging threats in API security.
By implementing these measures, you'll create a robust defense for your large language model endpoints, ensuring secure and controlled access, safeguarding sensitive data, and preventing abuse.
API security is an ongoing process, not a one-time task. Stay vigilant and continuously adapt your defenses to maintain a secure large language model integration.
When weaving large language model chains into web applications, safeguarding sensitive data becomes paramount. Here's how to build a fortress of protection around your sensitive assets.
Encryption, the guardian of data. Protect data in transit. Encrypt all sensitive data exchanged between the web application and model chain using HTTPS, TLS version 1.2 or higher, to shield it from prying eyes during transit.
Protect data at rest. Encrypt sensitive data stored within the model chain and the web application's databases to prevent unauthorized access in case of breaches.
Tokenization and pseudonymization for masking the true identity. Tokenization. Replace sensitive data with unique tokens that hold no inherent meaning, reducing the impact of potential breaches.
Pseudonymization. Replace identifying information with artificial identifiers, preserving some data utility while reducing direct identifiability.
Data minimization for less data and less risk. Collect and store only what's essential. Limit the amount of sensitive data collected and stored to minimize potential exposure in case of breaches.
Purge data when it's no longer needed. Proactively delete sensitive data that's no longer required for business purposes.
Access controls, the gatekeepers of data. Implement granular access controls. Restrict access to sensitive data within the model chain and web application to authorized users and processes based on their roles and legitimate needs.
Data auditing and logging for vigilant watch. Track data access and usage. Monitor who accesses sensitive data, when, and for what purpose to detect unauthorized access or suspicious activity.
And maintain detailed logs. Retain logs of data access and operations for investigation, compliance, and incident response.
Remember, data security is an ongoing process, not a one-time task. Regularly review and update your data protection measures to address evolving threats.
Stay informed about best practices and emerging threats in data security, and conduct regular security assessments and penetration testing to identify vulnerabilities in your LLM integration.
By implementing these measures, you'll construct a robust shield around your sensitive data, ensuring its confidentiality, integrity, and availability throughout the large language model integration journey.
Stay vigilant in your data protection efforts, and remember, even the most secure fortress requires ongoing maintenance and adaptation to face evolving threats.
Logging and monitoring are the vigilant watchdogs safeguarding your large language model integration. Let's explore how to equip them with powerful tools to sniff out suspicious activity and keep your digital fortress secure.
Cast a wide net with comprehensive logging. Log everything. Capture a comprehensive view of the large language model chain and web applications activities, including user actions, system events, API calls, data manipulations, and model outputs.
Centralized repository. Establish a secure and centralized repository for all logs, ensuring easy access and analysis.
Log levels and granularity. Customize log levels to capture essential details while minimizing noise, and consider granular options for specific areas of interest, like high-risk components or sensitive data access.
Maintain vigilant watch with real-time monitoring, beyond historical records. Go beyond historical records with real-time monitoring tools that provide a live dashboard of the model integration's current activity.
Correlating events. Don't analyze logs in isolation. Utilize tools that can correlate events across different logs, revealing patterns and potential threats that individual logs might miss.
Alerts and notifications. Set up automated alerts for critical events and suspicious activity like unauthorized access attempts, unexpected data modifications, or anomalous system behavior.
Focus on the shadows for threat detection and response. Integrate threat intelligence. Incorporate threat intelligence feeds into your monitoring system to stay ahead of emerging threats and tailor your defenses accordingly.
Incident response planning. Develop a comprehensive incident response plan outlining procedures for detecting, containing, and remediating security incidents involving the model chain and web application.
Regular review and adaptation. Regularly review your monitoring configuration and response plan to adapt to evolving threats and ensure continued effectiveness.
Remember, logging and monitoring are not merely passive observers. They are active defenders safeguarding your large language model integration.
Design your logging and monitoring strategy with careful consideration, tailoring it to your specific needs and threat landscape.
Leverage automated tools and advanced techniques to maximize the efficacy of your monitoring efforts, and integrate proactive threat detection and response to ensure swift and effective handling of security incidents.
By embracing robust logging and monitoring, you empower your large language model integration with the keen eyes and sharp instincts of a vigilant watchdog. Stay vigilant, keep the shadows illuminated, and ensure your large language model fortress remains secure against hidden threats.
When integrating large language model chains with web applications, treating all user input with suspicion is crucial.
It's like guarding the gates of your fortress against potential invaders. Here's how to rigorously sanitize and validate input to ensure a secure journey into the model.
Sanitize the impure by cleansing data before entry. Remove malicious characters. Strip out special characters or code snippets that could be used for injection attacks like SQL injection or cross-site scripting.
Encode special characters. Properly encode characters with special meaning in different contexts, such as HTML entities for web output.
Enforce data types. Ensure input adheres to expected data types such as numbers, text, and dates to prevent unexpected behavior or errors.
Apply input filters. Use libraries or frameworks designed for input validation and sanitization to streamline the process and benefit from built-in security measures.
Challenge every entry with comprehensive validation. Length restrictions. Enforce maximum lengths for input fields to prevent buffer overflow attacks and limit the potential surface for malicious code injection.
Value ranges. Ensure input values fall within acceptable ranges to prevent unexpected behavior or errors in downstream processes.
Regular expressions. Use regular expressions to match expected input patterns and reject invalid or potentially harmful data.
Whitelisting. Define a limited set of allowed characters or values, rejecting anything that falls outside the expected norms.
And blacklisting. Block known malicious patterns or keywords to prevent common attack vectors.
Validation as the final verdict. Server-side validation. Don't rely solely on client-side validation, which can be bypassed. Always perform thorough validation on the server before passing input to the model chain.
Error handling. Provide informative error messages to users when invalid input is detected, avoiding the exposure of sensitive system details.
Remember, input validation is a continuous process, not a one-time task. Regularly review and update your validation rules to address evolving threats and attack patterns.
Stay informed about common injection attack techniques and vulnerabilities, and conduct vulnerability scanning and penetration testing to identify potential weaknesses in your input validation processes.
By implementing robust input validation, you'll create a steadfast gatekeeper, ensuring only clean and safe data enters the model chain, protecting your web application and downstream processes from malicious manipulation.
Stay vigilant and maintain a critical eye on all incoming data to secure your large language model integration against potential attacks.
Now let's take a closer look at output validation. Identifying potential issues in large language model outputs.
Bias detection. Employ bias detection tools and techniques to identify potential biases in the model's outputs, ensuring fair and inclusive information. This could involve analyzing the training data, using fairness metrics, or employing adversarial attacks to expose potential biases.
Offensive content screening. Implement filters and algorithms to detect offensive, harmful, or discriminatory language in the model's outputs, protecting users from exposure to sensitive or inappropriate content. Consider using content moderation tools or sentiment analysis techniques.
Fact-checking and accuracy validation. Verify the factual accuracy of the model's outputs, especially when dealing with sensitive topics or claims. This could involve comparing outputs to reputable sources, employing data verification tools, or consulting human experts.
Techniques for output validation. Human-in-the-loop validation. Involve human reviewers to assess the model's outputs for bias, offense, and accuracy, especially for high-risk applications or sensitive content. Combine human expertise with the automation of tools for optimal results.
Explainable AI. Leverage XAI techniques to understand the reasoning behind the model's outputs, enabling human reviewers to better assess their reliability and identify potential biases or inaccuracies.
Post-processing techniques. Implement post-processing techniques like language smoothing or content filtering to refine the model's outputs, mitigating bias or offensive language while preserving intended meaning.
Build a safe haven by protecting users from untrusted outputs.
Clear warnings and disclaimers. If displaying unvalidated outputs is necessary, be transparent and inform users about their limitations and potential biases or inaccuracies.
User feedback and reporting. Provide mechanisms for users to report inappropriate or inaccurate outputs, allowing for continuous improvement and refinement of the validation process.
And regular monitoring and updating. Continuously monitor the performance of validation techniques and update them as necessary to adapt to evolving threats and the model's behavior over time.
Remember, output validation is not a guarantee of perfect results, but a process of continual improvement to ensure responsible and trustworthy large language model implementations.
Tailor your validation strategies to the specific context and risks of your large language model application.
Combine automation with human expertise for optimal results.
Transparency and user communication are crucial for building trust and mitigating potential harm.
By diligently screening and refining the model's outputs, you can transform them from rough diamonds into polished jewels, ready to enrich and empower your users without exposing them to potential harms.
Keep in mind, security is an ongoing journey, and the responsibility of safeguarding large language model outputs falls not just on the technology, but also on the vigilant efforts of security professionals like yourself.
When integrating large language model chains with web applications, establishing clear boundaries is paramount. Not everyone should have access to every chamber of the fortress, and certain treasures demand extra protection.
Here's how to implement granular access controls to safeguard both model functionalities and sensitive information.
Let's take a look at authentication and authorization.
Authentication. Verify each user's identity before granting access to LLM functionalities. Employ robust mechanisms like passwords or multi-factor authentication and single sign-on for seamless integration with existing identity management systems.
Authorization. Define what specific large language model functionalities and information each user or role can access. Implement strategies like role-based access control and attribute-based access control for more granular control based on attributes or context.
Let's take a look at some access control mechanisms. Access control lists. Specify permissions for individual users or groups at the resource level, such as specific large language models or datasets.
Role-based access control. Assign permissions based on predefined user roles, simplifying management and reducing the risk of errors.
Attribute-based access control. Grant access based on user attributes or context such as location, device, and time of day, enabling more flexible and dynamic control.
API gateways. Centralize access control for large language model APIs, enforcing policies and protecting against unauthorized access.
Auditing and logging. Track access attempts. Monitor who accesses model functionalities when and from where to detect unauthorized access attempts or suspicious activity.
And regularly review access policies. Periodically review and update access control policies to align with evolving business needs and security requirements.
Remember, access control is an ongoing process, not a one-time configuration. Stay vigilant and adaptable to maintain effective protection.
Integrate access controls with your overall identity and access management strategy, and conduct regular security audits to identify potential vulnerabilities in your access control mechanisms.
By implementing granular access controls, you create a web application that functions like a well-guarded fortress, granting entry only to those with legitimate business within its walls. Each chamber of model functionality is protected by its own set of keys, ensuring that sensitive information and powerful capabilities remain in the right hands.
When constructing a secure large language model integration, it's wise to leverage the expertise and craftsmanship of security professionals who've forged reliable building blocks.
Security libraries and frameworks offer pre-built, battle-tested solutions, saving you time, reducing errors, and fortifying your application's defenses. Here's how to wield these valuable tools effectively.
Let's look at choosing the right tools for the job. Authentication with Passport.js, Spring Security, and .NET Identity.
Encryption with OpenSSL, Libsodium, and Bouncy Castle.
Validation with Validator.js, Apache Commons Validator, and Fluent Validation.
Input sanitization with DOM Purify, OWASP Anti-SAMI, and Anti-XSS.
And threat modeling with OWASP Threat Dragon, Microsoft Threat Modeling Tool, and Erius Risk.
Seamless integration, compatibility. Ensure chosen libraries and frameworks align with your programming languages, frameworks, and architecture.
Documentation. Follow clear documentation and examples for proper integration and configuration.
Testing. Thoroughly test integration to ensure functionality and avoid unintended security issues.
Staying up to date. Security patches. Regularly update libraries and frameworks to address known vulnerabilities and stay protected against evolving threats.
Dependency management tools. Use tools like NPM, Maven, or NuGet to manage dependencies and track updates efficiently.
Let's look at some benefits of leveraging security libraries and frameworks. Reduce development time. Pre-built solutions accelerate development and focus efforts on core large language model integration logic.
Enhance security. Built-in protections and best practices minimize vulnerabilities and coding errors.
And community support. Benefit from community expertise, bug fixes, and shared knowledge for ongoing maintenance and troubleshooting.
Remember, treat security libraries and frameworks as trusted partners, not silver bullets. Understand their capabilities and limitations.
Integrate them thoughtfully within your overall security architecture and conduct regular security audits and penetration testing to ensure their effectiveness within your large language model integration.
By embracing these battle-tested tools, you'll construct your large language model integration with reinforced bricks, ensuring solid foundations and a fortress resilient against many common attacks.
Choose your building blocks wisely, integrate them with care, and maintain them vigilantly to safeguard your large language model journey.
Let's take a closer look at threat modeling. Identifying potential threats.
Stride approach. Utilize the Stride framework to systematically identify potential threats such as spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege across the large language model integration lifecycle.
Large language model-specific threats. Consider threats specific to large language models such as prompt injection attacks, data poisoning and bias amplification, model extraction and adversarial attacks, and downstream manipulation of outputs.
Business context. Factor in your specific business context, identifying sensitive data, user roles, and potential attack motivations.
Building mitigation strategies. Architectural countermeasures. Design your large language model integration with security in mind, incorporating features like microservices architecture and API security.
Input validation and output validation. Implement rigorous validation processes to cleanse data before feeding it to the model and before presenting outputs to users.
Access controls and data protection. Define granular access controls and utilize encryption, tokenization, and pseudonymization to protect sensitive data.
Monitoring and logging. Continuously monitor model activity and user interactions for anomalies and suspicious behavior.
Threat modeling tools and practices. OWASP Threat Dragon. Leverage threat modeling tools like OWASP Threat Dragon to visualize threats, vulnerabilities, and mitigations.
Custom large language model chain analysis. Leverage tools like FlowEyes to build your own threat modeling analysis tools with large language model chains.
Collaborative approach. Involve developers,
Custom large
security
language model,
professionals,
chain
and other
analysis.
stakeholders in the
Leverage
threat
tools like
modeling
Flowsy
process
to build your
for
own threat
comprehensive
modeling
coverage.
analysis tools with model
And regular
chains.
reviews and updates. Regularly review and update your threat model as your large language model integration evolves and new threats emerge.
Remember, threat modeling is not a one-time exercise, but an ongoing process of vigilance and adaptation.
Choose the threat modeling methodology that best aligns with your needs and expertise and integrate threat modeling results into your development and security processes for optimal effectiveness.
By proactively identifying and mitigating potential threats, you'll transform your large language model integration into a fortress equipped with potent antidotes against malicious actors.
Just like a vigilant knight constantly checking his armor and sharpening his sword, maintaining version control and ensuring timely security updates are essential for a secure large language model integration.
Here's how to keep your large language model fortress impregnable against vulnerabilities.
Implement a robust version control system like Git for all large language models, datasets, application components, and infrastructure configurations.
Maintain clear version tags and descriptions to track changes and understand their impact on security.
Utilize branching and merging strategies to manage development workflows while preserving security controls.
Security patch management. Actively subscribe to security advisories and vulnerability reports for all software and libraries used in your large language model integration.
Prioritize patching critical vulnerabilities promptly, especially those exposing sensitive data or enabling code execution.
Develop a clear process for testing and deploying security patches to minimize disruption and maintain security posture.
Automate your defenses. Implement automated mechanisms like OWASP dependency check to test for vulnerable and/or outdated software libraries and frameworks whenever possible.
Consider containerized deployments with immutable infrastructure to simplify rolling out updates and rollback if needed.
Monitor update logs and system behavior for any potential regressions or unexpected issues arising from automated updates.
Testing and rollback plans. Conduct thorough regression testing after applying security patches or significant version updates to ensure your model integration remains functional and secure.
Have rollback plans in place for reverting to previous versions in case of unexpected issues or security problems after updates.
And regularly test your rollback plan to ensure its effectiveness in case of emergencies.
Remember, version control and security updates are not one-time tasks, but ongoing processes that require dedication and vigilance.
Prioritize security patches for critical vulnerabilities and develop efficient update processes to minimize risks.
Automate updates where possible, but always test and monitor for potential regressions.
And be prepared to roll back to previous versions if necessary, and have a robust incident response plan in place.
When it comes to large language models, a robust incident response plan is your knight in shining armor, ready to leap into action when potential security breaches threaten your digital fortress.
Let's delve into crafting a plan that will keep your large language model integration safe and sound.
Defining responsibilities and communication. Assemble your response team. Identify key personnel from DevOps, security, legal, and communication departments, and define their roles and responsibilities during an incident.
Establish communication channels. Determine clear communication channels for internal and external stakeholders, ensuring timely and secure information flow.
Early warning systems. Implement tools and processes for monitoring mode activity, user behavior, and system logs for anomalies and suspicious activity.
Incident identification and escalation. Define criteria for identifying potential security incidents and establish escalation procedures for notifying designated responders.
Forensic analysis. Securely collect and analyze relevant data for evidence preservation and incident investigation.
Containment and eradication. Immediate actions. Outline predefined actions to contain the incident, such as shutting down affected systems, isolating compromised data, and revoking access privileges.
Root cause analysis. Conduct a thorough investigation to identify the root cause of the incident and prevent future occurrences.
Recovery and mitigation. Develop and execute a recovery plan to restore affected systems and data, and implement mitigation strategies to address vulnerabilities exploited in the incident.
Communication and reporting. Internal communication. Keep your team and relevant stakeholders informed throughout the incident, communicating progress and updates transparently.
External communication. Develop a strategy for public communication in case the incident impacts users or external parties, balancing transparency with security considerations.
Post-incident reporting. Document lessons learned from the incident and revise your response plan as necessary to address any gaps or weaknesses exposed.
Testing and training. Regularly test your plan. Conduct simulations and tabletop exercises to test your incident response plan, identify areas for improvement, and ensure team readiness.
And training and awareness. Train your team on incident response procedures, security best practices, and recognizing potential threats.
Remember, an effective incident response plan is adaptable, not static. Update it regularly to reflect changes in your large language model integration, emerging threats, and best practices. Communication is key during an incident. Ensure clear and timely information flow to maintain control and minimize damage. Learning from past incidents is crucial. Analyze incident reports and use them to improve your response plan and overall security posture.
By crafting a comprehensive and tested incident response plan, you equip your large language model integration with the armor and shield it needs to withstand any digital attack.
Regularly scheduled security audits are indeed the vigilant watchtowers of your large language model fortress, constantly scanning the horizon for potential vulnerabilities and ensuring your defenses remain strong. Let's explore how these audits can safeguard your large language model integration.
Shining a light on hidden weaknesses. Internal versus external audits. Consider both internal audits by your own security team and external audits by independent security professionals.
Scope and frequency. Tailor the scope and frequency of audits to your specific large language model integration, risk profile, and regulatory requirements. Consider factors like data sensitivity, system complexity, industry regulations, and business importance.
Vulnerability assessments and testing. Vulnerability assessments. Identify potential weaknesses in your model, code, infrastructure, and configuration.
Penetration testing. Simulate real-world attack scenarios to test the effectiveness of your security controls and identify potential exploitable vulnerabilities.
Compliance checks and reporting. Compliance with security standards. Ensure your large language model integration adheres to relevant security standards and regulations like GDPR, HIPAA, NIST, 853, etc.
Audit reports and remediation plans. Receive detailed audit reports outlining identified vulnerabilities and recommended remediation steps.
Continuous improvement. Track progress in addressing vulnerabilities and implementing recommended security improvements.
And finally, let's take a look at some benefits of regular security audits. Proactive identification of threats. Discover vulnerabilities before they can be exploited by attackers.
Improve security posture. Continuously strengthen your model integration's defenses and address emerging threats.
Compliance assurance. Demonstrate adherence to security regulations and industry best practices.
And enhance trust and reputation. Build confidence among users and stakeholders in your large language model integration security.
Remember, security audits are a continuous journey, not a one-time event. Make them a regular part of your large language model integration maintenance routine.
Choose qualified and experienced security auditors who understand the specific risks and challenges of model integrations.
And be transparent and responsive to audit findings, implementing recommended improvements promptly and effectively.
This is the end of Section 10, Architectural and Application Security Considerations for Integrating Large Language Model Chains with Web Applications. This is Section 11, Architectural and Application Security Considerations for Integrating Large Language Model Chains with Mobile Apps.
Large language models are expanding their reach beyond web applications, venturing into the dynamic world of mobile apps. While this opens exciting possibilities, it also introduces new security considerations. Just like with web apps, a layered approach to security is crucial for large language model integration with mobile apps.
This section will delve into both architectural and application-level vulnerabilities, guiding you through the essential security measures to prioritize throughout the design, development, and deployment process.
By implementing these best practices, you can unlock the full potential of large language models in your mobile apps while ensuring the safety and security of your users and data.
Let's first take a look at some common mobile app architecture designs. Model view view model.
Structure separates business logic model, user interface view, and presentation logic view model into distinct layers.
Large language model integration. Mid-tier. Large language model chains and API connections reside on a separate server, accessed by the view model via APIs. Enables cleaner separation of concerns and enhanced security.
Backend. Large language models and vector databases can be hosted within the app or on a dedicated server, requiring careful security considerations and resource management.
Security considerations. Secure communication between app and large language model servers using encrypted APIs.
Granular access controls and user authentication based on model functionalities.
Sandboxing and resource management for native large language model implementations within the app.
And secure data storage mechanisms for any local data involved in large language model interactions.
Model view presenter design. Structure. Similar to model view view model, but presenter handles interactions between model and view, offering tighter control over UI updates.
Large language model integration follows the same approach as model view view model, with presenter communicating with large language model servers or handling local model execution, ensuring security considerations are addressed similar to MVVM.
And clean architecture. Structure. Emphasizes dependency inversion and separation of concerns, with code independent of specific frameworks or platforms.
Large language model integration encourages using interfaces and abstractions for large language model interactions, allowing easy switching between server-side APIs, local libraries, or mock implementations for testing.
Security considerations remain similar to MVVM and MVP, focusing on secure communication, access control, and data handling.
Here are some tips for secure large language model integration in native apps. Leverage platform-specific security features and libraries.
Use Secure Enclave for sensitive data processing on hardware if available.
Implement code obfuscation and anti-tampering measures.
Regularly update libraries and frameworks to stay ahead of vulnerabilities.
And conduct thorough security audits and penetration testing.
Remember, choose the architecture that best suits your project's complexity, performance needs, and security requirements.
Prioritize secure communication, access control, and data handling for all model interactions, and stay informed about evolving mobile security threats and best practices.
Let's look at integrating large language model chains with mobile apps.
Scrutinizing the source. Reputable data providers. Source your data from reliable and trustworthy providers who can demonstrate robust data acquisition and quality control processes.
Transparency and provenance. Ensure information about data sources, collection methods, and potential biases is clear and readily available.
Diversity and balance. Choose datasets that are diverse and representative of the real-world population to avoid perpetuating biases or unfair outcomes.
Examining the training data. Content analysis and filtering. Analyze the training data for potential biases, offensive content, or vulnerabilities like adversarial examples. Consider using bias detection tools and human review processes.
Data cleansing and pre-processing. Remove irrelevant, inaccurate, or potentially harmful data before feeding it to the model. Implement data cleaning and pre-processing techniques.
Monitoring and continuous improvement. Continuously monitor your model's output for signs of bias or vulnerabilities arising from the training data. Be prepared to retrain the model with improved data if necessary.
Addressing specific concerns, privacy considerations. If the training data involves personally identifiable information, ensure you're compliant with relevant privacy regulations and user consent is obtained. Consider techniques like anonymization or differential privacy.
Security risks. Securely store and transmit the training data to prevent unauthorized access or tampering. Implement strong encryption and access controls.
Evolving threats. Stay informed about emerging vulnerabilities and biases in popular large language models and the broader AI landscape. Adapt your data sourcing and training practices accordingly.
Building trust and transparency. Be transparent about your data sourcing and training practices, openly outlining potential biases or limitations in your model.
Provide users with information on how their data is used and how they can control its use.
And develop feedback mechanisms for users to report potential issues or concerns related to your model's output or potential biases.
Remember, choosing the right source and training data is a critical first step in building a secure and trustworthy large language model-powered mobile app.
There's no one-size-fits-all approach. Evaluate your specific needs, risks, and regulatory requirements when selecting and processing training data.
Continuous monitoring, ethical considerations, and transparency are key to maintaining trust and minimizing potential harm from your large language model.
When it comes to large language models and mobile apps, sometimes less truly is more. Gathering a mountain of data might seem tempting, but remember, with great power comes great responsibility.
Collecting only the bare essentials not only safeguards user privacy, but also strengthens your app's security posture. Let's delve into the magic of minimalism.
Define the core functionality of your large language model. What specific tasks should it perform? Clearly identify the minimum data points needed to accomplish those tasks effectively.
For example, an image recognition model might only need pixel data, while a sentiment analysis model might require text itself.
Scrutinize every data point you consider collecting. Ask yourself, is it truly necessary for the model's function? Could the task be achieved with existing data or alternative methods?
Does it add significant value to the user experience? Would collecting this data meaningfully improve the app's functionality or performance?
Are there privacy concerns? Could collecting this data potentially infringe on user privacy or raise ethical questions?
Explore creative ways to achieve your model's goals without amassing unnecessary data. Consider techniques like on-device processing, pre-processed data on the mobile device itself, minimizing the need for cloud transmission and storage.
Federated learning. Train the model on user devices without directly sharing individual data, protecting privacy while leveraging collective learning power.
And differential privacy. Add statistical noise to data to ensure its usefulness for analysis while preserving individual privacy.
Be upfront with your users about what data you collect and how it's used. Provide clear options for users to control their data, such as opting out of data collection or requesting deletion. Remember, trust is built on transparency.
Regularly review your data collection practices. As your model evolves and user needs change, reassess which data points are truly essential. Don't be afraid to refine and minimize your data collection over time.
Benefits of minimizing data collection include enhanced security. A smaller attack surface means less data for attackers to exploit.
Improved privacy. Respecting user privacy builds trust and strengthens your brand reputation.
Streamlined performance. Processing less data translates to faster, more efficient model operation.
Ethical advantage. Demonstrates a commitment to responsible data practices and avoids potential ethical pitfalls.
Remember, minimizing data collection is not just about complying with regulations. It's about building a secure, trustworthy, and user-centric large language model experience.
By embracing this principle, you pave the way for a future where large language models empower users without compromising their privacy or security.
When it comes to your large language model and the data it processes, security should be your armor and encryption your trusty shield. Your users entrusted you with their information, and it's your responsibility to ensure it remains safe from prying eyes and malicious attacks.
Let's dive into the realm of secure data storage and transmission, where powerful protocols and encryption algorithms stand guard against digital threats.
Encrypted vaults, both on-device and in the cloud. Data at rest. Encrypt any sensitive data stored on the mobile device or in the cloud, minimizing the potential damage if your app or server is compromised.
Secure communication tunnels. HTTPS for trust and transparency. Let the S stand for secure. Always opt for HTTPS connections, which encrypt communication and validate server identity, ensuring you're sending data to the right place.
Secure sockets for encrypted whispers. TLS version 1.2 or higher protocols create secure tunnels for data transmission, encrypting information and protecting it from eavesdropping and tampering.
Certificate verification. Double-check the digital signature. Verify server certificates to ensure you're communicating with the legitimate server and avoid imposter attacks.
Beyond the basics with advanced security measures. Tokenization. Replace sensitive data, like credit card numbers, with unique tokens for added security and reduced attack surface.
Data anonymization and pseudonymization. Protect identities by transforming data into unrecognizable forms while retaining its usefulness for the model.
Secure key management. Store and manage encryption keys securely, utilizing techniques like hardware security modules and strict access controls. Remember, encryption and secure communication protocols are essential, but not impenetrable. Layer these measures with other security practices like secure coding, regular security audits, and vulnerability assessments for comprehensive protection.
Stay informed about emerging threats and vulnerabilities in mobile app security and encryption technology. Continuously update your practices to adapt to the evolving landscape.
Building a secure environment for your large language model-powered mobile app is an ongoing journey, not a one-time destination. Embrace a proactive approach to maintaining user trust and ensuring the safety of their data.
In the world of large language models and mobile apps, transparency and user control aren't just buzzwords, they're the cornerstones of trust.
Your users entrust you with their data and expect you to handle it with respect and responsibility.
Let's explore how empowering them with control and transparency can strengthen your large language model-powered app and build lasting trust.
Granular data control. Give your users the reins. Design your app to allow them to decide what data the model can access and use.
Consider options like opt-in, opt-out mechanisms. Provide clear options for users to choose whether and how their data is used by the large language model.
Granular permissions. Allow users to control access to specific data types such as location, contacts, or camera access.
Data deletion and correction. Give users the power to request deletion or correction of their data stored and used by the model.
Transparency. Plain and simple. Don't leave your users in the dark. Be transparent about data collection practices. Clearly explain what data you collect, how it's used, and why it's necessary for the model's functionality.
Large language model processing and outputs. Describe how the model uses the data, what types of outputs it generates, and how those outputs are used in the app.
Privacy policy and terms of service. Make your policies easily accessible and understandable, clearly outlining your data handling practices and user rights.
Feedback and communication channels. Open the door for dialogue. Create accessible channels for users to ask questions, express concerns, and provide feedback about your data practices and the model's operation.
Customer support channels. Provide email, live chat, or phone support for users to reach out with questions or concerns.
Community forums and social media. Foster open communication channels where users can discuss your model and share their experiences.
Building trust through action. Respect user choices. Honor opt-in, opt-out decisions and data access restrictions set by your users.
Respond promptly to concerns. Address user questions and feedback about data and privacy in a timely and transparent manner.
And demonstrate accountability. Show your commitment to responsible data handling through proactive security measures and regular audits.
Remember, user control and transparency are not one-time exercises but ongoing commitments. Regularly review and update your practices as your model evolves and user needs change.
Building trust takes time and effort. Show your users you value their privacy and control by consistently demonstrating responsible data handling and respecting their choices.
When integrating a large language model into your mobile app, securing your code becomes paramount. It's no longer just about protecting user data. You need to safeguard the very logic that drives your model's magic.
Enter the realm of code hardening and sandboxing, your digital knights and moats, ready to repel attackers and keep your precious app safe.
Let's take a look at code hardening. Address space layout randomization. Disrupt attackers by randomly scrambling the memory locations of your app's code and data. This makes it significantly harder for attackers to exploit known vulnerabilities or predict memory addresses.
Control flow obfuscation. Make your code a labyrinth for attackers. Scramble program control flow patterns, making it difficult for attackers to reverse engineer your code and understand its logic.
Sandboxing, memory sandboxing, create separate memory spaces for your app.
Secure enclaves. Utilize hardware-based secure enclaves if available to provide an even more secure execution environment for sensitive portions of your code.
Benefits of code hardening and sandboxing include enhanced security, makes your app more resistant to attacks like code injection, memory corruption, and reverse engineering.
Data protection minimizes the risk of vulnerabilities leading to data breaches or unauthorized access.
Improves stability, reduces the potential for unexpected interactions between the app and other apps installed on the device.
Trade-offs and considerations. Performance impact. Code hardening and sandboxing can add some overhead, potentially impacting your app's performance. Weigh the security benefits against potential performance trade-offs.
Platform compatibility. Certain techniques might not be supported on all mobile platforms. Choose techniques compatible with your target platforms.
Regular updates. Stay informed about emerging vulnerabilities and update your hardening and sandboxing strategies accordingly.
Remember, code hardening and sandboxing are essential layers of defense for your large language model-powered mobile app. Combine them with other security practices like secure coding, vulnerability assessments, and strong authentication.
Security is an ongoing journey, not a destination. Continuously improve your defenses to stay ahead of evolving threats and maintain a secure environment for your large language model and user data.
When constructing a mobile app that harnesses the power of large language models, the foundation matters. The libraries and frameworks you choose act as the building blocks of your app's functionality and security.
Selecting secure and up-to-date components is paramount to protect your large language model, user data, and the integrity of your app. Let's dive into the strategies for building a strong foundation.
Choosing wisely. Reputation matters. Opt for libraries and frameworks with a proven track record of security and active maintenance. Look for those with a history of prompt vulnerability patching and a dedicated community.
Security-focused. Prioritize options that have been developed with security in mind, incorporating features like input validation, authentication, and encryption.
Open source transparency. Consider the value of open source libraries and frameworks. Their code is publicly available for scrutiny, enabling broader community contributions to security improvements.
Staying up to date, patch early, patch often. Regularly update libraries and frameworks to address newly discovered vulnerabilities. Promptly integrate security patches to minimize exposure to attacks.
Dependency management tools. Leverage tools like Maven or Gradle to automate dependency updates and ensure your app always uses the latest secure versions.
Vulnerability notifications. Subscribe to security bulletins and mailing lists to stay informed about emerging vulnerabilities and available patches.
Evaluating security. Review code and documentation. Examine the source code of libraries and frameworks if possible to assess their security practices and potential vulnerabilities.
Security audits and tools. Utilize security scanning tools to identify known vulnerabilities in your app's dependencies and prioritize updates accordingly.
Community feedback. Seek insights from the developer community regarding the security reputation of different libraries and frameworks.
Additional considerations. Mobile-specific libraries. Choose libraries and frameworks specifically designed for mobile app development, as they often address unique security challenges of mobile platforms.
Third-party risk management. Assess the security practices of third-party providers of libraries and frameworks, as their vulnerabilities could impact your app.
Remember, security is a shared responsibility. Even with secure libraries and frameworks, ensure your own code adheres to secure coding practices and undergoes regular security testing.
Stay vigilant and proactive in maintaining the security of your app's dependencies. It's an ongoing process, not a one-time task.
In the ever-evolving landscape of digital threats, vigilance is key. When it comes to your large language model-powered mobile app, that vigilance translates into one crucial practice: the consistent application of security updates.
Just like patching armor before entering battle, these updates reinforce your digital defenses.
Why updates matter? Plugging the holes. Security updates address newly discovered vulnerabilities in your app and its underlying libraries.
Maintaining user trust. Regular updates demonstrate your commitment to user safety and data security. Users will feel more confident in trusting their information and interactions to your app when they know you prioritize safeguarding their data.
Building a culture of updates. Automate where possible. Utilize automated update mechanisms for your app and libraries whenever available. This ensures the latest patches are applied swiftly and without manual intervention.
Monitor and prioritize. Set up alerts for critical vulnerabilities and prioritize patching those immediately. Don't wait for a full app update to address urgent security issues.
Communicate with users. Clearly inform users about security updates, explaining the importance of installing them promptly. Consider in-app notifications or release notes to educate users about the fixes and improvements included.
Testing and compatibility. Ensure updates undergo thorough testing and compatibility checks to avoid introducing new bugs or breaking functionality.
Device fragmentation. The diverse Android landscape, with its many device versions and update schedules, can make ensuring everyone receives timely updates challenging.
Consider alternative mechanisms like downloadable patches for older devices.
User adoption. Encourage users to install updates by emphasizing the security benefits and potential risks of delaying. Offer flexible options like scheduling updates when convenient for users.
Remember, security updates are not a one-time fix. They're an ongoing process of vigilance and proactive defense. Develop a robust update strategy and integrate it into your app's lifecycle management.
Collaboration is key. Keep a pulse on industry best practices, participate in security communities, and collaborate with library and framework maintainers to stay informed and address vulnerabilities effectively.
With any powerful technology like a large language model-powered mobile app, great potential comes with its own set of shadows, potential threats and vulnerabilities waiting to be exploited.
To truly unlock the power of your large language model while mitigating risks, you need to become a master of the shadows, wielding the torch of threat modeling and risk assessment. Let's delve into this crucial practice.
Let's look at mapping the threatscape. Identify threats. Conduct a thorough threat modeling exercise, considering potential attacks against your large language model app. This includes data breaches, model manipulation, adversarial inputs, unauthorized access, and privacy violations.
Analyze attackers. Understand the motivations and capabilities of potential attackers. Are they state-sponsored actors, individual hackers, or opportunistic script kiddies?
Assess attack paths. Map out the possible routes attackers could take to exploit vulnerabilities. Consider technical avenues such as code injection and API vulnerabilities, and social engineering tactics such as phishing and app store manipulation.
Quantifying risks, likelihood and impact. Assess the likelihood of each identified threat occurring and the potential impact it could have on your app, users, and data. Prioritize mitigation efforts based on this risk score.
Data sensitivity. Consider the sensitivity of the data your large language model handles. A data breach involving sensitive user information would have a more significant impact than one affecting less sensitive data.
Reputational risks. Don't underestimate the damage to your reputation and brand caused by security incidents. Factor in this potential impact when prioritizing mitigation efforts.
Building your defenses. Mitigation strategies. Based on your risk assessment, develop and implement mitigation strategies for identified threats. This could involve secure coding practices, encryption, input validation, sandboxing, access controls, and vulnerability patching.
Continuous monitoring. Actively monitor your app and model for signs of suspicious activity. Utilize security tools and logs to detect potential attacks early and take necessary countermeasures.
Incident response plan. Have a clear and tested incident response plan in place to handle security breaches and minimize damage. This includes communication protocols, data recovery procedures, and user notification strategies.
Adapting to the changing shadows. Regular reviews. Your threat model and risk assessment are not static documents. Regularly review and update them as your app evolves, the model changes, and new threats emerge.
Embrace collaboration. Share your threat model and risk assessment with security experts and the developer community. Collaborate to identify blind spots and strengthen your overall security posture.
Remember, threat modeling and risk assessment are not one-time activities. They're ongoing processes crucial for the continuous security of your large language model-powered mobile app.
By shining the light of awareness on potential threats, you empower yourself to build robust defenses and safeguard your users, data, and the valuable large language model at the heart of your app.
The journey to secure large language model-powered mobile apps doesn't end with technical measures. It extends to empowering your users with knowledge and awareness.
After all, they're the first line of defense and your partners in building a secure digital ecosystem. Let's explore ways to educate and engage your users, turning them into active participants in your security journey.
Transparent communication. Be upfront about the potential risks inherent in using large language model-powered apps. Explain how data is used, what types of vulnerabilities exist, and how users can protect themselves.
Security tips and best practices. Provide clear and actionable tips on safe large language model app usage. This could include awareness of phishing scams, avoiding suspicious inputs, keeping apps updated, and reporting suspicious activity.
In-app tutorials and help guides. Embed educational elements within your app itself. Utilize interactive tutorials, pop-up explanations, and readily accessible help guides to empower users within the app experience.
Feedback loops for trust and collaboration. Report channels. Create easily accessible avenues for users to report suspicious activity, potential vulnerabilities, or concerns about data privacy. Consider email, in-app feedback forms, or even anonymous reporting mechanisms.
Acknowledge and respond. Promptly acknowledge user reports and take them seriously. Investigate issues, provide updates on progress, and demonstrate your commitment to addressing user concerns.
Community engagement. Foster a community around your large language model app. Encourage open communication with users, address their questions and feedback transparently, and build trust through active engagement.
Balancing transparency and user experience. Provide context and reassurance. While informing users about potential risks, avoid creating undue fear or negativity. Focus on empowering them with knowledge and demonstrating your commitment to security.
Keep it clear and concise. Don't overwhelm users with technical jargon. Explain security concepts in simple, understandable language, catering to diverse levels of technical expertise.
And make it engaging and accessible. Leverage visuals, interactive elements, and gamification techniques to make user education an engaging and memorable experience.
Remember, user education is not a one-time event. It's an ongoing process. Integrate it into your app development lifecycle, update information as threats evolve, and adapt your approach based on user feedback.
Building trust through transparency and engagement empowers users to become active participants in your security journey. This collaborative approach strengthens your overall security posture and fosters a more secure and productive large language model experience for everyone.
This is the end of Section 11, Architectural and Application Security Considerations for Integrating Large Language Model Chains with Mobile Apps. This is Section 12, Security Considerations for Integrating Large Language Model Chains with Embedded Data Lakes.
Integrating large language model chains with embedded data lakes unlocks an exciting world of possibilities for on-device intelligence and personalized experiences. However, with great power comes great responsibility, and ensuring the security of this architecture demands careful consideration.
Let's delve into the potential threats and explore strategies to safeguard your large language model chains and embedded data lakes.
Vulnerability landscape. Large language model execution. Vulnerabilities. Attackers might exploit weaknesses in the way the large language model chains process data. This could involve injecting malicious code into inputs, exploiting bugs in model inference, or manipulating training data to introduce bias and ultimately compromise data integrity.
Data access control flaws. Weak access control mechanisms or configuration errors within the embedded data lake could allow unauthorized users to access sensitive data. This could be achieved through social engineering, exploiting software vulnerabilities, or bypassing security measures through physical access to the device.
Communication channels, weaknesses. Insecure communication protocols or vulnerabilities in data transmission pathways between the large language model, the data lake, and external servers could expose sensitive information to interception or manipulation.
Data encryption. Encrypt data at rest within the embedded data lake and in transit between different components. Utilize strong encryption algorithms and secure key management practices.
Access control granularity. Implement granular access controls within the data lake, restricting access to specific data types and attributes based on user privileges and authorization levels. Regularly review and audit access control policies.
Threat modeling and penetration testing. Conduct regular threat modeling exercises to identify potential attack vectors and conduct penetration testing to proactively discover and address vulnerabilities before malicious actors can exploit them.
Secure communication protocols. Utilize secure communication protocols like TLS version 1.2 or higher when transmitting data between the large language model, the data lake, and external servers. Implement additional security measures like data signing and verification to ensure data integrity.
Additional considerations. Secure boot and tamper protection. Implement secure boot mechanisms and tamper protection features on devices hosting the large language model chains and embedded data lakes to prevent unauthorized software modifications and protect against malware injection.
User education and awareness. Educate users about potential security risks associated with large language model-powered applications and best practices for data privacy protection. Encourage them to report suspicious activity or unusual behavior.
Incident response planning. Develop a comprehensive incident response plan to effectively handle data breaches and minimize potential damage. This should include clear communication protocols, data recovery procedures, and user notification strategies.
Remember, data breaches are not inevitable, but they require proactive planning and a layered security approach. By understanding the vulnerabilities, implementing robust mitigation strategies, and fostering a culture of security awareness, you can significantly reduce the risk of data breaches and safeguard the sensitive information entrusted to your large language model chains and embedded data lakes.
Model manipulation poses a serious threat to large language model chains, potentially introducing bias, disrupting functionality, or violating user trust. Let's unravel these vulnerabilities and explore strategies to protect your models.
Attack vectors and manipulation techniques. Poisoning the well. Attackers might try to manipulate training data to introduce bias or backdoors into large language models. This could involve injecting malicious samples during model development or compromising data sources used for ongoing training.
Adversarial inputs. Crafted adversarial examples, carefully designed inputs aimed at misleading the model, could trigger incorrect outputs or unexpected behavior, potentially leading to security breaches or privacy violations.
Model extraction and theft. Attackers might attempt to extract or steal models for nefarious purposes, such as replicating sensitive functionality, impersonating the model, or exploiting vulnerabilities within it.
Secure data pipelines. Implement robust security measures throughout data pipelines, including data validation, cleaning, and authentication, to ensure the integrity of training data and prevent poisoning attacks.
Adversarial training. Incorporate adversarial training techniques during model development to make models more resilient to adversarial inputs. This involves exposing the model to carefully crafted adversarial examples during training to increase its robustness.
Input validation and sanitization. Rigorously validate and sanitize all inputs provided to the model chain to detect and block potential adversarial examples or malicious data.
Model monitoring and anomaly detection. Continuously monitor model behavior for anomalies or unexpected outputs that could indicate manipulation attempts. Implement anomaly detection systems to trigger alerts and initiate investigations.
Secure execution environments. Isolate sensitive large language model components within secure execution environments, such as hardware-based enclaves or trusted execution environments, to provide additional protection against tampering and unauthorized access.
Additional considerations. Provenance tracking. Track the provenance of model updates and data sources to identify potential points of compromise and facilitate forensic analysis in case of suspected model manipulation.
Trusted model sources. Obtain models from reputable and trusted sources to reduce the risk of pre-existing backdoors or vulnerabilities.
User education and transparency. Educate users about the potential for model manipulation and encourage them to report suspicious behavior or unexpected outputs. Foster transparency about model development and update processes to build trust.
Remember, model manipulation is an evolving threat, requiring continuous vigilance and adaptation of security measures.
By understanding the attack vectors, implementing robust mitigation strategies, and fostering a culture of security awareness, you can significantly reduce the risk of model manipulation and protect the integrity of your large language model chains and embedded data lakes.
In the realm of large language models and embedded data lakes, even the shadows hold risks. Inference attacks, like silent thieves in the night, can exploit information hidden within the data or outputs, unveiling private details and compromising user privacy.
Let's shed light on these threats and explore strategies to keep your data lake and large language model chains shrouded in privacy.
The vulnerability landscape. Inferred relationships. Attackers might analyze model outputs and data lake contents to infer relationships or patterns between seemingly unrelated data points,
potentially revealing sensitive information about individuals or groups.
Membership inference attacks. By observing model outputs for different inputs, attackers could potentially determine whether a specific data point belongs to a private dataset stored in the embedded data lake, compromising data privacy and potentially enabling further attacks.
Model inversion attacks. In some cases, attackers might try to reverse engineer the model from its outputs to reconstruct sensitive information that was used for training or inference.
Mitigation strategies. Differential privacy. Implement differential privacy techniques during model training and inference to add controlled noise to data and outputs, ensuring accurate results while minimizing the risk of revealing individual information.
Federated learning. Consider federated learning approaches where training data remains on individual devices, reducing the attack surface for data breaches and inference attacks on the central data lake.
Data minimization. Minimize the amount of data stored in the embedded data lake and only collect and process data necessary for model functionality. This reduces the potential for attackers to exploit information leakage vulnerabilities.
Secure aggregation and homomorphic encryption. Utilize secure aggregation techniques and homomorphic encryption to combine data from multiple sources while preserving privacy and enabling computations on encrypted data without decryption.
Model distillation and knowledge transfer. Explore model distillation or knowledge transfer techniques to create smaller, less revealing models that retain the essential functionality of the original large language model while reducing the risk of privacy leaks through model inversion attacks.
Additional considerations. Privacy-preserving machine learning algorithms. Explore and experiment with privacy-preserving machine learning algorithms specifically designed to minimize information leakage during training and inference.
Regular privacy audits and risk assessments. Conduct regular privacy audits and risk assessments to identify potential vulnerabilities and proactively address privacy concerns within your large language model chains and embedded data lakes.
Transparent privacy policies and practices. Be transparent about your data collection, storage, and usage practices, and obtain informed consent from users for processing their data within the large language model and data lake environment.
Remember, privacy is not a luxury but a fundamental right in the digital age. By understanding the potential for privacy leaks, implementing robust mitigation strategies, and prioritizing user privacy throughout the design, development, and deployment of your large language model chains and embedded data lakes, you can build a trustworthy and secure ecosystem that protects personal information and fosters user trust.
Imagine your large language model, once a beacon of efficiency, grinding to a halt, its chains tangled, its data lake choked. Such is the threat of denial-of-service attacks, aimed at crippling performance and rendering your model inaccessible to users. Let's explore these vulnerabilities and forge our defensive shield.
Vulnerability landscape, resource exhaustion. Attackers could bombard the model with massive amounts of malicious inputs, consuming processing power, memory, and storage, leaving legitimate users stranded in a state of frustrating unresponsiveness.
Infinite loops and algorithmic complexity. Carefully crafted inputs could exploit weaknesses in the model's internal logic, triggering infinite loops or computationally expensive procedures that bring the system to its knees.
Data flooding and cache poisoning. Overwhelming the data lake with invalid or irrelevant data could saturate storage capacity, disrupting processing and potentially poisoning its contents, leading to incorrect model outputs.
Mitigation strategies. Rate limiting and throttling. Implement rate limiting and throttling mechanisms to control the rate and volume of data and requests entering the large language model chain and data lake. This helps prevent resource exhaustion and ensures fair access for legitimate users.
Input validation and anomaly detection. Rigorously validate all inputs and utilize anomaly detection systems to identify and filter out suspicious or malicious data before it reaches the large language model or data lake, preventing resource exhaustion and potential data poisoning.
Resource monitoring and scalability. Continuously monitor system resources and model performance. Implement load balancing and auto-scaling mechanisms to dynamically allocate resources and adjust capacity based on demand,
preventing overwhelmed systems and ensuring smooth operation.
Sandboxing and fault isolation. Consider sandboxing individual large language model modules or functions to limit the impact of DOS attacks and prevent propagation within the chain. Fault isolation mechanisms can help localize issues and prevent cascading failures.
Proactive threat intelligence and honeypots. Leverage threat intelligence sources and honeypot systems to stay informed about emerging DOS attack techniques and proactively adapt your defenses. Honeypots can lure attackers and provide valuable data for analysis and mitigation strategies.
Additional considerations: regular system updates and patching. Ensure your large language model frameworks, libraries, and operating systems are up to date with the latest security patches to address vulnerabilities that could be exploited for DOS attacks.
Security education and awareness. Educate users about potential DOS risks and encourage them to report suspicious activity or unusual behavior observed during model interactions.
Incident response planning and recovery. Develop a comprehensive incident response plan to efficiently handle DOS attacks, minimize downtime, and quickly restore user access to the large language model chain and data lake.
Remember, DOS attacks are not insurmountable obstacles, but require vigilance and proactive defense. By understanding the attack vectors, implementing robust mitigation strategies, and fostering a culture of security awareness, you can ensure your large language model chains and embedded data lakes stand tall against the tide of malicious intent, delivering a consistent and reliable experience for your users.
In the intricate realm of large language models and embedded data lakes, where information flows like a bustling marketplace, protecting sensitive data demands more than just padlocks. It requires erecting secure walls and deploying vigilant guards in the form of robust data segregation and access control mechanisms. Let's delve into these crucial architectural considerations.
Data segregation. Tiered data lake architecture. Implement a tiered data lake architecture where sensitive data is stored in separate tiers with increasingly stringent access controls and security measures. For example, highly confidential information might reside in a dedicated encrypted tier with limited access points, while less sensitive data can be stored in tiers with relaxed restrictions.
Data labeling and tagging. Clearly label and tag data within the lake based on its sensitivity level, purpose, and ownership. This facilitates granular access control decisions and helps track data usage and potential breaches.
Data masking and redaction. Consider data masking or redaction techniques when dealing with sensitive data within the large language model chain. This involves replacing or obfuscating specific data elements while preserving its utility for model training or inference, further minimizing the attack surface for unauthorized access.
Role-based access control. Implement role-based access control to grant and restrict access to specific data and model functionalities based on user roles and privileges. This ensures only authorized personnel can access sensitive information and prevents unauthorized modifications or misuse.
Least privilege principle. Adhere to the principle of least privilege, granting users only the minimum level of access required for their specific tasks. This minimizes the potential damage caused by accidental or malicious actions.
Multi-factor authentication. Enforce multi-factor authentication for all access points to the large language model chain and data lake. This adds an extra layer of security by requiring additional verification beyond passwords, making it harder for attackers to gain unauthorized access.
Regular review and auditing. Regularly review and audit access control policies and user privileges to ensure they remain aligned with current needs and identify potential vulnerabilities. Conduct access audits to track user activity and detect suspicious behavior.
Data encryption at rest and in transit. Encrypt data at rest within the data lake and in transit between different components of the large language model chain. Utilize strong encryption algorithms and secure key management practices to protect data confidentiality.
Tamper-proof data provenance. Implement tamper-proof data provenance mechanisms to track the origin, lineage, and modifications of data within the data lake. This helps provide accountability and facilitates forensic investigations in case of security incidents.
Secure execution environments. Consider utilizing secure execution environments like enclaves or virtualized containers to isolate sensitive large language model modules and data from untrusted environments, further safeguarding their security.
Remember, data segregation and access controls are the cornerstones of a secure large language model architecture. By carefully designing and implementing these mechanisms, you can create a layered defense that protects sensitive information, safeguards user privacy, and builds trust in your large language model-powered applications.
In a world where threats lurk in the shadows, even software fortresses can be breached. But what if we could create an inner sanctum, a chamber impervious to prying eyes and malicious intent? Hardware-based enclaves offer this promise, providing a sanctuary for sensitive large language model components within your architecture. Let's explore their potential.
Enclave architecture. Isolated execution. Enclaves act as secure, isolated execution environments within the device's hardware, typically based on trusted execution environments or secure enclaves provided by processor manufacturers.
Hardware-based protection. Enclave access and operations are protected by hardware-level security mechanisms, making it extremely difficult for attackers to breach or tamper with code and data residing within them.
Confidentiality and integrity. Enclaves ensure the confidentiality and integrity of sensitive model components and data, even if the device's primary operating system or other software components are compromised.
Applications for large language model chains and data lakes. Protecting sensitive models and data. Enclaves can safeguard sensitive large language models, model parameters, confidential training data, and private user data within the embedded data lake.
Secure model inference. Inference tasks can be performed within enclaves, protecting user inputs and model outputs from unauthorized access or manipulation.
Secure key management and encryption. Enclaves can securely store and manage cryptographic keys used for data encryption and authentication, further enhancing data protection.
Implementation considerations. Hardware availability. Check for hardware-based enclave support on your target devices, as not all devices may have this capability.
Programming frameworks and tools. Utilize appropriate programming frameworks and tools specifically designed for developing enclave-based applications.
Careful design and testing. Carefully design your large language model chain and data lake architecture to leverage enclaves for sensitive components without compromising overall performance or functionality. Conduct thorough testing to ensure security and functionality.
Remote attestation. Consider using remote attestation mechanisms to verify the integrity of enclaves and ensure they haven't been compromised before entrusting them with sensitive data or computations.
Hybrid approaches. Explore combining enclaves with other security measures like secure boot, data encryption, and access controls to create a layered defense strategy for your large language model and data lake.
Remember, secure enclaves offer a promising layer of hardware-based security for large language model chains and embedded data lakes.
By understanding their capabilities and architectural considerations, you can strategically deploy them to protect sensitive components and create a more secure and trustworthy large language model experience for your users.
In the realm of security, sometimes less is more. When it comes to large language models and embedded data lakes, minimizing the attack surface on individual devices can be a powerful security strategy. This is where federated learning and data minimization step into the limelight.
Distributed training. In federated learning, large language models are trained collaboratively on data distributed across multiple devices, rather than relying on a centralized data lake. This reduces the amount of sensitive data stored on individual devices, making them less attractive targets for attackers.
Privacy-preserving mechanisms. Federated learning often incorporates privacy-preserving techniques like differential privacy and secure aggregation to further minimize the risk of revealing individual user data during the training process.
Reduced vulnerability footprint. With decentralized training, a successful attack on one device wouldn't compromise the entire model or training dataset, limiting the potential damage.
Data minimization. Need-to-know basis. Only collect and store the minimum amount of data necessary for model functionality within the embedded data lake. This reduces the overall attack surface and minimizes the potential exposure of sensitive information.
Data aggregation and pre-processing. Consider aggregating and pre-processing data on the device before sending it to the large language model chain or central server. This further reduces the need for storing raw data on individual devices and limits the information exposed to potential attackers.
Model pruning and compression. Explore techniques like model pruning and compression to reduce the size and complexity of models deployed on devices. This reduces storage requirements and minimizes the processing power needed while still preserving model accuracy.
Combining federated learning and data minimization can create a powerful synergy, reducing the attack surface and protecting user privacy while maintaining model accuracy and functionality. However, trade-offs exist. Federated learning can be computationally expensive and require careful orchestration, while data minimization can potentially limit the effectiveness of large language models.
Additional considerations: secure communication protocols. Ensure secure communication protocols like TLS are used when transmitting data between devices and the large language model chain, even in a federated setup.
On-device security measures. Implement robust security measures like secure enclaves and tamper-proof storage on devices where data and model components reside.
Continuous monitoring and evaluation. Monitor the performance and security of your federated learning and data minimization strategies, adapting them as needed to maintain a balance between security and functionality.
Remember, federated learning and data minimization offer valuable tools for building secure large language model experiences. By strategically deploying these techniques, you can shrink the attack surface, protect user privacy, and foster trust in your large language model-powered applications.
Threat modeling and risk assessment are vital tools in proactively safeguarding your large language model applications. Let's delve into how these practices can guide your security efforts.
Threat modeling. Identifying vulnerabilities. Through structured exercises like STRIDE or PASTA, you systematically analyze your large language model system, pinpointing potential vulnerabilities and attack vectors.
Understanding the attacker's perspective. Putting yourself in the shoes of an attacker helps you anticipate their tactics and techniques, allowing you to prioritize mitigation efforts for the most likely and impactful threats.
Focusing on key risks. Threat modeling helps you identify the most critical risks, ensuring you are not just chasing down every possible vulnerability, but focusing on the ones that truly matter.
Evaluating severity and likelihood. By analyzing the potential impact of a vulnerability and the likelihood of an attack exploiting it, you can prioritize your mitigation efforts, focusing on risks that pose the greatest threat.
Cost-benefit analysis. Risk assessments help you determine the most cost-effective security measures by weighing the effort and expense of mitigation against the potential losses from exploited vulnerabilities.
Data-driven decision-making. By quantifying risks and factoring in various variables, you can make informed decisions about resource allocation and prioritize security investments based on objective data.
Combining approaches. Threat modeling informs risk assessment. The vulnerabilities identified through threat modeling provide the foundation for analyzing and prioritizing risks.
Risk assessment refines threat modeling. Insights from risk assessment can inform further iterations of your threat modeling process, leading to a more targeted and effective analysis.
Large language model specific considerations. Focus on data and model vulnerabilities. Pay particular attention to vulnerabilities related to data security, model manipulation, and privacy leaks.
Consider federated learning and enclaves. Factor in the security implications of utilizing techniques like federated learning or secure enclaves during threat modeling and risk assessment.
And let's take a look at some best practices. Engage diverse stakeholders. Involve developers, security experts, data scientists, and other relevant stakeholders in your threat modeling and risk assessment activities.
Leverage tools and frameworks. Utilize dedicated threat modeling tools and frameworks like Microsoft STRIDE or OWASP Threat Dragon to facilitate your analysis and documentation.
Regularly revisit and update. Don't treat threat modeling and risk assessment as one-time activities. Regularly revisit your findings and update them as your threat landscape evolves.
Secure communication protocols are the invisible armor shielding data on its journey through your large language model and data lake ecosystem. Let's explore why encrypting these pathways is crucial for maintaining your security posture.
The data highway under siege, man-in-the-middle attacks. Without secure protocols, data flowing between components, user inputs, model outputs, sensitive configurations, is vulnerable to interception and manipulation by malicious actors lurking on the network.
Data sniffing and eavesdropping. Unsecured communication leaves data exposed to passive snooping, revealing confidential information and potentially enabling attackers to exploit vulnerabilities.
Data tampering and alteration. Hackers can tamper with data in transit to compromise results, inject errors, or disrupt the functionality of your large language model system.
Creating a secure communication fortress, TLS version 1.2 or higher. Implement secure communication protocols like transport layer security.
Mutual authentication. Implement mutual authentication mechanisms to verify the identity of both servers and clients communicating within your large language model and data lake ecosystem. This prevents unauthorized access and impersonation attempts.
Strong encryption algorithms. Choose strong encryption algorithms and key management practices to ensure the robustness of your data encryption and decryption processes.
Regular certificate updates. Maintain TLS certificates with proper validity periods and update them promptly to prevent breaches due to expired certificates.
Large language model specific considerations. Model distribution security. Encrypt model updates and deployments while distributing them to various nodes or devices within your large language model chain.
External API security. Secure communication APIs and gateways that serve as entry points for user interactions and external integrations with your large language model system.
Federated learning and enclaves. Consider additional security measures like secure multi-party computation techniques or secure enclaves when dealing with data exchange in federated learning scenarios.
Remember, secure communication protocols are vital for establishing trust and maintaining data integrity within your large language model and data lake ecosystem.
By prioritizing encryption, authentication, and robust key management practices, you create a secure tunnel for data transmission, safeguarding your system from eavesdroppers, attackers, and unauthorized access. While we've fortified the technical defenses, the final piece of the puzzle lies in empowering your users. User education and awareness are the critical weapons in safeguarding the human element of your large language model-powered applications.
Let's explore how to equip your users with the knowledge and best practices to navigate the world of large language models securely.
Understanding the landscape, potential risks. Educate users about potential security risks associated with large language models, such as bias in model outputs, privacy concerns with data usage, and manipulation attempts.
Responsible interaction. Train users on best practices for interacting with large language model applications, including avoiding biased inputs, being mindful of data privacy settings, and reporting suspicious behavior.
Trust and transparency. Build trust by being transparent about large language model capabilities and limitations. Inform users about how your models work, the data they utilize, and the steps you take to ensure their security and privacy.
Tailoring your outreach. Target diverse users. Adapt your educational materials and approaches to different user groups, considering their technical expertise and preferred learning styles.
Interactive learning. Employ engaging formats like video tutorials, interactive quizzes, and simulations to make security education enjoyable and impactful.
In-application guidance. Integrate prompts and notifications within your large language model applications to remind users about best practices and potential risks in context.
Building a culture of security. Regular communication. Communicate security updates, emerging threats, and best practices updates continuously through newsletters, blog posts, and social media channels.
Feedback mechanisms. Encourage users to report suspicious behavior, provide feedback on your security measures, and participate in discussions about large language model security.
Promote community awareness. Collaborate with industry partners and user communities to raise awareness about large language model security challenges and best practices for responsible user behavior.
Remember, user education is not a one-time event but an ongoing process of building awareness and fostering a culture of security.
By empowering your users with knowledge and best practices, you create a stronger defense against vulnerabilities, build trust, and ensure a safe and secure large language model experience for all.
Physical security may seem less glamorous than digital safeguards, but it forms the crucial foundation for your large language model and embedded data lake ecosystem. Let's delve into how securing the physical realm strengthens your overall security posture.
The vital walls of defense, unauthorized access prevention. Robust physical security measures deter and prevent unauthorized individuals from accessing devices containing sensitive data and model components. This can include hardware tampering, data theft, or malicious manipulation.
Data breach minimization. Even in the face of a digital attack, strong physical security can contain the damage. It can limit the attacker's ability to exfiltrate sensitive data or manipulate critical hardware components.
Compliance and trust. Adhering to industry regulations and best practices regarding physical security demonstrates your commitment to data protection and builds trust with users and stakeholders.
Physical security best practices. Device security. Implement hardware-level security measures like tamper-resistant enclosures, encryption at rest, and secure boot for devices hosting the large language model chain and embedded data lake.
Access control. Enforce physical access control measures like secure entry points, restricted areas, and personnel authorization protocols to limit access to sensitive devices.
Environmental controls. Consider environmental controls like temperature and humidity monitoring, power backup systems, and fire suppression measures to protect devices from physical damage and maintain operational integrity.
Monitoring and logging. Implement physical security monitoring systems like CCTV cameras, intrusion detection systems, and access logs to track activity and detect potential breaches.
Regular audits and updates. Conduct regular physical security audits to identify vulnerabilities and weaknesses in your system and implement timely updates and improvements.
Large language model-specific considerations. Data location. Carefully consider the physical location of devices hosting your large language model and data lake, prioritizing secure environments with restricted access and robust physical security measures.
Supply chain security. Establish secure supply chain practices to ensure the integrity of hardware components and software throughout their life cycle, from procurement to deployment.
And remote management security. If remote management of devices is necessary, implement secure protocols and authentication mechanisms to prevent unauthorized access or manipulation.
Remember, physical security is not an afterthought, but an integral part of building a secure large language model and embedded data lake ecosystem.
By investing in robust physical safeguards, you create a stronger defense against both digital and physical threats, protect sensitive data, and build trust with your users.
This is the end of Section 12, Security Considerations for Integrating Large Language Model Chains with Embedded Data Lakes.
CONNELL-SEC.